Hi everyone, so today's topic is about dynamic programming and how you can learn dynamic programming that we are going to learn in this series, right? So I will start with a very famous quote about dynamic programming. This, those who cannot remember their past are condemned to repeat it, right? So I will explain what this quote means and what dynamic programming is all about. So we will talk about what is DP and where you can apply DP, and we will see few examples of dynamic programming in this video. Okay. So coming to the first question, let me start with a very simple example. Let's say I give you one problem. Let's say you need to compute this sum. Let's say 1 plus 1 plus 1 plus 1 plus 1. So I ask you, tell me what this sum is. So what you will do, you are just going to count the number of ones and you are going to say the sum is going to be 5. Now let me give you another problem, and let's say you need to count this. Okay. So now you will say this answer is going to be 6. So how do you compute this sum, right? So there are two ways. One way is, okay, this sum is 5 and I just need to add 1 to the previous sum to get 6. So what is this? So this is something that you have learned from the past, right? So this is what you have learned from past. Okay. So if you use this technique, if you remember what you have solved in past, you can easily optimize this problem, right? So other way would be, if you do a brute force, you will again spend a linear time in counting the number of ones. But if you know the answer to this sub problem, you can easily compute this problem in order 1 time, right? So this is what DP is all about. It is about remembering the problems that you have solved already, right? So this, for example, if I say this is a problem that you need to solve, right? And let me say, okay, this is a sub problem for this given problem, right? Okay. So what is DP? So DP is all about remembering the problems you have solved in the past, right? So it is, we need to memorize the solutions of sub problems that we have already solved and where we can apply DP. Again, very important question, right? So in lot of problems, you can see there are certain algorithms, there are certain problems which follow a greedy approach, there are certain problems which follow a DNC approach, there are many problems which can be solved using dynamic programming, right? So DP is all about logical thinking, and let me give you the two cases where you need to apply DP, right? The first property is called optimal substructure, which means you can divide a problem into smaller instances of the same type. For example, if I say I need to compute a Fibonacci number, right? So yeah, let me also tell about the second property, which is called overlapping subproblems. Okay. So let me explain you these two properties, and if a problem contains these two properties, you can definitely apply dynamic programming to solve that kind of a problem. For example, in this case, let's say this is a function sum, right? And it gets some data and you get the answer as 6. So if this problem is to compute sum, this problem is also about computing the sum, right? So the smaller sub problem is of the same type. So you can say sum of 6 elements in the array can be expressed as sum of 5 elements of the array, these 5 plus 1 or plus array of 5, whatever it is. So you can see it follows an optimal substructure. You can express a bigger problem in terms of smaller subproblems. So this is a bigger problem, this is a smaller subproblem. So this property of expressing a bigger problem in terms of subproblem is called optimal substructure. So this is what the optimal substructure is all about. And it is not just DP where you will follow optimal substructure. You can have optimal substructure in other types of problems also. For example, in divide and conquer. A very good example of divide and conquer is merge sort, where you divide an array of size n into two different arrays of size n by 2, and you say, okay, I'm going to solve this subproblem, I'm going to sort this array, I'm going to sort this array, and then I'm going to combine these two to get my sorted array, right? So here you also have this property of optimal substructure, but what you will not have here is the property of overlapping subproblems, right? So let's see what does overlapping subproblem mean, right? Okay, let me take another example, that is of Fibonacci numbers, right? For example, you need to compute a particular Fibonacci. Let's say you need to compute fib of 5, and you also know that f of n is given as, okay, let's say you want to compute f of 5, and you also know f of n is given as f of n minus 1 plus f of n minus 2. So in order to do this, what you will do, you will say, okay, let me just, yeah, so let me say fib of 5. To compute fib of 5, I need fib of 4 and fib of 3. To compute fib of 4, I need fib of 3 and 2. To compute fib of 3, I need fib of 2 and fib of 1. And to get this, I again need 2 and 1, I need 1 and 0, I need 1 and 0, and I again need 1 and 0. So if you carefully look at this diagram, so you will find that there are many states, okay, there are many states in this which are getting computed multiple times. For example, have a look at this subproblem and this subproblem. These two are exactly same. If you look at this, this and this, these are also same, right? So if you look at this problem, it has both of these properties. It has optimal substructure, where you are breaking down this problem into smaller subproblems of same type. And second, you can see that, yeah, so you can see that these problems, right? So if you compute fib of 3 here, you can store the answer, and here you do not need to compute fib of 3 again. So here we are wasting time, right? So when you write a recursive solution, you can analyze the complexity of this becomes O of 2 raised to the power n, right? So we need to remember the subproblems so that we do not compute this entire subtree again, right? So this is what DP is all about. It will allow you to memorize the solution of a subproblem that you have already solved, right? So second property is the property of overlapping subproblems. Do not compute the same subproblem again and again, right? So this is what we are going to do. So I hope you got an intuition what is DP, where it can be used, and we saw one example of Fibonacci, right? So let's see if we solve this problem using dynamic programming, what changes we will make. For example, again you start from f of 5, and this time in order to store your answers you need some data structure like an array or a hash table. So let's maintain a hash table or an array which can store the answer for all the states. So let's say this is a DP array, and it is going to store the values I have computed so far, right? So let's say I want to compute fib of 5, I am going to make a call on 4, and later on I will make a call on 3, but first let's expand 4. So let's make a call on 3, let's make a call on 2, but let's first expand 3. Let's make a call on 2, and let's make a call on 1, and let's also make a call on 1, and let's make a call on 0, right? So these states, we will come to these states later on, right? So when you reach 1, you know this is the base case. You can return 1 from here, you can return 0 from here. So, and when you are going to return anything from a particular state, you are also going to mark the answer for that state as whatever the answer is, right? So at fib of 2, you know the answer is going to be 1 plus 0, which is 1. At fib of 1, you know the answer is going to be 1, right? And at fib of 3, right? So when you're going to return from 2, you can see that this particular state is not computed as of now, right? So you can mark, okay, the answer is going to be 1. So at 3, you will make a call on 2 and you will make a call on 1. So you get the answer as 1 plus 1, which is 2. Okay. from 4 you are making a call to, so this is 2. From 4 you are making a call on 3, which is computed now. You are making a call on 2, and now you can check in this table if fib of 2 is computed or not. So as you can see that fib of 2 is already computed, so you can just return 1 from here. And this becomes 3, so you store the answer as 3. And at fib of 5 you are going to make a call on 4, and from here you are going to make a call on 3, and you can see that 3 is already computed, so you just return what? Fib of 3, which is 2. So fib of 5 is now 3 plus 2, which is 5, and you store your answer here. So this is how you are going to apply DP, right? So there are two ways in which you can apply DP. So this approach that we just discussed is called top-down approach. Okay. So this approach is called a top-down approach. The other way that you could have done to solve this problem would have been a bottom-up approach, right? So top-down is nothing but recursion. You apply recursion, plus you have a DP array which stores your answers of the sub-problems that you have solved. So this is called recursion plus memoization. Okay, so you are just doing recursion but with memoization of the states that you have solved these problems, so we will just remember the results of that sub-problems, right? So yeah, let's just quickly discuss about the bottom-up approach also. So for example, the bottom-up approach is very simple, right? So in this approach, you will start with the smallest sub-problem. Let's say this is 0 and this is 1. And you know that each box of this DP array can be computed by knowing the answers of previous two boxes. So you can clearly see that DP of I is nothing but sum of previous two states. So you can just see, so you can say, okay, for DP of 2 I need to sum these two values. So this is 1. To get DP of 3 I need to do 1 plus 1, which is 2. To get DP of 4 I need to sum these, which is 3. And to get DP of 5 I need to sum these, which is also 5, right? So this approach in which you are building your solution from bottom to top, you start from the smallest sub-problem and you go towards the biggest sub-problem, that is n. This approach is called a bottom-up approach, right? So I will just write it again. From smaller sub-problem you go towards a bigger problem, that is your DP of n. And in this case you start from the largest possible problem, which is DP of n, and you move towards the base case and you again build up your solution by coming from the base case towards the main case, right? So this is how top-down DP is, and this is what bottom-up DP is. In the next video, we will talk in more detail about these two types of dynamic programming along with the code. See you guys in the next part.
Hi everyone, so now we are going to look at how you can actually implement a dynamic programming program and how you can use the approach that we have discussed, right? So in the last video we talked about that you can use dynamic programming in problems where you have overlapping sub-problems, and you should also have optimal substructure, which means you can combine sub-problems to get the bigger solution for the bigger problem. So that property is called optimal substructure, right? So we also talked about one example of Fibonacci series in which you can say, okay, if you want to get the ith term of the series, right? So series is like this: 2, 3, 5, 8 and so on, right? So we said, okay, if we want to get this term of the series, let's say this is the nth term of the Fibonacci series, right? So we came out with a very simple recurrence that the nth term is nothing but the sum of previous two terms, right? And we said, okay, we can implement this recurrence as f of n equals to f of n minus 1 plus f of n minus 2. So this particular term is f of n minus 1, and this particular term is f of n minus 2. Right? So first of all, I'm going to show you the recursive implementation. Okay, and we will see if we use this recursion, the complexity is order of 2 raised to the power n. So this is exponential complexity. This is pretty bad. So this is a bad complexity, right? So what we will do, we will use dynamic programming to optimize this complexity, and if we use a DP based solution, the complexity will be order of n. And when we talk about DP, we will discuss both the top down approach and we will also discuss the bottom up approach, right? So let's get into the coding and start implementing our code. Okay, so first of all, I will make one function int fib which accepts n, and as you know, the base case, right? So in the base case, we need to give these two values if n is 0 or if n is 1, right? Then my answer is going to be n itself, right? So okay, so in any recursive program you will have a base case. If n is 0 or you can say n is 1, you can return n. Else you can say okay, you do not know the answer, so your answer for the nth term would be fib of n minus 1 plus fib of n minus 2. And let me just say okay, let me return the answer. So this is how you will actually implement a Fibonacci series program using recursion, and let us try to get the output for nth Fibonacci number, right? So let's say see out fib of n. Okay, let's build the program and let's run it. Okay, let's say I say give me the sixth Fibonacci. Now you can see the output is 8, and we can clearly check that sixth Fibonacci is actually 8, 0, 1, 2, 3, 4, 5 and 6, right? So now let me go into little more depth of recursion, right? How does the recursion work, right? How does recursion work in case of Fibonacci? And let us draw the recursion tree on one side, and let us also draw call stack on another side, right? And let me do it for a small example. Let me say okay, give me the fourth Fibonacci, and fourth Fibonacci is 3, and let us see how we are actually computing the fourth or the fifth Fibonacci, right? And let's see. Okay, so this fifth Fibonacci, this is 5, right? Okay, so what happens actually is when you say okay, I want fib of 5, it is going to make two calls, so one on 4, one on 3, but this call will happen later when the call for the 4 is finished. So in the call stack you have main, which makes a call on fib of 4. This is fib of 4, and from 4 you make a call on 3, from 3 you make a call on 2, from here you make a call on 1. So it goes to fib of 3, then it goes to fib of 2, then it goes to fib of 1, and since 1 is a base case, right, it returns a 1 here, right? So this returns a 1 here, and now 2 knows that I need two values, so it makes a call on fib of n minus 1, and it makes a call on fib of n minus 2. So every function makes two calls, so this answer is now 1, so this call will be initiated, so this will be fib of 0, and this will return a 0 here, so it gets an answer as 0. So it will add up the two values and it will return 1, so 2 will also return 1, and 2 gets popped off from the call stack. So let me just erase this and so on, right? Okay, now you have fib of 3, and again it is going to make a call on fib of 1 because 3 is also going to make two calls, so it returns a 1 because it's a base case, and now fib of 3 returns a 2, so this returns a 1, and it already had one answer which is 1, so it adds them up and returns 2. So fib of 4 had actually made two calls, one on fib of 3 and another call will be made on fib of 2. So what will happen, these two will go off from the call stack, and you will make a call on fib of 2. Okay, so you will make a call on fib of 2. So now fib of 2 is there in the top of the stack. So let me just erase this. And again, fib of 2 will make two calls, one on fib of 1, which gives 1 to it, another call on fib of 0, which gives 0 to it, right? So it makes a call on 1, which goes off from the stack, and it makes a call on 0, which returns a 0, and this actually returns a 1 here, right? And now 4 is going to return 3, and finally 5 is going to make a call on 3, and again the same story is going to get repeated. So remember how we computed fib of 3. So fib of 3 will be computed now. So in main you had made a call on fib of 5. So in main you make a call on fib of 5, which makes a call on fib of 3, right? So this 3 will be computed in the same manner. So you will make a call on fib of 2, and you will make a 2 will make a call on fib of 1 and 0. It returns a 1, it returns a 0, it returns 1 again, and it makes a call on fib of 1, which returns a 1 here, right? So 3 returns 2. So for 5 you get two answers, one is 3, one is 2, so this returns a 5 here. So fib of 5 is finally 5. This is what you get. But why this is going to take time? So let us talk about time complexity of this solution, and let us also analyze the space complexity, right? Space complexity in case of recursion is basically the extra stack space that you are using, right? So any extra stack space that you use will also add to your space complexity apart from any other space that you are using, right? So in case of recursion, the space complexity will be computed by the maximum depth of the call stack. So at any given point you have n number of stack frames. Okay, so in our case this space complexity would be order of n, right? Because you cannot have all of these frames parallel in the stack, so it is actually like this. When you're going into this branch, the space is increasing, right? So when this node goes off from the stack, the space decreases. When this node is added, the space increases again, right? And so on. You will find, okay, so if I say this is the flow of the program and this is the space, you will find that space is maximum at a certain point, right? So at these 2 points, when you have this 1 and this 0 in the call stack, space utilization is maximum, and this is equal to order of n, right? This is the space complexity of the program. And what about time, right? So we can say, okay, if so we basically need to count how many operations we have performed for a given n, right? So you can say, okay, for a given n we just make 2 calls for every n, right? So for a given n, right, we make 2 calls, one on n minus 1, one on n minus 2. From here we again make 2 calls, n minus 2 and n minus 3. From here we make 2 calls, n minus 3 and n minus 4, and it goes on, right? So basically you need to count the number of nodes that you are generating in the tree. So clearly you can see the first level has 1 node, second level has 2 nodes, next level has 4 nodes, and the last level will have approximately 2 raised to the power n minus 1 nodes, assuming the tree is complete, right? And you can see there are going to be lot of overlapping subproblems also. For example, this n minus 2, this whole tree will be same as this whole tree, right? This n minus 3 is going to be same as this, right? So there are going to be lot of overlapping subproblems that you can also see here, right? So you are computing 3 here also, and you are computing 3 here also, right? Similarly, you are computing 2 here also, you are computing 2 here also, and you are also computing 2 here, and you are also, right? So these number of sub problems are going to increase as your n is going to increase, right? So as n increases, your overlapping sub problems also increase, right? and that leads to the bad time complexity of this program, right? And if you carefully analyze how many operations you are going to do for a given n, you can clearly say, okay, the total number of steps involved is 1 plus 2 plus 4 plus up to 2 raised to the power n minus 1. This is order of 2 raised to the power n, right? So this is the time complexity of the program. So we can say, okay, the time complexity is order of 2 raised to the power n. Now why do we need dp? We need to bring this complexity down, right? Let us analyze how we can use dp, and in the next video we will write the top down solution for Fibonacci, right? It will be a dp solution that we will see in the next video. So thanks a lot, see you guys in the next part. Now we will see how we can make this recursive solution into a DP solution, right? So this approach will be valid for all problems. Wherever you are able to use recursion and you have overlapping subproblems, you can convert them into a DP solution, right? So the idea is that we want to basically store the overlapping subproblems, right? So what we will do, we will maintain a array to store the solution for overlapping subproblems, right? It basically means you are adding some memory to your recursive solution, right? So now the recursion knows what states have been computed, right? Okay, so basically this is recursion plus memoization, right? Which means you are adding some memory to your recursive solution, right? So let us see what is this concept of adding memory. So let's say, okay, I have a DP array. Let's say maximum n is 100, and let's say this is initialized with all zeros, right? So what I can do, I can pass this DP array to this function, and in this function I can accept the DP array. And now what we are going to do, now here in the recursive case, we are actually computing fib of n, right? So we are computing what is fib of n. That is not known to us, but it might be possible when we are on a given call, we have already computed fib of n, right? So whenever we compute some value, we are going to store it in dp of n. So I can say if dp of n is not 0, which means that value has already been computed in some other call. So I can just say, okay, return dp of n. So this is nothing but the lookup. And whenever you're going to compute some value, you're going to store in dp of n. So these are the two steps that you need to add to make a recursive solution as a top-down dp solution, right? So now let us dry run this code and see what happens if you compute fib of 5. Let me see, okay, I have a dp array like this, 0, 1, 2, 3, 4 and 5, and in the beginning everything is going to be 0, right? Okay, so okay, we say, okay, we are going to compute fib of 5, so you get n, so 5 makes a call on 4, and now you can see, okay, dp of 4 is not computed because it is equal to 0, right? So we make a call on fib of 3 and fib of 2. We make a call on fib of 3 and 2, and from 3 we will make a call on 2 and 1, and you can also see that 2 is also not computed, and when you make a call on 1, you hit the base case, because if n is 1, you return 1. So this will return 1, but this call will be made later on, as we saw in the last example also, right? This will also make a call on 3, but later on. So as of now, we are just going in this direction, right? So we are not going in only this direction now. So from 2, you can say, okay, fib of 2 is also 0, which means it is not computed. So you make a call on 1 and 0. So you first make a call on 1, which says, okay, because I am the base case, I am going to return a 1. So it returns a 1 here, right? And it will make a call on 0. It is also the base case, and it returns a 0 here, right? So now what is going to happen when you're going to say, okay, I know the dp of 2 is going to be 1. So before returning, you store the answer in dp of 2 as 1. This answer is going to be stored as 1. This returns a 1 here. And from 3 you make a call on 1, and since 1 is the base case, it returns a 1, right? So remember, in the dp array we have not updated this as 1. You can update, but since it is a base case, we are not looking the answer in the dp array, right? But you may update this answer as well, right? But it won't matter because you're first checking the base case, then you're checking dp of n. So at dp of 3, you know the answer is going to be 1 plus 1, which is 2. So you store dp of 3 as 2. So dp of 3 becomes 2. So this returns a 2 here. Now from 4 you make a call on 2, and when you are at 2 you check if dp of 2 is 0 or not. So clearly dp of 2 is non-zero, which means 2 has already been computed. Where? Here. So we have already computed 2. This directly returns a 1 here. So dp of 4 returns a 3 here, right? And now 5 will make a call on 3, and since dp of 3 is already computed and it is not 0, so you just return from this point. Instead of evaluating the tree, you directly return, right? So this returns a 2, and dp of 5 becomes 3 plus 2, 5, and 5 is stored in, right? So this approach is called a top-down dp. So this is called top-down dp, because you are going from a top of the recursion call towards the bottom, which is the smallest case, and then you are building up your solution, right? This approach is called top-down dp, or it is also called recursion plus memoization, right? So this is the memory that you have added to your function. So this is basically the memory, right? Or it's basically an array. You can also use a hash map in some cases where your these values, right? So these indices are very large, right? So maybe in some problems you will see that you cannot have a very large array, but you can have a large you can store a large index in a hash map, right? Maybe in some problems we will do, right? So this approach is top-down dp. And let us also talk about the complexity, right? If we talk about the space complexity, it is going to remain same, because you can see the maximum depth of the call stack is order of n, so it is going to be O of n. And what about time, right? So clearly you can see you have evaluated n nodes here, and you have looked up values for n minus 1 nodes here, right? So it is going to be n plus n minus 1, which is again order of n. So you have significantly reduced your complexity from exponential to linear, which is a great improvement, right? So your complexity has been reduced from exponential to linear. And let us run this code just to see if it works well, right? So let me say, okay, yeah, so here we need to also pass our dp array, and here also we need to pass our dp array. Okay, so build is successful, and let us run the code now. Let me give dp of 5. You can see the answer is 5. Let me give dp of 100. Okay, so dp of 6 is going to be 6. And yeah, dp of 100 won't work because we have made an array of 100, right? Maybe you can try for dp of 12, and yes, it's 144, right? So according to the problem, you can have proper constraints and you can solve this problem, right? Okay, so in the next video we will discuss the bottom-up approach, which is again going to be very simple one, right? Hi everyone, so now let's talk about the bottom-up approach to solving a Fibonacci series problem. So the idea here is we won't be using recursion, we won't be forming our solution from the very basic, right? So let me define a program Fibonacci bottom up which accepts n, and we will see how we can solve this problem, right? So the idea is you will again create an array which will store the answer for every state, but instead of going from top to down, you will just do it in a bottom up manner, right? So the first approach that we have seen is a top down approach, and second approach that we are going to see is going to be a bottom up approach. So idea here is you will make a array and you will initialize the base cases in this array. So you know dp of 0 is 0, dp of 1 is 1, and for all indices starting from 2 to n, you will say, okay, if I want to compute this value, this ith index, what is this dp of I? So you can clearly see it is nothing but the sum of previous two values. So you can use this dp of I minus 1 plus dp of I minus 2, and you can repeat it for all the states. This will give you 1 here, this will give you 2 here, this will give you 3, 5, and so on, right? So just implement this recurrence using a loop, and you can clearly see, okay, if you do this, your complexity would be order of n about for time, and since you are using a extra array, it would take order n space order. This would be the space and the time complexity of the bottom up approach. So let's quickly implement this one. So int dp of, let's say, 100, and I'm assuming 100 is the largest number for which you want to compute the answer, right? And if n is large, you can have a large array, or you can do dynamic memory allocation as well, right? And let me initialize everything with a 0 except dp of 1, which is going to be 1, right? So now you can say, okay, for I equals to 2, I less than equals to n, dp of I can be computed as dp of I minus 1 plus dp of I minus 2, and finally you will return dp of n. That's it. So instead of calling fib, we will call fib of bottom up, and here we do not need to send the dp array, right? So this is your bottom up approach to solve the Fibonacci problem. Let's build the solution and let's run it. Okay, so dp of 5, it's 5, dp of 6, it's 8, and dp of 12, it's 144. So it's correct. So you can clearly see that this is also working, and we have also already discussed the space and the time complexity for this. So one optimization that you can make, let's talk about space optimization, right? So clearly you can see that in order to compute the current number, right, you just need to store the last two values. So if you want to compute 5, you need the answer for dp of n minus 1 and n minus 2. You do not need to store entire array, right? So what you can do, you can take two variables, let's say a and b, that store the values of last two Fibonacci, right? So you can store the last two Fibonacci and you can eliminate this array. So if you do this, your space complexity from order n can be reduced to order 1 space, right? So maybe let's try this one too. So int Fibonacci, and let's say space optimized. So you get n and you check if n is 0 or n is 1, you return n. Otherwise you can say, okay, I have a which is 0, I have b which is 1, and I want to compute c. So you can put a loop for int I equals to 2, I less than n, I plus plus. So your new Fibonacci c would be a plus b. So it would be the sum of previous two terms, and once you compute c, you also need to update Okay, so this is 0, this is 1, so this is A, this is B, and C I said is sum of these two, which is going to be 1. So for the next time you want to compute these, you want to add these two, so you can say okay, this is A and this is B. What you will do, you will say okay, in the new case A will become equals to B and B will become equals to C for the next term, right? For next term. And when you will compute C, you will get the sum of these two, which is 2. Then you will compute sum of these two, which is 3, and so on, right? So A becomes equal to B, B becomes equal to C. So A stores the first Fibonacci and B stores the second Fibonacci, and C is your final answer, right? Okay, so finally you can say okay, return C. That is your final Fibonacci. So this is again a bottom-up approach, but with space optimization. Okay, so let's build this, and let me call fib space optimization, and let me run this. So the fifth Fibonacci is right, so basically the indexing is 1 less, so it should be less than equal to n, right? So let me build again and run this. The fifth Fibonacci is 5 and the sixth Fibonacci is 8, so it means this is correct. And now you have seen 4 variants of Fibonacci, right? So one is your recursive approach, another is your top-down approach, another is your bottom-up approach, another is your bottom-up approach with space optimization, right? So we also have another approach that we will cover later. So this approach also reduces the time complexity of Fibonacci, and it is based upon a concept called matrix exponentiation, and we will cover this as an extra topic little later on, right? And this will reduce your complexity to order of log of n. So this would be your space complexity, right? So it has to do something with the recurrence. The way you are going to compute nth Fibonacci will depend upon what is the value of n by 2th Fibonacci, right? And so on. So if you are able to break your recurrence of n in terms of n by 2, you can also reduce your complexity to order of log n, right? So this is a slightly advanced topic that we will cover later on. So it's not exactly DP. So there is another technique called matrix exponentiation, right? So we will cover this later on, right? So thanks a lot. See you guys in the next part.
Hi everyone, so now we are going to discuss one problem that is called minimum steps to 1. Right? So in this problem you are given a number n and you need to convert this number into 1, and you are given certain conditions that you can reduce n into n by 3 if n is divisible by 3, you can reduce n into n by 2 if n is divisible by 2, or you can subtract 1 from it. For example, let me start with the number 5 and I need to convert this into 1. So what you can do, you can say okay, I can go to 4, and from 4 I can go to either 2 by dividing it by 2, or from 4 I can go to 3 by dividing it by subtracting 1 from here, and from here I can go to 1 by subtracting 1, or I can go to 1 by dividing 1, and from here I can go to 1 by dividing it by 3, or from here I can go to 2 by subtracting 1, and from here again I can go to 1 by subtracting 1 or by dividing it by 2. Okay, so you need to count what is the minimum number of steps needed to make this number as 1, right? For example, if I give you a number 9, you can clearly say okay, let's divide by 3 to make it 3, let's divide it by 3 to make it 1, and you can see you need only 2 steps. But do you think this kind of approach, that if we divided with a larger number to reach a smaller sub-problem, is optimal, right? So you can think of some test cases and you can find out the answer, right? And let me tell you that this approach is not optimal, right? So if you think greedily, right, so greedy approach is not correct. So greedy is not going to pass. Why? For example, if I give you a number 10, right, you can say, okay, the greedy approach would say, we will reduce this to 5 by dividing it by 2, because 10 is divisible by 2, and from 5 I have only one option, I can go to 4, and from 4 I can go to 2, and from here I can go to 1. So you can see you need 1, 2, 3, 4 steps. You would need 4 number of steps. But in the ideal case, right, so if you try out all possibilities, from 10 you can go to 9, you can also go to 5, and you can say, okay, in order to make 10 as 1, I will first make 9 as 1, and to make 9 as 1, we know we can go to 8, we can go to 3, and that's it. And from 8 we know we can go to 7, and we can go to 4, and so on, right? So this will continue, but we know that we will reach 1 from this. So we need to find out the shortest path that takes 10 to 1, and from 5 again we know this tree is going to get repeated here. From 5 I can go to 4, and so on. Okay. So I need to find out what is the optimal answer for this sub-problem and what is the optimal answer for this sub-problem. For 9 we already know the answer is 2, because we have computed here, right? And from 5 we know the optimal answer would be 1, 2 and 3. You need 3 steps here, right? So in order to convert 10 into 1, how many steps you would need? You will say, okay, from 10 I can go to 9 or I can go to 5. So I will choose the one which gives me the minimum steps. So I can say my answer is, let's say this answer is, from n you go to n by 3, you can go to n by 2, or you can go to n minus 1. So you need to compute the answers for these sub-problems. Let's say this answer is x, this answer is y, this answer is z. So you can say f of n, which is the minimum number of steps to make n as 1, can be written as minimum of x, y, z plus 1, because you need one step to go from the current sub-problem to the sub-problem, right? So this can be again written as minimum of f of n by 3, f of n by 2, and f of n minus 1 plus 1, right? So this is what the recurrence would be, right? And this is the optimal solution to solve this problem. You are not going to say, I'm going to pick the one which reduces my sub-problem immediately, right? But pick the one which is globally optimum, right? Which gives you the best solution till the base case, right? So let me also just dry run this one. So for example, from 10 you make a call on 9, from here you make a call on 3, and from here you make a call on 1. And this one is going to return 0, because in order to make 1 as 1 you need 0 steps. And from 3 you will say, okay, I can go to 2 also, I can go to 1 also. This 2 is going to return, this is going to make a call here, and this 1 is going to say 0, and this 2 is going to say 1. So 3 is going to compute, there are two ways, 1 via 2, 1 via 1, so minimum is 0, plus 1 is 1. And from 9 you make a call on 3, you make a call on 8, and you get to see, let's say this is some a number of steps. So minimum of 1 and a would be 1, and if you add a 1 here you will get this 2. So this returns a 2 here, and similarly this returns a 3 here, and you can say, okay, for 10 the answer is going to be minimum is 2 plus 1 you add, so it returns a 3 here. And here you can clearly see that there are many states which are going to be overlapping sub-problems. For example, you can clearly see that this 4 and this 4 is going to be a overlapping subproblem, and it also satisfies the two properties we talked about. The first one is optimal substructure, where you can express a given problem in terms of similar subproblems, right? And second is your overlapping subproblems property, right? So you can have these two properties here, and you can solve it using dynamic programming, right? So this approach that we just discussed is called a top-down approach, and let's spend some time on talking about how we can approach this in a bottom-up manner, right? So top-down is a recursive approach with memoization, and bottom-up is an iterative approach in which you just need to compute the DP array in a bottom-up manner, right? So let's say this is 1, this is 2, this is 3, this is 4, 5, 6. Okay, so let's say you need to know, okay, the very first thing that you need to know in this case is what is DP of 1, the smallest possible case. So you can clearly say the DP of 1 is going to be 0, because in order to make 1 as 0, you need only 0 steps, right? And let's also compute DP of 2. So what we are going to do, we are going to use a loop from I equals to 2, I less than equals to n, and I plus plus, and you need to compute DP of I. And DP of I can again be expressed using this kind of a relation, right? So what we are going to do, okay, so at DP of 2, I can say from 2 I can reach what states I can reach from 2. So you can reach 1 by dividing 2 by 2, or you can reach 1 by subtracting 1 from 2. So you can reach only this state, and the answer for this state is 0. So your final answer is going to be minimum of 0 and 0 plus 1. So this is going to be 1. So DP of 2 is going to be 1. What about 3? From 3 you can end up at 2 if you subtract 1, or if you divide it by 3 you can end up at 1. So these are the two states that you can reach. So the minimum of 0 and 1 is going to be 0, and if you need to add 1, it will become 1. What about DP of 4? From DP of 4 you can go to 3, and you can go to 2. So minimum of 1 and 1 is 1 plus 1, it gives you 2. Let's talk about DP of 5. From 5 you can end up only in one state. From 5 you can go only to 4, because it is not divisible by 3, it is not divisible by 2. So the answer is going to be 2 plus 1, 3. From 6 you can end up at 5, you can end up at 3, you can end up at 2. So your answer is going to be minimum of 1, 1 and 3, which is 1 plus 1, it is going to be 2. Similarly for 7 you can do the work, 8 you can compute, 9 you can compute, and so on. For example, if I talk about DP of 9, you can end up at 8, you can end up at 3, and you take the minimum and get your answers. Similarly, you will you compute this till the last state, right? And you can say this DP of I can be computed in O1 time. So the overall complexity of this would be order of n. You need to compute n states, and each state takes order 1 time to compute. And similarly in the top-down approach, if you use memoization, you will make sure that you are not computing each state more than once, right? So this makes your entire time complexity as order of n, both in the top-down and in the bottom-up case, right? So in the next part, we will see the implementation, but I would suggest if you can just write down the code yourself, and it's a pretty easy code that you can definitely write. So thanks a lot. See you guys in the next part.
Hi everyone, so now we will talk about the problem minimum steps to 1, and we have already discussed the approach along with the dry run. So I'm just going to implement the code. The first would be my top-down approach, and second would be my bottom approach. So let me say, okay, I want to write a function int minimum steps which accepts the value of n, and it should return how many steps it will take to make this number as 1, and it's given you from n. You can go to n by 3, or you can go to n by 2, or you can go to n minus 1. So let's think about the base case, and let's also think about the recursive case, right? So first we will write recursion, then we will make it as a top-down DP problem. So base case would be that if you have already reached 1, right, the smallest possible value of n, that is 1, then it will take 0 steps to make it as 1, right? So if the number is already 1, you do not need to do anything, so you will just return 0. In the recursive case, as I said, you have 3 options, right? So let's say the first option would be to okay, let me say you have 3 options, option 2 and option 3, and all of the 3 options are not valid for every value of n, because if n is not divisible by 3, you will not have option 1, right? So let me say by default these options are going to store int max. Okay, int max goes in the header file called climits, which means a very large value, and we have seen the recurrence is going to be minimum of the 3 options, right? So first option, if n is divisible by 3, then you can say, okay, I can compute option 1 by making a call on min steps, and here I give n by 3. So let's also include the DP array that we would be using, and let me give the DP array, right? If n is divisible by 2, I can update my option 2 as min steps n by 2 and the DP array. Otherwise my option 3 always would be min steps of n minus 1, and I give the DP array, right? So my final answer, right, my answer is going to be minimum of option 1, option 2 and option 3. So min function takes 2 arguments, so in order to take minimum of 3 numbers, I need to have this plus 1, right? Whatever it is, I need to take plus 1, or even okay, I will just do a plus 1 here and I can remove this plus 1, right? So my final answer is going to be answer. So this is going to be DP of. So this is going to be the top-down approach, and let me just again explain what we have done here and see out minimum steps of n given the DP array, and let's make a DP array and it's going to be 0. And also we also need to look up if a particular state is already computed. Look up if n is already computed. So if DP of n is not equal to 0, which means there is some value lying in the DP of n, we will just return DP of n. So this makes this recursive solution as a top-down DP problem, and this is the compute if DP of n is not known, right? Basically for the first time you will compute and store your answer, right? So let us dry run for, let's say, n equals to 10. Let's say n is 10, right? Then you have 3 options. Option 1 is infinity, option 2 is infinity, option 3 is also infinity, but n is divisible by 2. This case won't execute, so no call from here. And since n is divisible by 2, so you will make a call on DP of 5. You will ask, okay, how many steps you would need to make 5 as 1, right? So this is going to be a call on n equals to 5, and here you are going to make a call on n equals to 9. 5 will make a call on 4, and 4 will make a call on 2, it will make a call on 3, it will make a call on 1, it will make a call on 1, it will make a call on 1, it will make a call on 2, it will make a call on 1 and 1. and 9 will make a call on 8 and so on. It will also make a call on 3 and it will make a call on 1 and 2 and so on, right? But we know the smallest path is going to be this path from 10, 9, 3 and 1. So this one is going to return 0 because to make 1 as 1 you need 0 steps, and this 3 is going to return 1 because you took 1 step here. So this option would be okay. So this option for 3, because 3 is divisible by 3, so this answer is 0 plus 1 1. So this 3 is going to return 1. So you need 1 step to make 3 as 1, right? Let me just erase this. Yeah, so this 1 is going to return 0, this 3 is going to return 1, and this 9 made a call on 3, right? So this 9 will say okay, my answer is going to be 2, and similarly 5 is going to have some answer, which is going to be from 5 you go to 3 and 1, so it returns 0, it returns a 1, it returns a 2, and 5 returns a 3, right? So but you are taking a minimum of all possible options. So at n equal to 10 you take a minimum of infinity, 3 and 2, and you say okay, the final answer is going to be 3. So you can say okay, there are 3 steps. From 10 you go to 9, from here you go to 3, and from here you go to 1. So the final answer is going to be 3, right? So this is how we have actually executed this code. So from every state you are going on the all possible sub problems, and you are getting the answers from some problems using this recursive function call, and you take the minimum. And if some state is already computed, for example 3 is already computed here, so you won't be computing this 3 again, right? So since it has overlapping sub problems and we are able to use the memoization thing, so the complexity would be order of n, because from 0 to 10 here you won't be computing any state more than once, right? So this can be done in, this is done in order n time, right? But if you use recursion, it would again turn out to be exponential. So let us build the code and let us run it and say okay, minimum steps for, let's say n equals to 10, right? It says 3 steps. Let's say n equals to 5, it says again 3 steps. From 5 you go to 4, from 4 you go to 2, and then you go to 1. It takes 3 steps, right? Okay, so in the next part we will cover up the bottom up approach for the same. Hi everyone, so let's talk about the bottom up approach to the minimum steps problem. So we are going to talk about bottom up approach implementation, right? So again, you need a DP array, and I'm assuming the size is 100, but it can be anything. So what you need to do, we first need to figure out the base case, right? And that we have already seen in the top down part, that if n is 1, the answer is going to be 0. So what you can do, you can initialize everything with a 0, and then you can say okay, if right, if dp of 1, right, so dp of 1 is also going to be 0, that is obviously already initialized here, right? So what you can do, you can put a loop from int I equals to 2, I less than equals to n, I plus plus, and you can compute the value of dp of I, right? So let me just quickly go through how we will implement this bottom up approach. For example, you want to compute, let's say dp of 1 is 0, dp of 2, 3, 4, 5, and so on, let's say 6. So from dp of 2, so this is your value of n, so from this n you can go to 1 by doing n by 2, or you can go to n minus 1, right? So in both of the case you will end up at 0, so your answer is going to be minimum of these two, which is 0 plus 1, so it is going to be 1. At dp of 3 your n is 3, so you can go to dp of 1, or you can go to dp of 2 by doing n by 3, or you can do n minus 1. So dp of 1 is 0, dp of 2 is 1, so your minimum of 0 and 1. So your minimum of 0 and 1, it is going to be 0. Your answer is going to be minimum of 0 1 plus 1, so it's going to be 2. Similarly at 4, you can end up at 3 or you can end up at 2. That's the two options by doing n by 2, or you can do n minus 1, because 4 is not divisible by 3. So minimum of 1 and 2 is 1, so your answer is going to be 2. At 5, you have only one option. You can only end up at 4 because you can only do n minus 1. So your answer is going to be minimum is 2 plus 1, 3. At 6, you can either end up at 5, or you can end up at 3, or you can end up at 2. Sorry, at 3 your answer is going to be 1, because you can also end up at 1, right? So this is minimum is 0 plus 1, it's going to be 1, right? So this is a mistake, so it's 1. And at 6, you can again end up at n by 3, n by 2, n minus 1. So at n by 3, which is 2, the answer is 1. At n by 2, which is 3, the answer is 1. At here, the answer is going to be 3. So minimum is 1 and you add a 1, so it becomes 2. So that this you will repeat for all values of n. And you can see that this operation of finding the minimum takes O1 time. And since you're doing it across n cells, the overall complexity would be order of n, right? So this is what I'm going to do. So I'm going to take three variables, option 1, option 2, option 3. All of them will be initialized as int max, and then I can say, okay, if n is divisible by 3, then option 1 is dp of I by 3, right? So now remember, instead of saying the current position as n, we have current position as I, right? So I is the current state that you're going to compute. So you're computing dp of I, and that will depend upon dp of I by 3, I by 2, and I minus 1. So if n is divisible by 2, then option 2 would be dp of I by 2. And since we are filling up this array in a bottom up manner, these states would already have been computed, right? Otherwise, option 3 is always there, which is dp of I minus 1. And finally, you can say, okay, I have seen all the three options. My answer, so my answer is, whatever is my answer, it will be stored in dp of I. It will be minimum of option 1 and 2 and option 3. And you can add a 1 here, right? Or you can add 1 here also, right? So that does not matter. This is my dp of I, and I can say return dp of n. That's it. Okay, so now let's run this code. See out minimum steps, bottom up, and you give n. So minimum steps. Okay, so for 10 you can see you need 3 steps. For 5 you need 4 steps, and for 6 you need 2 steps. So this is what we have seen already, and this is how we can implement the bottom up approach to minimum steps to one problem, right? So I hope you would find this approach useful, and this is something that we are going to use in couple of more problems, right? So in a bottom up solution, you are just going to iterate a linear array, and you just need to think, how do you compute the value for the ith state? Okay, for the current dp of I, how it can be computed from the smaller sub problems, and those sub problems have already been computed when you are iterating from a small to big n, right? So this is what you need to do in a bottom up dp problem. Thanks a lot. See you guys in the next part.
Hi everyone. So now we are going to discuss one very popular problem that is called minimum coin change, right? So let's see what the problem is. So you're given that you have coins of certain denominations. Let's talk about Indian currency, right? So in Indian currency, you have different type of coins. You have a 1 rupee coin, you have 2 rupee coin, you have 5 rupee coin, even you have 10 rupee, 20 rupee, 50 rupee, and you have 500 rupee, and you have 2000 rupee, right? So let's say, and you need to make a change for certain rupees. Let's say I want you to give me a change for 137 rupees, right? So you need to make 137 rupees change by using uh, minimum number of coins or currencies from the available denomination, right? And for each type of coin or currency, you have infinite coins. Okay, so you have infinite coins of same type, which means you can use the same coin multiple times, right? So the question is, what is the minimum number of coins needed to make 137 rupees, right? So the first approach that might come to your mind again would be a greedy approach. So if you want to make 137 rupees, let us first pick the largest available currency. Okay, so we also have a 100 rupee note here, right? And we also have a 200 rupee, right? So I just missed those. So yeah, so the first approach is that, okay, let us pick the largest one, so that will basically we would be left with 37 rupees, and we have already collected a 100 rupee note, right? So in order to get the 37 rupees, you can pick the largest possible currency denomination that you can pick, which is less than equal to 37, that is 20. And if this is a sorted array, you can use binary search to just find out 20, the lower bound, and you are left with 17 rupees, right? And you have picked 20, right? And now to make 17 rupees, you can say, okay, the lower bound is 10, so I'm left with 7 rupees. And to make 7 rupees, I know I can pick 5, and I'm left with 2 rupees. To make 2 rupees, I know I can pick 2 rupees to get 0, right? So you can see, you can pick 5 followed by 2, right? So you need 1, 2, 3, 4 and 5. So minimum number of coins you need is 5 coins, right? So I want to now discuss whether this approach is optimal or not, right? So this is something that many students will think is the right approach, but actually it is not, right? So it is also true that this type of approach is true for Indian currency, but you have to make test cases to make sure that it works for all other currencies also if you are going to implement it, right? But it is true for Indian currency, right? So if you see that this approach will work for Indian currency only, not for all possible denominations, right? So let me give you one counter case, and let's say you are going to some other country where the coins are available in a different denomination. Let's say the coins are like this. So you have let's say coin of 1 rupee, you have a coin of 7 rupee, and you have a coin of 10 rupee, right? And let's say I want to make 15 rupees as the change. I want to make 15 rupees, right? So again, if you go with this greedy approach where you are going to pick the largest possible coin which is less than equal to 15, you will pick 10, right? So once you pick 10, you are left with 5 rupees, okay? And in order to make 5 rupees, you can pick only one coin. You will have 5 minus 1, which is 4. This is 5. And again, to make 4 rupees, you will make 3 rupees, and then you will make 2 rupees, then you will make 1 rupee, and then you will eventually get 0 rupee, right? So yeah, let me just change the marker. Okay. So if you carefully see this, right, you will see that you actually need 6 coins which is not the correct answer, right? So the best answer would be if you could have done 7, 7 and 1, right? If you could have done, I will take, okay, 7 coins and 1 coin, that actually make 15 rupees using 3 coins, right? So clearly the greedy approach in this case is not optimal, right? So the best way to verify whether greedy will work or not, you make a counter test case. You think of a test case where you approach greedy is going to fail, and now you can be sure that this certainly can be solved using dynamic programming. We do not know what is the best way to make this given change, so we would try out all possible options, right? So now the solution that we are going to use will be a dynamic programming solution, and dynamic programming is nothing but an optimization to the recursive formulation, right? So recursive formulation will allow you to consider all possible cases like this. So if I say, okay, I will start with 15 rupees, in what states I can land up, right? So if I pick a coin of 1, let me also draw that available coins are 1, 7 and 10, right? So if I pick a 1 rupee coin, I can reduce my amount to 14 rupees. If I pick a 7 rupee coin, I can reduce my amount to 8 rupees. If I pick a 10 rupee coin, I can reduce my amount to 5 rupees. Now you can see these are your sub problems, right? So these become your sub problems. If you know the solution to these sub problems, you can definitely form the solution for this. So let's say to make a change of 14, you need X number of coins. To make a change of 8, you need Y number of coins. To make a change of 5, you need Z number of coins. So your answer, right, I'm just writing it here. So your answer would be nothing but minimum of X, Y, Z plus 1. So it is very similar to the minimum steps to 1 problem that we had discussed in the last video. So your answer would be minimum of all these 3 plus 1, right? And since this follows an optimal substructure, you can again break down every problem in the same manner. So you can break down 14 into, okay, I can go to 13. If I pick 7, I can go to 7. And if I pick 10, I can go to 4. Again, from 8, I can go to 7. And I can go to 1. And I can go to 10. And similarly from 5, I can go to only one state, which is 4, right? And this is going to be quite, so from here you can end up at 12, you can end up at 13 minus 7, which is 6, or you can end up at 3, and from here you can end up at 6, and you can also end up at 0, right? So this 0 becomes your base case, right? And we know that this is the first state which has reached 0, because all other are going to take more time, or they will take a longer path to reach 0. So we can say, okay, let's return a 1 from here, right? So remember, I'm not drawing all these states because it is going to be a pretty large tree, and we are going to compute it in a left to right order, right? So it's not that we are going to compute this directly first, but yeah, this would be one of the answers in this branch, right? So 0 is going to return that, okay, if I am left with 0 rupees, I need 0 coins to make the change, right? So this is going to return a 0 from here, right? So let me just use a different marker, okay? So we are going to use return a 0. And from 7 I can say, okay, I came to know this is some answer A, this is some answer 0, and I know the answer is going to be minimum of these two, which is 0, okay, and this is going to return a 1, right, using this formula. And since we are at 14, we know, okay, the x is going to be minimum of this value. Let's say this is some A, this is 1, this is some B. So minimum of A, 1 and B, and I am assuming this is the minimum, so the minimum is going to be 1, so x is going to be minimum of these 3 plus 1, which is going to be 2, right? And similarly from this you will get one of the answer, and now you can see that this is also going to reduce it to a similar state, and you can see we have computed the answer for 7, which is 1, and similarly we will compute the answer for 7 here, but we will not make a call, right? So since we are doing a top-down DP, we would have an array where the answer of 7 is already stored as 1, right? Because you need one coin to make a change of 7, and that coin is the 7 rupee coin. So this answer is going to be 1, and similarly y would be 1, and if you take a minimum of x, y and z, it is going to be 1, right? So z is going to be something which is greater than equal to 1, right? So z is going to be 4, right? Because it is going to be 5. You need 5 coins to make a change of 5. So minimum is going to be 1, and if you add 1 here, right? Okay, so yeah, for 14, so this is actually going to be 2, right? It is going to be 2, yeah. So when you take minimum from this, you will also add a 1 from here, right? So this, the answer for 14 is going to be minimum of all these, which is A1 and B, which is 1 plus 1, which is 2. Similarly, the answer is going to be 1 plus 1, which is going to be 2. So the minimum of 2, 2 and 5 is going to be 2, and you add a 1 here, you get 3. So in order to make 15 as the change, you would need 3 coins, right? So this is the recursive tree, and this is what is going to happen in the top-down approach. You are going to do recursion with some memoization, right? So if I talk about what are the calls you are going to make, so in order to compute f of n, you are basically trying all possible coins, right? From 15 you are going to, okay, so what is this state? This state is nothing but you pick some coin, right? Okay, so how many calls you will have? You will see what all coins I can pick. So it would be n minus coins of I. So this state would be n minus coins of I. For example, if n is 15 and you pick a 7 rupee coin, so you'll end up at 8, which is 15 minus 7, right? So f of n is nothing but it is minimum of all the states which you can reach from a given n by picking a certain coin, right? So it would be minimum of f of n minus coins of I, provided, okay, provided this value, and here you can say for all I, okay. So you have to try for all I, provided if n minus coins of I is greater than equal to 0, right? So you cannot pick a coin whose denomination is greater than the value of n. For example, you want to make 7 rupees, so you cannot pick a 10 or 20 rupee coin, right? So you just compute this value and you take the minimum for all possible values of I, right? So this is what you are going to do in a top-down DP approach. So let me quickly also discuss about the bottom-up case, okay? So let me just see how we can do this in a bottom-up manner, right? And then we will also talk about the complexity of the same problem. Okay, so let's see how we can implement same using a bottom-up DP. So for bottom-up DP, I'm going to take a relatively small example. Let's say the coins which are available, let's say 1, 3 and 5, and let's say I want to make a change for, let's say, 8 rupees, right? Okay. So there are multiple ways to make 8 rupees, but the shortest would be you pick these 2 coins, right? So let's say, okay, we have a DP array, and since the state is described by one variable, which is n, it would be a 1D DP. So let's see what is the answer for n equals to 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so in order to make a change for 0, I need 0 coins. In order to make 1 rupee, how many coins I would need? I can say, okay, from 1 I can go to 0 by picking a 1 rupee coin. So this would be minimum of this plus 1, so it is going to be 1. Okay, what about at 2? So if I want from a state 2, I can pick a 1 rupee coin to end up in a state of 1. So for 2 I will make a call on 1, and this is now computed as 1, so minimum is 1 plus 1, it is going to be 2. So you need 2 coins to make a change for 2 rupees, given these are the coins. For n equal to 3, right? So you have 2 options. You can pick 1 rupee coin, you can pick a 3 rupee coin. You cannot pick a 5 rupee coin because it does not satisfy this condition, right? So you can say, okay, from 3 I can go to 2, I can go to 1, sorry, I can go to 0, right? I cannot go to 1, right? So I can subtract 1, I can subtract 3 to end up at these sub-problems, and minimum of 0 and 2 is 0. So this answer is going to be 0 plus 1, which is 1. And you can see that actually it is an optimal answer. For n equals to 4, you can pick 1, you can pick 3. So if you pick 1, you end up here. If you pick 3, you end up here. So minimum of 1 and 1 is 1 plus 1, which is 2. So what it is saying, if you go to 3, you pick a 1 rupee coin, and to make 3, you pick a 3 rupee coin. So this is the denomination you choose, or you can first pick a 3 rupee coin, you end up at 1, and at 1 you pick 1 rupee coin to make 1. So this makes basically these 2 cases. So in both of these cases, you will need 2 coins. So you pick 3 followed by 1, or you pick 1 followed by 3. So to make 5, the best possible way would be to go to 0 by picking a 5 rupee coin, and you can definitely take the minimum between this and 5 minus 3, which is 2. So this is going to be 1. Similarly for 6, the best would be you go to 5, so it would be 2. For 7, you can go to 6, you can go to 7 minus 3, which is 4, and you can go to 7 minus 5, which is 2. Okay, so the best would be if you go to 7 minus 2 plus 1, which is 3, right? So in order to make 7, you need 2 coins, okay, and this would be 3. And for 8, you can say, okay, I can pick 1, I can go to 7, I can pick 3, I can go to 5, and I pick 5, I can go to 8 minus 5, which is 3. So here the answer is 1, and I can see the minimum is 1, so this is going to be 2. So in order to make a change for 8 rupees, you can see we need exactly 2 coins, which is 3 and 5, right? So this is what the bottom up DP is going to do, and let's talk a bit about time complexity of this. So you can see that you need to compute DP of n, and DP of n that we have already seen can be written as minimum of DP of n minus coins of I for all possible I, for all I, okay, provided this condition is also satisfied. So when you are going to do this loop, so if you have, let's say, t type of coins, you have t type of coins, so this dp of n of one particular state is going to take order of t time to compute, and you know how many states you need to compute. You need to compute n number of states, so it would be order of t into n. So the overall complexity both in the top and bottom up case would be t into n, where n is the amount and t is the type of coins you have, right? So I hope this particular solution is now clear to you, and this dp is same as this f, right? So do not think of it as a different thing, right? So these two are effectively same. So here I have written dp of n minus coins of I for all possible I. So in the next video we will talk about the implementation, and thanks a lot for watching this video. See you guys in the next part.
Hi everyone, so we are going to talk about the coin change problem, and we are going to see the implementation now. And we saw one example that if n is 15 and you have these coins, you want to count the number of ways, count the minimum coins that would be needed to make the change, right? So we also saw that if you have a large problem, you have a large denomination, we will reduce it to sub problems, right? From n we are going to make a call on n minus coins of 1. Basically we will say, okay, sub problem will compute how many coins are needed to make a denomination of 14, and then we can pick a 1 rupee coin to make it 15. Or we can say, okay, sub problem will have a look at how to make a 8 and how to make a 5, and we will pick one more coin of 7 rupees to make it 15. Or sub problem will see how to make 5 rupees, and we will pick a 10 rupee coin to make 15 rupees, right? So this is what we have done, and we have seen that dp of n is going to be, and let's say it takes x coins, y coins, and it takes z coins. So your answer is going to be minimum of x, y, z and whatever it is plus 1, because you need one more coin on the top of it, right? So we can write it as, it would be minimum for all I dp of n minus coins of I. So this is going, we are going to loop over it. So n minus coins of I. Whatever it is the minimum, we will add a 1 here to get the minimum number of coins, right? So we are going to see how we can implement this in a top-down manner first, and then we are going to see how we can implement the same in a bottom-up manner, right? So I would suggest you to also give it a try by yourself, and you would be able to do this one, right? So minimum coins is the problem. So let me start. Okay, so I'm just taking one example. Let's say n is 15 and coins have this denomination 1, 7 and 10, and I need to count the minimum coins needed. So we get the n, we get the coins array, and we should also get how many different type of coins are there. Let's say m type of coins are there, or let's say t type of coins are there, and n is the amount, right? So, and we should also get the dp array, right? So let me say, okay, dp of 100 and it is 0. And think about the base case, right? So clearly you can say if you have 0 rupees, you need 0 coins. So if n is 0, your answer is going to be 0. For all non-zero answers, you need to have a recursive case which computes how many coins would be needed for a given n, right? And so let us iterate over this coins array, right? So we can say, okay, answer is not known to us. Let's say answer is int max, and we are going to say, okay, for int I equals to 0, I less than t, I plus plus, and here I can say my answer is going to be minimum of whatever is my current answer, whatever I have computed so far, right? Now you have in the earlier problem you have to only take minimum of 3 elements. Now here you have to take minimum of lot of options, right? So you have, this array can have a large size also, so if you want to consider the minimum, right? So I'm just taking one variable called answer, which is infinity, and I say, okay, if infinity is minimum or this answer x is minimum, so I make it as x. Then I say if x is minimum or y is minimum, let's say y is minimum, then I make it as y. If z is minimum, then I make it as z, otherwise it remains as y. So it is just like taking minimum of n possible options, right? So answer is going to be minimum of answer. And what is my current answer, right? So the answer for my sub problem, it would be minimum coins. I will make a recursive call and my amount would be reduced. So it would be n minus coins of I. If I pick one coin whose value is coins of I, then my sub problem amount would be n minus coins of I, and I will give the coins array, I will give t, and I will also give the dp array. But this can be done only if n minus coins of I is greater than equal to 0, which means the current coin is less than equal to the value of n. For example, if you want to make 5 rupees, then you cannot pick a coin whose denomination is 10 rupees. So this constraint is going to ensure that you do not pick very large coins which are even bigger than n, right? Only in those cases you will compute the sub problem and you will update your answer as sub problem, right? Sub problem answer plus 1, right? So this is what you are going to do, or you can add a 1 here, right? So that's it. And finally dp of n is going to be equal to answer, and you can say okay, return dp of n. And here you will have a case to look up if a particular state is already computed. So if dp of n is not 0, which means we have already computed for this given state, I'm going to say return dp of n. That's it. And let us try to run this code. So number of types of coins is going to be size of coins array divided by size of int. So you do cout minimum coins, you pass in the value of n, you pass in coins, you pass in t, and the dp array. That's it. So C limits. So you can see the answer is 3. If you want to make 15 rupees, your answer is going to be 3, and that we have already seen how it is going to happen, right? So 15 is going to make a call on 14, 14 is going to make a call on 7, and this is going to make a call on 0. So 0 returns 0, 7 returns 1, 14 returns 2, and 15 will return 3, right? After comparing with this, 8 will also return 2, right? And 5 will return 5. So the minimum of 2, 2 and 5 is 2, so your answer is going to be 3. This is how we are going to solve this problem, right? So in the for loop, we have done nothing, but we have just made a call on all possible sub problems, right? So this is what we are doing, and we are taking a minimum at every step, right? And your answer to the current problem would be the answer to the sub problem plus 1, right? So this is how we have implemented the top down solution. In the next part, we will also see how we can implement the bottom up solution. Hi everyone, so for the minimum coins bottom up approach, we would adopt a very similar technique that we used in the minimum steps to one problem. So what we will do, as discussed in the concept video also, we will have to find the answer for every value of n, right? And for every value of n, we have multiple options. We can break down that n into multiple sub problems, right? So what we are going to do, we are going to form an array in this manner, and we are going to say, okay, what is the number of minimum coins that you would need to make a denomination as 1 or 2 or 3 or 4 or 5 or 6 or 7 or up to n, right? And starting from n equals to 0. So we also know that for n equals to 0, the answer is going to be 0. So this would form our base case. And for all other values, right, at n equals to 1, you know you have a coins array of 1, 7 and 15. You can pick a coin of 1, but you cannot pick these two. So you can just go to 1 minus 1, which is 0. So answer is going to be whatever is the minimum plus 1. 0 plus 1, 1. At n equal to 2, you can just go to here, because you can pick only this coin, right? So you will iterate over all possible coins, but you will pick those coins where the value is less than this. So it is going to be 1. From 2 you will end up at 1. So answer is going to be 1 plus 1, which is 2. Similarly 3 here, and similarly you have 4 here, but at n equal to 5 you will have 5. Here you will have 6. But n equal to 7, you can pick 2 coins. You can either pick 1 or you can pick 7. If you pick 7, you end up at, if you pick 1, you end up at 6. If you pick 7, you end up at 0. So clearly the answer of two sub problems is 0 and 6. Minimum is 0, so the answer is going to be 1, right? Similarly for 8, you can see the answer is going to be either you end up here or you end up here. In both cases it is 1. So the answer is going to be minimum of 1 and 1, which is 1 plus 1, it is going to be 2. Similarly so on. And at 15 you will have an option to end up at 14, and at 14 you will have an option to end up at 7. So the minimum is 1. So the answer for 14 is 2. And similarly at 15 you have two options. Either you end up at 14 or you end up at, sorry, this coin is 10, right? So you have three options. You can end up at 14, you can end up at 8, and you can end up at 5. So you can see these three states have already been computed. So for answer for 14 is 2, for answer for 8 is 2, and for 5 it is 5, right? So minimum is 2, 2 and 5. So minimum of these is 2, and you can say, okay, my answer is going to be 3. So you finally store a 3 here, right? This is what it is going to be, right? So the complexity, as we discussed, is going to be order of n. So you will need a loop to iterate over all of these, and for every state you need to make these many calls, right? In the worst case, so if there are t coins, you need to make t sub problems, right? So it is going to be order of n into t. Okay, let's see this bottom up approach now. And yeah, so what I can do, I can make a function min coins bottom up, and let me accept the same parameters here also. So this is n, and dp array, maybe we can create our own dp array here, and let's say everything is 0. So let's say answer is not known to us, it's going to be int max, or let's say answer is not needed, right? So we need to iterate over all states from 1 to capital N. So I take a for loop where n goes from 1, n is less than equal to n, n plus plus. So small n is a variable now, right? So capital N is the actual n, right? And small n is a variable that iterates over all the states. And at every state we have multiple options, right? So what we can do, we can initialize our current answer. So current answer is nothing but dp of I. We can say, okay, set it as int max, because we are going to find at the minimum, right? Okay, so initialize the current answer as int max, which is a large number, and then we will try to find out the minimum by iterating over all possible coins. So for int t equals to 0, t less than t, t plus plus. So if I pick the tth coin, or let's say if I pick the ith coin, right? So I can go to a sub problem where the sub problem answer would be nothing but dp of n minus coins of I. This is going to be the answer of sub problem, but only if n minus coins of I is greater than equal to 0. Okay, so I will compute the sub problem only if this condition is true, like we did in the top down case. Now we have the sub problem answer, and then we can update our current answer, right? So okay, we can say okay, so current answer is going to be stored in dp of I. So dp of I is going to be minimum of whatever is my current answer, that is dp of I, and the sub problem answer, which is sub problem plus 1. That's it. And finally, if you come out of this loop, you can say okay, return dp of capital N. That will give you the final answer, right? So see guys, what we have done here, let me just repeat if you are not sure. So okay, you have, suppose you are filling this position N, right? And let's say this position is, let's say 12. So from 12 you can make a call on 11, you can make a call on, let's say coins are 1, 7 and 10, right? So you can make a call on 11, you can make a call on, let's say 5, and you can make a call on 2 also, right? Let's say this is 2, this is dp of 2. So whatever is the answer here, right? So you say okay, for n equals to 12, I know the answer is going to be infinity in the beginning, but if I found a coin whose denomination is less than equal to n, right? So this also means coins I is smaller than n, right? Or less than equal to n, right? If I can pick a coin whose denomination is less than n, then I will find the subproblem answer. So whatever is the answer for this particular subproblem, okay, so this is, add one more to it and update your dp of I. So this is sorry, this would be your dp of n, right? So my mistake, this would be dp of n, right? This would be also dp of n, right? Because this time I'm using to iterate over the variables, right? So you will update your dp of n as minimum for all possible dp of n minus coins of I plus 1, right? So this is what we need to do, right? The same thing we are doing here. Okay, if this is minimum, take this. If this is minimum, take this. If this is minimum, take this, right? So whatever is the minimum, you just take it. So this would be dp of n, right? So yeah. Okay, so let's build the code and see. I was not declared. Yeah, this would be also dp of n, right? Okay, so build is successful. Let's run this one, and this way we will call min coins bottom up, and we won't pass the dp array now, right? N coins and t, only 3 variables. So min coins, so you can see the answer for 15 is still 3, and we have also discussed the space and time complexity of this code. So I hope you got the bottom up approach for the coins problem, and see you guys in the next part.
Hi everyone, so let's now talk about another interesting DP problem that is called Wine's problem. So in this problem you are given a array of wine bottles which basically denote the prices of wines, right, in the first year, right? So what is given is, this is an array of prices corresponding to the ith bottle, right? So this is P of I, which denotes the price of ith wine, right? So let's say this array is nothing but P and price of ith wine, right? So this is the initial price. So it is given that you can sell wines from extreme ends, right? So in 1 year you can sell one bottle. Okay, so which bottle you can sell, that would be either the extreme left, okay, so last bottle or the first bottle, right? So in this array, for example, in the first year you can either sell this bottle or you can sell this bottle, and it is also given the prices of wines increase, right, every year. They increase every year, and basically in the ith year, right, or let's say in the yth year, your price of the bottle pi would become pi into y. For example, in the first year, if these are the prices, then in the next year, the prices are going to get doubled. For example, let's say 2 will become 4, 3 will become 6, 5 will become 10, and 1 will become 2, and 4 will become 8. So these are the prices you will have in the second year, right? In the third year, the prices will become 3 times. In the fourth year, the prices will become 4 times. And in the final year, when you have to sell only one bottle, the prices will become 5 times, right? So it's not you have to sell exactly one bottle in 1 year. So the question is about, again, optimization. You need to find out what is the maximum profit you can make by selling all the bottles. So maximum profit you can make by selling all the bottles, and it is clear that if you have n number of bottles, it would take n years to sell all of them, right? So again, let's think how to solve this problem, right? So again, I would start with the contradictory or the wrong approach that some of you might think. So some of you might think that, okay, that prices are going to get increased. So let's first sell that bottle which is cheaper. So in case of 2 and 4, if you sell 2 first and if you sell 4 later, then price of 4 will increase more than the price of 2 and you will get more profit. So let's say what the greedy approach is going to give us, right? Okay, let's say we have a choice between 2 and 4, so we will sell second bottle in the first bottle in the first year, ending up in a profit of 2 into 1. Then we will have a choice between 3 and 4. So okay, we will say, okay, we will sell the third bottle first, so we will get 3 into 2, 6 rupees. So here I am multiplying the year number with the bottle price because the prices are going to get increase. So now we are left with these bottles. So between 5 and 4, we will sell 4 first because 4 is a smaller number. So it will give us 12 rupees plus 1 and 5, we will sell 1 first in the fourth year, plus we will finally sell 5 in the fifth year. So this becomes 25 plus 24, 29 and 12, 41, 47 and 2, 49. So this gives us 49 rupees. Okay. So another thing that we can do is that we will say, okay, let's think of something different, right? Maybe I do not want to sell these bottles in this order. Maybe some order, right? Some other ordering, right? Instead of using this ordering, I say, okay, I will use some other ordering, and now my price, it's going to look something like this. Okay. So yeah, between 2 and 4, again let's start with 2. We sell 2 in the first year. Then we will sell between 3 and 4. We can chase, okay, let's sell 4 in the second year. And between 3 and 1, okay, we are left with these bottles. So I will sell 1 in the third year. I will sell 3 in the fourth year. And I will sell 5 in the fifth year. So this will eventually give me, this is 25 plus 12, 37 plus 3, 40, 48, and this is 250. Right? So you can definitely see that we are able to get a better answer what we were getting from a greedy approach. So again, this greedy approach is going to fail. Right? So personally, if I would have given this question, I would start straightway from a DP approach, because this is something that is intuitive, right? So in greedy, it might be possible that if you sell this bottle or this bottle first, it also affects how the other bottles are going to be sold, right? So you have to think recursively what are the consequences of what would be the effect on the bottles which are inside this, right? So again, I would not suggest a greedy solution for this. You will have to start it using a recursive or a DP approach, right? Okay, now let's think about how we can formulate a recursive or a brute force or a DP solution in this case, right? So thing is we do not know which bottle to sell. So we have a confusion between this bottle and this bottle. So what will DP do? It will say, okay, try out both the choices, right? So let's say there is a function f and we give this array to this function. Okay, we have I, we have j, and we also have an array, right? So, but array is not a part of the state of DP. So what I can do, I need to sell the bottles from the ith index till the jth index. Tell me what is the maximum profit you can make by selling out these two bottles, right? So if I had to break down this, I would think, okay, the first option is that, okay, I will sell this bottle which will give me a profit of AI into, sorry, P of I into whatever is the year that is going on, right? Let's say the current year is Y, plus the remaining profit I will get from by selling these bottles, right? So this remaining profit can be achieved by making a call on a function in which I is I plus 1 and j is j. That's it, because this is now a sub problem, right? So DP knows, the recursion knows how to solve this sub problem. Or I could say I can sell the last bottle first into whatever is the year that is going on, plus the profit I can make by selling out bottles from I to j minus 1 in the remaining years, right? Okay, let me add one more variable here. Let me say, okay, we also know what is the current year, right? So when we will sell the remaining bottles, the year will start from y plus 1 and this is also y plus 1, right? Okay, so this is what is going to happen, right? And we are going to take a maximum, right? So the one which gives us maximum profit, not only looking at the current step, we are also looking at what happens afterwards, right? So this is what DP is going to do, right? So if you think about of a greedy solution, it looks at what is locally optimum, right? But if you think of DP, it sees the entire consequences, what is going to happen till the last, right? So it looks at your globally optimum solution, right? So it gives you the global optimum, right? Which gives you the DP approach, right? So again, once you draw these states, you will find out that there are many states which have same values of I and j, right? So let me say that, okay, you have array here 0, 1, 2 and 3. You can make a call on, you start with the state 0, 3, you can make a call on 0, 2, or you can make a call on 1, 3. From here you can make a call on 0, 1, or you can make a call on 1, 2. From here you can make a call on 1, 2, and you can make a call on 2, 3, right? So once you draw this diagram, and you will see that there are certain states which are getting overlapped. So this is one state, right? And clearly you can see this follows an optimal substructure. If you know the answer for this state and this state, you can compute the answer for this state, right? Because you need to, let's say this answer is x, this answer is y. So the answer for this state is nothing but maximum of x comma y. So it follows the optimal substructure property, plus you can see that these two states are overlapping states, right? So it has overlapping subproblems. So that is why this is going to be solved using a dynamic programming. So this recurrence relation you can definitely implement in a top-down manner and get your answer. And what would be your base case? What would be the smallest possible case? Okay, so if I becomes greater than j, right, that means no bottles are left in your array. You can say your answer is going to be 0. So just return a 0 if I is greater than j, which means no bottles are left, right? And in the next part, I'm going to explain you the bottom-up approach for solving the same problem. So thanks a lot. See you guys in the next part. Hi everyone. So now let's discuss the bottom-up approach to Wien's problem. And as we discussed in the last video, that each state in this is represented by two variables I and j, right? So this is I, this is j, and we have derived one recurrence that dp of ij, yeah, or you can say f of ij is going to be maximum of the two possible options you can have, right? So if you sell this first bottle, then you will have uh, this thing, right? So you will get profit as p of I into whatever is the year going on, plus you will make a call on the remaining part, let's say dp of I plus 1 to j, and it will also start from year plus 1, right? So when you call this, you make your year as year plus 1, right? And other option could be you sell this bottle first and you make a call on this part, how much profit you can make from the remaining part of the array. So you can say it is p of j into the year y plus dp of I comma j minus 1, and year is going to be year plus 1, right? So this year either can be a parameter in the function call, or you can compute this year from I and j only, right? So if you give I and j as a parameter, you can make out a formula which basically describes y as a in terms of I and j, because you have n, so it would be something of this kind, n minus I plus j, something of that thing, right? Because if you know that, okay, I had initially 5 bottles and I know these bottles are left, so I know these bottles have been sold, so how many years are left, right? So you can just subtract these two terms to get, okay, how many years have been passed till now. So you can express y as a function of I and j. That is something we will see in the implementation, right? So let's now focus on the bottom-up approach and how we are going to solve this, right? And we also saw in the uh, top-down approach that we will start from a large case and we will build towards the bottom. So let's say if you have only 3 bottles, 0, 1 and 2, so you have an array from 0 to 2, you can reduce in 0 to 1 and you can reduce in 1 to 2, and you can say, okay, this becomes 0 0, this becomes 1 1, this becomes 1 1, and this becomes 2 2. Yes, right. Yes. So this is now a base case, right? So in these cases, you have only one bottle left and you can figure out what is the price of one bottle in the final year. And if you try to go beyond this, your answer is going to be 0, because of the termination condition, your start will become greater than end, or I will become greater than j, right? So if you go beyond this, right? So, and we have seen that it is going to be each state is represented by 2 dimensions, and for the simplification, I am assuming there are only 3 bottles, and we will try to find out how we can compute the answer for this in a bottom up manner, right? Okay, so let me make a 2D array, because now each state is represented by 2 variables I and j. Okay, so I have this cell as 0 0, I have 0 comma 1, 0 comma 2, 1 comma 0, 1 comma 1, 1 comma 2, 2 comma 0, 2 comma 1, and 2 comma 2. Okay. So these would be the states that I would looking forward to compute, and our final answer should be here, right? Because we need to compute what this final profit would be. So we need to compute f of or dp of 0 comma 2. So if I sell all the bottles starting from the 0th index till the 2nd index, what would be the maximum profit? So this is the cell value that we are looking forward to compute, right? So as you can see that first of all we are going towards the base case. So we would be filling those values where I is greater than j, right? So in these cells particularly, you can see I is greater than j. So this answer is going to be 0, right? Okay, so let's make all of these cells as 0 where I is greater than j, and we are not going to call those states directly, right? Or another thing that we could have done is we could have started from the diagonal index, right? We could say, okay, we will start from this by filling this diagonal, right? Because if you look at this diagonal, it is the most easy diagonal to fill because you have only one bottle. You do not need to think what will happen after selling this bottle because this is the last bottle that is left, right? So this says 0, 0, which means in this particular array of 2, 3 and 5, you have reached a state where only this bottle is left and these two bottles have already been sold. So what would be the maximum profit you can make by selling this bottle? So can you tell me? So can you think what it would be? So clearly we know that only one bottle is left. It means we are in the third year. We have sold these two bottles in 2 years and we are right now in the third year. So this bottle is going to give me a maximum profit of 2 into 3, which is 6. So let me say this profit is 6. Okay. So what about 1, 1? 1, 1 means, okay, only this bottle is left. We have only this bottle is left and we sold this bottle and this bottle, and this is the only bottle which is now left in our array. And if we sell this bottle, what is the maximum profit that we are going to make? So clearly we can say we are in the third year because 2 bottles have been sold, and this bottle we would be able to sell at a price of 3 into 3, which is 9 rupees. Alright, let's talk about this entry also, right? Because you can see that these values are important, right? So you need to form these values because we are doing a bottom-up approach. So what about 2, 2, right? Which means only this bottle is left. In the first year we have sold this bottle, in the second year we have sold this bottle, and again this bottle is left, right? So 2, 2 means a state where only we have one bottle and this is this bottle. So we need to think only about this bottle. So this bottle is going to give us a maximum profit of 5 into 3, 15, because we are in the third year, right? Now we will solve for little complex states. We will solve for this state 0, 1, right? Because it's a bottom-up approach, we are going from a smaller state towards a bigger state. So 0, 1 means that we now have 2 bottles. So if I talk about 2, 3 and 5, we are in this state, which means we have already sold this bottle and we are talking about what is the maximum profit that we can make by selling 2 and 3. Okay, so again, what year it would be? We are in the second year because one bottle is already gone from the array that we sold in the first year. So in the second year, I have 2 options. I can sell 2 and I can see what profit I can make by selling 3, or I can say I will sell 3 first and I will see what profit I can make by selling 2, right? So if you now see clearly here, if you sell 2 first, so your profit will be 2 into 2, 4, plus the profit you can make by selling this. So this is the profit that comes from 1, 1. 1, 1 is this cell, so this is 9, right? So this profit is going to be 13. So one option could be 13. Another option could be you sell 3 first, so 3 into 2, 6, plus you sell the remaining, which is 0, 0. So from 0, 0, which means you are making a call here, you get a profit of 6. So this gives me a profit of 12 rupees. So clearly I can say that the maximum of these two, right? The maximum of these two would be 13. So I put a 13 here, right? So you can clearly see to compute 13, we made a call here and we also made a call here, right? And if the cell is I, j, we are making 2 calls. Okay, so this call is towards I, j minus 1, and this call is towards this is your I plus 1 and j, right? And clearly you can relate these two with these two, right? So in order to compute a particular cell, we are making 2 calls here, right? Now you can see you cannot compute this cell. You have to compute it diagonal by diagonal. So let's complete this diagonal, because in order to compute this state, you also need this state and this state. So this we have computed. We will now compute this particular state, which is 1, 2. Okay, so let's talk about how to compute 1 comma 2. So we have this is 0, 1 and 2, and we are in second year because we have left with two bottles, 1 comma 2, and we have already sold this bottle, second one, the first bottle, and we are left with these two bottles, right? So how much profit we can make by selling two bottles, that we have to see, right? So first option is, let's sell 3, so we will make a profit of 6, plus we will be left with this. So we need to get the answer for the state 2 comma 2. So 2 comma 2 is here, so this answer is 15. So 15 plus 6 is 21, right? And you can also see that if you sell this bottle in second year, it will give you 6, and then you have no other option, you have to sell this bottle in the third year, which will give you 5 into 3, 15 rupees. So this is 21. Another option is you sell 5 first, so you get 5 into 2, 10, plus you make a call on this 1 comma 1, which is this, and this gives you 9. So this gives you a profit of 19. So the maximum is 21, so I put a 21 here, right? Okay. Finally, we can compute this state. So this is what we need to compute, and we are in this state 0 comma 2. So we have all of these bottles. So again, we have two options. We can sell 2 by in the first year at a price of 2, plus we can get the remaining profit of 1 comma 2, which is 21. So this is going to be 23, or we can say we will sell 5 first, plus get the remaining profit, which is 13. So this is going to be 18 rupees, right? So maximum is 23. So this answer is going to be 23. And clearly you can see that we have made a 2 calls, 1 call here and 1 call here, right? So let me just remove this arrow. Okay, so this is 23, this is 21, and this is 9, and so on. And if you carefully look at this, right, so this actually looks like this top down tree, right, because this particular cell is dependent upon these two, and this is dependent upon here and here, this is dependent here and here. And you can also see that there are overlapping subproblems. For example, this problem is a overlapping subproblem, and similarly this particular cell has been used 2 times, one to compute this and one to compute this. So if you use DP, you can avoid a repeated computation of subproblems, and this is how you are going to build a bottom-up solution to Wien's problem. So I hope this concept is now clear to you, and we will see the implementation in the next part.
Hi everyone, so we will now discuss the solution for the Wien's problem, and we have also seen what is the recurrence. So given this array, and we want to find out if we sell Wien's from each corner, what is the maximum profit that we can make. And we also know that price of Wien's in the ith year becomes I times, right? So price is going to increase. So in the yth year, all the prices will be multiplied with the y. That is something known given in the problem. And we have also derived the recurrence that the maximum profit that we can make by selling all the bottles from I to j is going to be, either we can sell out just bottle first, so this would be your array of I into whatever is the price in the current year plus this subproblem. So this is profit of I plus 1 to j. Or you can say, okay, you will sell this array of j first into y plus profit of I comma j minus 1. So clearly in this problem, you can see in the state of DP, there are two variables involved. One is your start and one is your end, right? This problem will be a problem of 2DTP because there are two variables that are getting updated, and we will, while implementing, we will also take one more y that will make things easier for us, and for the next remaining part we will increment y by y plus 1, right? But still it will be a 2DTP problem because we can calculate the value of y by knowing the value of I and j, right? Because if you know the total number of bottles is n equals to 5 and you know 3 bottles are left, let's say I is here, j is here, and there are 3 bottles, right? Then you know that 2 years have been passed, right? Just to make things simple, I will add on one more variable to my code, that is y. And why we are going to use dp? Because if you say this is 0 to 4, right, then we are going to make a call on 0 to 3, and we are going to make a call on 1 to 4. From here you will make a call on 0 to 2, you will also make a call on 1 to 3. From here you will make a call on 1 to 3, and you will make a call on 2 to 4 also, right? What I'm doing is that in the state, right, in the function call, the state of I and j is changing, right? Because if you do I minus 1j, you get up these values of I and j, and if you do I plus 1 and j, you get up these values, right? Similarly, if you do I minus 1 and j, sorry, I and j minus 1 here, and if you do I plus 1 and j here, right? So you can see there can be multiple states which are forming overlapping subproblems. So these two are going to form overlapping subproblems, and that is the reason we are going to use dp here, right? Okay, so let's get down into the code and implement this one, right? Okay. So first thing is we need to know about the base case, and second is we should have a recursive case, right? So base case is very easy. Suppose you're selling bottles and you're selling bottles from I to j. So at every point you are going to shrink I and j, because I is going right and j is going left. So it might happen that in the worst case no bottles are left, right? So no bottles are left. That will happen if I overshoots j. Okay, so if I overshoots j, which means I becomes greater than j, your profit will be 0. This would form our base case. So I can say if I is greater than j, let me return 0. And in the recursive case, I have two options. One is to sell the first bottle, which is at the ith position, and the price of that bottle in the current year, so current year I am denoting by y, will be y plus the, okay, so let me make this function as profit, okay, plus the profit from the remaining bottles, that would be wines array I plus 1, j and 5 plus 1. Option 2 would be I can sell the jth bottle first into y plus profit from the remaining bottles, that would be I comma j minus 1, and y would be y plus 1. And finally, what I need to return? I need to return the maximum of these two, option 1 and option 2. That is my final profit, right? Okay, so let's try to run this code, and in the beginning the year is 1, so I can do cout profit of wines, I is 0, j is n minus 1, and the year is y, right? So let's build our code and run it. So I can say okay. So you can see the answer is coming out to be 50 for the case that we have already discussed in the video. And if you use a greedy strategy, that gives you an answer of 49, right? So we will not use greedy, we will use dp, that gives you the optimal answer, that is 50 rupees, right? So this is how easy the code is, but in this case we have just implemented the recursive solution. If you want to implement dp, then you need to make a dp array. Let's say we have an array of 100 cross 100 and it is initialized with 0, right? So here you will send the dp array, and here you will accept the dp array, okay, and here you will see if particular state is already computed, right? So return if I comma j, if dp of ij is known, right? So what we are doing, we are basically computing dp of ij. What is the optimal answer if you have bottles from index I to index j remaining in your array. So if it is already known, so if dp of ij is non-zero, so I will just return it dp of ij, right? So let me build this again. Okay, so we also need to pass the dp array. Right, so we need to pass the dp array in the function call here also, then build our code, right? So build is successful and let's run this now. So it's Vine's problem.exe. So you can see answer is again 50, and by doing this we have improved our time complexity to n square, right? Because you are filling out a grid, right? So what you are doing, you are basically starting from this index. So there is a grid like this, there is a matrix. So in the beginning you're making a call from 0 comma n minus 1, so which means you're at this cell and you're making certain calls. Let me just draw again. So you are at this particular cell 0 comma n minus 1, right? So you're at this cell, you're making a call here, you're making a call here, and from here you're making a call here, you're making a call here, and so on, right? And there would be cases, if you go beyond this point you will see that I becomes greater than j. For example, in this cell this is 1 comma 0, so I is greater than j, right? So I is 1, j is 0, so here the answer is going to be 0. Similarly the answer is going to be 0 for these kinds of cells. So effectively you will start by selling out the bottle at this index first, right? This will give you more clarity if you have seen the video for the bottom up approach, but in both approaches we are filling out the same matrix, right? So we are filling out the same matrix, and finally your answer 50 would be here, right? And it depends upon the answers which are coming from this cell and this cell, and that is further dependent upon answer from this cell and this cell, right? And so on, right? So I hope this implementation part is clear, and this is quite easy to implement the top down approach, and bottom up is going to be a bit trickier because you need to fill this array diagonally, right? You need diagonal filling in the bottom up approach. Okay. So that's all for this video, guys. Thanks a lot. See you guys in the next part. Hi everyone, so we would be now discussing this problem called maximum subarray sum, and the question is very clear from the name itself that you need to find the subarray which contains the maximum sum, or you need to get the maximum sum which can be formed using a subarray, right? So what is a subarray? So a subarray is nothing but a sequence of elements which is continuous. For example, if you have an array, right, then subarray is a continuous part of the array, right? It's a smaller array that lies completely inside this array, so this is a subarray, right? And remember, it is different from a subsequence. So when we talk about subsequence, your elements, it is not necessary the elements should be continuous, right? So this type of a selection will be called a subsequence, and this continuous part would be called a subarray, right? And all subarrays are also subsequences, right? So this is one difference that you should know before getting into this problem. So goal is you need to find out one part of the array. Let's say it starts from index I, let's say it end up at index j, and let's say this is the part which contains the maximum sum. Okay, so now if you carefully look at this, there can be multiple ways to solve this problem. The first approach that will come to your mind will be a brute force approach, right? In which you will select for all ij, you will find out the sum. Okay, you will just sum up your array from array I to array j, right? So ai plus 1 plus up to aj, and you will see, okay, for what values of ij this sum is maximized, right? So you can choose all ij in n square ways, and you can compute this sum in order n time. So the complexity of the brute force solution would become order of n cube. Okay, but you can do something better, right? So what better you can do, you can say, okay, instead of finding this sum every time, I can use something like a prefix sum. Okay, you can say, okay, if I want to find out, let's say I will make another array which is the cumulative sum of all elements of the array. For example, if the elements are 1 2 3 minus 2 5, then cumulative sum would be 1 3 6 1, and this would become 6, right? Now someone says, okay, I want to get the sum for this part of the array. So how you can find it? You can just find it in order one time. You can say, okay, if this index is I, this index is j, then in the cumulative sum array you will just subtract 6 minus 1, which is 5, right? So this sum 2 plus 3 is 5, and if you look at this array, right, so you can say, okay, give me the sum up to this point, which is C sum of j, and I will subtract this part, which is the sum before this ith point, so minus C sum of I minus 1. So this gives you the sum of elements from I to j. So this will only take order one time. So this is 6 minus 1, this is also 5. So this is one approach you can use, but again, in this approach you will have to find this sum for all pairs of ij, and sum you can find in order one time, but number of pairs would be still n square, right? So your complexity would be order of n square, right? So now let us look at something better, and this would involve your dp. So let's see the dp solution, right? And we would be able to solve this problem in order and time, right? So the goal in dp is to maintain a state, right? So given an array, we need to maintain what is the maximum sum that I can form up to a particular point, right? So in this problem, since the question is about maximum sum array, so what we can do, okay, we will say that, okay, suppose you are at this particular jth index, and you know what is the maximum sum you can form up to this point, right? So what is the maximum sum up to this point, right? Then what you can do, you can also form what is the maximum sum up to this point, right? So maybe let's say this sum is 10, and let's say this element is 5, so you might add this element here, right? So you can say, okay, the maximum sum, if we include this element, it will become 10 plus 5, it would be 15, and let's say this element is minus 2, right? So what you can do, you can say, okay, if I include this element, the maximum sum up to this point would become 13, right? And maybe you have some very large number, let's say minus 20, right? Then you can say, if I include this element, the maximum sum would become negative, right? So whenever our sum will become negative, we are not going to take that element, because it's large enough, it has already made a sum which is positive as negative, so we will ignore this element. But suppose this element would have been, let's say 7, right? Then your sum would increase, right? Then your sum would become 20, right? So what you will do, you will try to form what is the maximum sum that you can form up to the ith index or the jth index, and then you can say, okay, if this sum becomes negative, let's make it as 0, or if it is a positive number, right, we will keep it. Okay, so keep it, because a positive sum can be combined with some other positive number even though the element is negative, right? So even if this element is negative, we can say, okay, we will still add it to our sum, but we will also keep a track of what is the maximum so far, what is the maximum number we have formed so far, So the maximum up to this position will be 15, up to this position will be 15, but up to this position it will become 20, right? So you need to keep a track of two things. What is the maximum so far, and what is the maximum sum, what is the sum till the ith number if you include the ith number, right? Sum till the ith index, right? If you include the ith index, right? So it might mean that some elements are already skipped, right? And this does not mean that you are taking all elements up to I, right? So let us first see the implementation, then we will get into little more dry run of this program, right? So I'm just going to open Sublime and I have the array ready, and let me make this function int maximum sum, and here I get the array, I get the number of elements, and the goal is to return the maximum sum, right? Okay, so let me say, okay, I will make a DP array, and this time I'm just doing the bottom up DP, right? So let's say all elements are 0, and what I can do, I can iterate over all elements from 0 to n, right? Or I can say let's start from 1 to n minus 1, right? And let me say dp of 0 is going to be a of 0 if a of 0 is greater than 0, right? So it will be of 0, otherwise it will be 0, right? Okay, so what we did, we said in dp of 0 I will store the 0th element if that is positive, otherwise the answer is going to be 0, because it does not make sense to include the first negative element in our sum, right? Okay, so what I'm going to do, I'm going to say, okay, dp of I, okay, let me say what is the max so far, that is equal to dp of 0 in the beginning, right? So what I can do, I can say, okay, in dp of I will add the current element to the previous sum, right? So it would be dp of I minus 1 plus the current element, right? What is the current element? That is array of I, right? So if dp of I is positive, right, then it is good to go. But if this is negative, right, then I'm going to make this dp of I as 0, and I'm going to update max so far as maximum of whatever is my current answer and what is my previous maximum at every step, and finally I will return max so far, right? So see, what we are doing here is we are just checking what is the maximum sum you can form by including the current element, right? So given this array, right, so here what we are saying, that if at any point your sum becomes negative, right? So if sum becomes negative at any point, right, for example, you are just summing up this array, right, and you see, okay, after adding this element, this whole sum becomes negative. So you already have the maximum till this point. Let's say this is 20, and let's say this element is minus 80, right? This makes this entire sum as negative, right? And let's say you have some positive elements here, right? So if you do not discard this sum 20 plus minus 80, right, if you do not make it as 0, it will also reduce the positive effect of this array, right? So this is the whole idea, right? But let's say if this element would have been minus 8, then this would have become 12, and since it is a positive number and you can add more positive number to get a bigger positive, right? Okay, so this is what we are doing, right? So we are going to store what is the maximum sum that you can form at any index ending at I, right? Ending at the ith index, right? And this max so far just looks at what is the maximum number you ever formed during any at any ith index, right? So it is just like finding maximum of 10 best numbers, right? Okay, or let's say n best numbers, right? So this is what it is doing, right? So if you look at this example now, right, so let's make a DP array for this. Yeah. So in the beginning this would be 0 because it's negative, then the sum would be 2, here the sum would be 7, and here I'm going to write the maximum. So maximum is 0, maximum is 2, maximum is 7, and this is your DP. This is the value of max so far, right? Okay, so this minus 1, so when you add this to previous state it becomes 6, but the maximum remains 7. So when you add this to previous state this becomes 12, but and the maximum is also 12. So when you add 3 it becomes 15, and the maximum also becomes 15. When you add minus 2 this becomes 13, but the maximum remains 15. When you add 7 it becomes 20, but the maximum also becomes 20. So when you add minus 5 it becomes 15, but the maximum is 20. When you add 2, DP of I is 17 and the maximum is 20, right? So finally your maximum answer is this, right? So you will see this would be a increasing array, right? And this is what DP of I is, right? So DP of I just stores what is the maximum sum you can form at a index ending at I, right? Okay. So let us see what is the maximum sum for this array now. So it is nothing but you just take these elements, right? So this would give you maximum sum as 20, 7 minus 2, 5, 8, 14, 13 and 7, which is 20, right? So let's run our code to see if we have done this correctly. So see out maximum sum, and let me give array and n. Okay, so this should be ARR. So you can see the answer is coming out to be 20, and this is how we have solved this problem in just linear time, right? So it is taking only linear time, right? And in the next part I will discuss one more implementation that is space optimized for this problem, right? Hi everyone, so now we are going to look at an space efficient implementation of the maximum sum subarray problem, right? So space optimized code, right? So what we need to do to make this optimization is, if you analyze carefully, your answer for the current state just depends upon the answer for the previous state, which means you do not need to store the answers for all the states. You just need to store what is the previous maximum or what is the previous sum so far, right? So what we can do, we can just take one variable instead of taking entire array, and that will help us to reduce our space complexity to order 1. So this algorithm is also called Green's algorithm, right? But you can, it is something that you can make it on your own as well. So let's try to make a space optimized version of this code. So maximum sum space optimized, right? So you have the array, you have n, and what we are going to do, instead of taking a DP array, we are going to say, okay, what is the current sum so far, which is 0? What is the max so far? That is also 0. And what I can do, I can just iterate over all the elements of the array, and we will do a similar thing. So we added to our current sum the current element, so it will become current sum plus equals to array of I, and we will check if the current sum at any point becomes negative, we will make it as 0, because that won't really help us to make a larger sum by adding some positive elements, right? If you add some positive sum to a negative sum, it reduces the effect of the positive sum, so it's better to make it as 0. And if it is positive, you can compare. If it is larger than the maximum sum, then you can take the maximum of the current sum and the maximum so far. So that's it, and you can say okay, return current sum. So this will give you the maximum sub-array sum, and there is a special case which you would need to handle, right? So let me say, okay, let me run this code, maximum sum space optimized, right? So so let's build the code and run this, right? Maximum sub-array sum. So you can oh sorry, you should return the max so far. Small mistake here. Let me build again, and so you can see answer is 20, which means this is correct, right? So what we are doing here, we are doing exactly same, but instead of taking a DP array, we are just taking a single variable that stores what is the maximum sum that ends at an index I, right? So one special case, right? So special case that you might need to handle, right? So this you will handle yourself. So if array contains all negative elements, right, then your output by this code will be 0, but it might be possible you need to output the smallest negative element, right? In that case, this would be your answer. If all elements are negative, your sum would be 0, but it is possible that you might need to output the smallest negative element because you want at least one element in the subarray, right? So you can use a simple if condition to check inside a loop. If everything is negative, then just give me the smallest negative element, and that would be your answer, right? So I hope this DP part for the maximum sum subarray sum is clear, and I will see you guys in the next part now. Hi everyone, so we will discuss one more problem now, that is called ladders problem. And again, it's a very interesting problem, and in this question you're given that there is a ladder which contains n number of steps, and there is a person who is standing here and he wants to reach the topmost point. Okay, let's say, yeah, there is a guy here, he wants to reach the topmost point, which is, let's say, this point, right? And you want to find out how many ways are there to reach this hut, right? So what is given in the question, that there are n steps and that person can take maximum jump of k. Okay, maximum jump of k at each step. So k is again a number and it is given in the input, right? So input is given n and k, and you need to output the number of ways, right? How many ways are there to reach n, right? Nth step. For example, if I say n is 4, k is 3, it means you can take up to a maximum jump of 3, which means the person can take a jump of 1, it can take a jump of 2, and it can take a jump of 3 steps at every step. These are the possible options. So if is here, so he can go to 1, he can go to 2, and he can go to 3. So 1, 2, and 3. But he cannot go to 4, right? And at this step, he can again go to 2, he can go to 3, and he can go to 4, and so on, right? So you have to tell me what would be the answer, what would be the ways given n comma k, right? This you need to figure out what would be this recurrence. So once you have the recurrence, we can implement it using recursion, we can implement it using DP, and so on, right? Okay, so maybe you can spend 2 minutes to think about the solution, and now I'm going to discuss the solution once you have thought yourself, right? So the way I'm going to think this solution is in the form of uh, how I can reach this hut, right? So clearly, if I want to reach this point, right? Let's say I want to know how many ways are there to reach this particular point. Let's say this is the nth point, right? And suppose if I reach this point, I will say, okay, I can reach this point from this particular step by taking a jump of 1, or I can reach from this particular step by taking a jump of 2, or I can reach from this step by taking a jump of 3 or k. Okay, basically you have couple of ways to reach this final step up to n minus k, right? So there is one way in which I'm coming from the previous step. So if you know the number of ways to reach this point, you also know the number of ways to reach this particular point via this point, right? So if I say number of ways to reach this is f of n, then I can say the number of ways to reach this step would be f of n minus 1. Number of ways to reach this particular step would be f of n minus 2. Number of ways to reach this step would be f of n minus k. And we cannot count this particular way because there is no such way. So this, if you take a jump from this step, it will end up somewhere in one of these steps, and the ways would be already counted in this f of n minus 1, right? For if you take this jump, this would contribute to f of n minus 1, f of n minus 2, f of n minus k, but it will not contribute directly to f of n, right? So if I know the number of ways to reach these particular steps, right, then what can you say about f of n? How many ways you have to reach the nth step, right, in terms of these, right? So clearly it would be summation of all of these. It would be f of n minus 1 plus f of n minus 2 plus up to f of n minus k. The reason being, you have an option to reach this step, so you can come either from this or from this or from this. It's whenever you have the condition as or, we add a plus. Whenever we had and, we have multiply, right? So it is not possible that you are directly coming to this particular step from this step and this step. So it won't be and, it would be or, right? So you can come from only these last case steps, right? So if you're still confused or still you want a good understanding, maybe let's say this is Delhi, and maybe if you come from the South India, there are 5 flights which land at Delhi, right? Let's say if you come from China, there are 8 flights which land at Delhi. And maybe if you come from Europe, there are 10 flights which land at Delhi. So can you tell me what is the total number of ways to reach Delhi, right? So clearly total ways would be sum of these. If you can start from any country, right? If you can start from China, you can start from Europe, you can start from South India, and so on. Maybe from US you're going to China, but that does not matter, right? You just want to see how many ways are there from China to land in Delhi, right? And this would contribute to the ways in China, right? So let's not worry about this. In how many ways you can land at Delhi? So you will just do 8 plus 10 plus 12. So these are the ways, right? So it is 23 ways. Similarly, in our example, it is going to be these many ways, right? So we can say, okay, this is nothing but summation of f of n minus I, where I goes from 1 to k. That's it. And this is what your f of n is, or this is what your dp of n is. So you can simply write dp of n is going to be summation over all k summation of dp of n minus I. That's it. And now let's think about how we can implement this using top down dp. So let's talk about top down DP first, then we will talk about bottom up DP and one optimization, right? So in top down DP, let's see this example. If n is 4, k is 3, what is the number of ways, right? So clearly you can take one step at every time. This forms one way. You can take 1 2 one step, another way, 2 1 1 another step, 1 2 1 1 2 another step, 2 2 another step, 3 1 another way, and 1 3 another way, right? These are the possible ways. So if you see, these are 3 plus 3 6 and 1 7 ways. So in top down DP, suppose you are at n equals to 4, right? So you will make 3 calls because you need to make k number of calls. So you will make a call at 3 2 1. They will make a call at 2 1 and 0, and 2 will make a call at 1 and 0. Okay, so at 1 you can go to only 0, right? So this is how the recursion tree is going to look like. And what I'm going to do, I'm going to store the sub problem answers also, right? So let's say when I hit this base case 0, right? From 2, I'm not going to make a call on -1 because that is a state that is not reachable, right? So we will just stop if n minus I becomes negative, right? So from 0 to 1, right? So if you hit 0, it means you are at ground. So how many ways are there to stand on the ground? So clearly there is one way. 1 is going to return 1. From 2 you make a call on 0, it also returns 1. So the answer for 2 would be sum of these two, 1 plus 1, which is 2. 2 is going to return a 2, and in your DP table you will store, okay, the answer for 0 is 1, answer for 1 is 1, answer for 2 is 2. Okay. And similarly at 3 you make a call on 1, so this returns a 1. You make a call on 0, this returns 1. So the answer for 3 is going to be 2 plus 1 plus 1, which is 4. Okay, and from here you make a call on 2, and that is already computed. So this answer is 2, and you make a call on 1, so it returns a 1. So for n equals to 4, the answer is going to be 4 plus 2 plus 1, right? So that is going to be again 7 ways, right? So remember, I'm not computing overlapping sub problems here, right? I'm just directly assuming that you're using a top-down DP, and this is how the tree for the top-down DP is going to look like. If you use recursion, then it is going to be evaluated further, right? We have just cut short our tree to save time, and this is what is top-down approach. Okay, so okay, you can clearly say, okay, the answer for n equals to 4 is going to be 7. So this is your DP array in case of top-down approach, right? So what is important to understand, that each sub-problem answer is optimal. So if I talk about how many ways are there to reach n equals to 3, so it will say there are 4 ways, and if you want to see those ways, so it says there are 2 ways in which you will first reach 2 and then you will jump to 3. So those ways are 1 1 and 2 1, right? So in both of these ways you are able to reach 2 and then you take a jump of 1 to reach 3. And there is one way in which you are coming directly from 1, right? So here you are jumping from 1 to 3. So there is one such way. So you will end up at 1 first, then you will take a jump of 2. So there is one such way. And there is also one such way in which you are going directly from 0 to 3. So that way is nothing but you directly take a jump of 3. So for n equals to 3 and k equals to 3, you have 4 possible ways, right? Similarly, for n equals to 2, you have 2 ways, which is 1 1 and 2. For n equals to 1, you have only one way, which is you take a jump of 1, right? And for n equals to 4, you are building your answer by using, okay, how many ways are there to reach this point, this point, this point, and so on, right? So you are basing your answer based upon previous case states, right? So here what you need to store in dp is the answer for the previous k states. That is important to build the answer for the current state, right? So this is what the top down dp is going to do, and let us write the code and discuss about the time complexity of the solution, right? Okay, so let me just say ladders question.cpp, and let me just type in given n and k, I input n and k, and then let's say there is a function called int ladders top down. It accepts n, k and the dp array. And what you can do, you can have a base case if n is 0, right? Which means I am at the ground step, so there is one way to stand on the ground, because if you do not return this one, everything is going to be 0, right? And in the recursive case, from a given state you will make a call on n minus I. So what I am going to do, for let's say my base is going to be 0, and for int I equals to 1, I less than equal to k, I plus plus, I will add something to my answer. So base plus equals to ladders top down of n minus I, k is k and dp is dp. But this call I will make only if and only if n minus I is greater than equal to 0, because I do not want to make a call on a negative state, right? And you can return these, right? So this is your recursive implementation, and as of now we have not used the dp array. So you can also store your answer in dp of n. This is equal to ways, and here you can look up if dp of n is not 0, you just return dp of n. Okay, this is your top down dp, and let's make a dp array, dp of let's say 100, and this is 0, and let's make a call on cout ladders top down. You give n, you give k, you give dp handle, and you return 0. Okay, so let's build this code now. Build is done. Input is 4 and 3, so you can see there are 7 ways for this problem. You give some other output, let's say 5 and 3, you can see there are 13 ways, right? Now in the next part I will talk about the bottom-up approach, and in this case we learned that if you want to form a solution for a given problem, you just need to think how to get the current problem from the given subproblems. You are not worried how these problems are getting solved, because recursion is going to do the work for you, and this is how exactly this problem is getting solved, right? And let's also talk about the time complexity. So effectively you have an array of size n, and for every state, for every n, right, for every n in n, you are computing the sum of previous k elements. Maybe this is k elements, and then you're saying, okay, whatever is the sum, just add them up. So that sum is going to take order of k time, and this whole is going to be of the order O of n into k. So this is going to be the time complexity of this code. And if I talk about the space complexity, you can see the maximum depth is order of n, so space complexity is going to be order of n, right, in this case. Okay. So I hope this is clear, and now we will talk about bottom-up approach in the next video. Hi everyone, so let's discuss about the bottom-up approach to the ladders problem. And as of now we have seen that the state of dp is like this. Dp of n is nothing but summation over all I going from 1 to k dp of I minus k. So if you make a array like this, and the whole idea here is to fill up this array in a bottom up manner, and let's say this is 0 1 2 3 4 5 6 7 8 9 10 and so on, right? So what you will do, you will first say, okay, dp of 0 is 1 because this is the base case, and for dp of 1 you need to iterate on the previous key elements. So you have only one element here, let's say k is 3, so you will iterate over just one element, so this becomes sum is 1, so which means there is only one way to reach 1, and for n equals to 2 you again iterate over last k states, so sum them up, so you get 2, and here you iterate on last 3, and it is 2 plus 1 plus 1, which is 4, and at k equal to 4, n equals to 4, you iterate on previous 3 states, right, and sum them up, right? So this answer is 7. At here you iterate on last 3, which is 7 plus 4 11 plus 2 13, and at 6 you iterate on again last 3, which is this, and you can say, okay, the sum is 24, right? So this is how you are going to build this, right? So in order to fill n cells, you need to iterate over on last k, right? So the complexity is again going to be n into k, and implementation is pretty easy, so let's quickly implement this, and then we will see one optimization that you can do to reduce the complexity from n into k into O of n plus k, right? Or this is O of n since we are assuming k would be less than 1, right? So we will do this but later on, right, after this bottom up dp implementation, right? So let's make one function int ladders bottom up, and we get n, we get k, we make a dp array, and let's say everything is 0. Then we can say, okay, dp of 0 is 1 because this is a base case, and for all others going from I equals to 1, I less than equals to n, and I'm going to say, okay, what is my current answer, right? So current answer is dp of I, and that is going to be sum of previous k states, right? So for int j equals to 1, j less than equal to k, j plus plus, and here you can see that I'm using I for n and j for I, right? So here we would basically do dp of I plus equals to dp of I minus j, right? So this is, you from the ith state you're looking at k state up to k states backward, and j is the variable that denotes how much is the jump you are taking, right? So this you will do only if and only if I minus j is greater than equal to 0. So you will not make any call on the negative states, and that's it. And finally you will return dp of n. Okay. So maybe if you want to see the bottom up dp table, you can print it and verify that it is same as what we are building, right? For int I equals to 0, I less than equals to n, I plus plus, and see out dp of I, maybe. And here instead of calling this, I can just see out bottom up ways would be ladders of bottom up, you give n and k, and that's it. So let's say n is 6, k is 3, and maybe we are stuck. Oh, this should be j plus plus, right? This should be j plus. So let's build this again and this. 6 and 3. So you can see this is the bottom of DP table, and it's same as what we have built: 1 1 2 4 7 13 24, 1 1 2 4 7 13 24, and bottom base is 24 for n equals to 6. So this is perfect. And now in the next part we will talk about an optimization which will reduce the complexity from n into k into a linear complexity, right? Maybe you should also try yourself, and then we will discuss. Hi everyone, so now we will look at another optimized implementation of ladders problem, and this is basically inspired from the bottom up approach by carefully observing one pattern, right? So you know that in order to compute any state of dp, let's say you want to compute dp of 6, you basically are going to sum up the last k elements, right? And when you're going to compute dp of 7, you're going to sum up these last k elements, right? So now the idea is that when you are computing dp of 6, the last three elements are 4, 7 and 13, right? This is your dp of I or dp of n, right? So these are the last k elements that you needed to make this as 24. So you just sum all of them up and you get to this answer as 24, right? But when you are computing the next state, let's say dp of n plus 1, okay, what do you need? You effectively need all of these elements plus this element and minus this element, right? So if you carefully analyze, this makes the next window, right? So you're basically doing a sliding window kind of a thing, in which first you needed the sum of this window, and in the next step this window moves one step ahead, in which you add this particular element and you subtract this particular element, and this gives you the answer for the next state. This sum gives you the answer for the next state. For example, if you do think 24 plus 13 plus 7, so that will give you dp of 7, right? So that is going to be 24 and 7 is 31. This is going to be 44, right? So another way to see dp of n or dp of n plus 1, you can say this is nothing but, okay, so let me just tell you again. So you need to have this window, okay? So this window is nothing but, if you talk about this sum is stored at dp of n. So you need this sliding window. You need to subtract this particular element. So this element is dp of n plus 1 minus k minus 1, right? So if you are at this particular step, this element is dp of n, this element is dp of n minus 1, this is dp of n minus 2, and this is dp of n minus 3, dp of n minus 3. This is nothing but dp of n minus k. Let me say this is nothing but the dp of n minus k. dp of n plus 1 is, right? So what you need to do, you need to have this window, you need to subtract this element, and you also need to add this particular element, right? So let me just draw again. So plus we will do dp of n. This becomes 2 times dp of n minus dp of n minus k. This is another recurrence, right, that we have just derived from the same recurrence. But the good thing about this recurrence is it does not require a loop. Loop is not required to do the sum. You can do this sum in O1 time, right? So that will help us to reduce the complexity from On to Ok. So O of nk to O of n. This is what we are trying to do. And if you're not clear what we are doing, so let me just explain what we just did now. And you can also formulate this as dp of n by putting n equal to n minus 1, you can say it is 2 times dp of n minus 1 minus dp of n minus k minus 1. Okay. So you can also write this recurrence in this form. And what we are saying is, suppose you have these three numbers, right? Let's say these three numbers are 4, 7 and 13, right? 4, 7 and 13, and maybe somehow you computed this value. Let's say this value is known to you, and this is nothing but sum of these three. This is 24, and let's say this position is n. You want to compute this position, right? So one way is you just sum up last three values, and another way is you can say, okay, I will add 24 to this box to make a window like this, and I will subtract this box to get this particular window, right? So add this element, subtract this element, right? So okay, so let us first write what is this pink window, what is the answer of this pink window. So if you sum up all of these elements, so this answer is here, so this is dp of n, so this answer is dp of n minus 1. Okay, so given this position is n, you want to subtract this particular element. So what is this element? It is dp of n minus k minus 1, and you want to add this element. So what is this element? It is again dp of n minus 1. So clearly your dp of n can be written as 2 times of dp of n minus 1 minus dp of n minus k. And we can also verify this recurrence is correct. Now suppose we have again n equals to whatever it is, n, and let's say k equals to 3. So which means we need to sum up the last k elements, right? So for the first part, for the first k elements, we cannot use this formula because n minus k would become negative. So we will make this term as 0. We will use 2 times of dp of n minus 1. So okay, so for n equals to 0, the answer is 1. For n equals to 1, again the answer is 1 because the cumulative sum is 1, right? So these two will be our base case. And let us compute dp of 2 now, right? So dp of 2 is nothing but sum of these two, and considering this as 0 for the first k elements, right? You can see the answer is nothing but 2 times of dp of n minus 1. So this is 1, so 2 times of this is 2. And what about 3, right? So one way is you add up all these elements, this gives you 4, or you just take 2 times of dp of n minus 1 and take this as 0 because this is less than this is, right? So this becomes 4, right? And from this position onwards you can apply this formula, and now you know the value of dp of n minus k, right? Okay, so what would be the answer at this position? So if we just take the sum, it would be 4 plus 2 plus 1, which is 7, or if you do 4 into 2 minus 1, basically subtract this particular element, so this is also 7. What would be the answer at this position? You do 7 into 2 minus 1, so it would be 13. What would be the answer at this position? You do 13 into 2 minus this particular 2. This would be 24. And you can see you're getting the same array as you got up in the bottom up approach. So these two arrays are exactly similar, but this is saving time, right? This is the optimized approach, right? So I hope you are getting what to do now, and let us quickly implement this in a bottom up dp approach. So I can say, okay, int ladder optimized, you have n, you have k, and you have a dp array. Okay, so dp of 0 equals to dp of 1 equals to 1, and for int I equals to 2, I less than equals to k, I plus plus, and you can say okay, dp of I is nothing but 2 times of dp of I minus 1. And for the remaining part, you can say for int I equals to k plus 1, I less than equals to n, I plus plus, dp of I equals to 2 times of dp of I minus 1 minus dp of what, n minus k minus 1, right? So this is k minus 1 here, right? So dp of n minus k minus, I minus k minus 1, that's it. And if you want to just print and see if you are getting the correct array, for int I equals to 0, I less than n, I plus plus, you just print out your dp array like we did in the earlier case, and you return dp of n. That's it. And instead of calling this function now, bottom up is optimized, and this is going to be ladders underscore optimized. Let me see 6 and 3. So you can see answer for 6 is 24, and your array is also correct, right? So which means our logic is working fine. So I just divided this into 2 parts, but you can do it using a single for loop by putting the if condition. If I is less than equal to k, then you have to take this term as 0. That's the only change that you will make, right? So I hope this recurrence and this technique of optimizing a dp recurrence is clear to you, and this might not be possible to use it in all problems, but yeah, in some problems, especially where you have cumulative sum kind of a thing or a sliding window kind of a thing, you can use this approach to optimize your solution, right? So thanks a lot. I will see you guys in the next part.
Hi everyone. So in this lecture we will be discussing a problem called as rod cutting problem. So what you're given a rod of a particular length. For example, n is 8 here, and you're also given the prices of different pieces of the rod. Okay, so you can divide this rod into multiple pieces of different lengths. Maybe you cut a piece of length 1 here, then you cut a piece of length 4 here, then you cut a piece of length 3 here, and so on. Okay, so you can divide this rod into multiple pieces, and price of each piece is given to you. Okay, so if you make a piece of length, let's say 3, if this piece has a length 3, okay, then its price would be 8 units. Okay, so that is what is given to you. Okay, so for n equal to 1 till n equal to n, that is the largest piece, that is, if you do not make any cut in the rod, then the price of this rod would be 20 units. Okay, so if you sell this rod directly, you will be able to sell it for 20 rupees. But what you can do, you can divide this rod into multiple pieces. Let us say you make 8 pieces of unit length. So if you just divide it into 8 pieces of unit length, then you can see each piece will be sold for 1 rupee, and the profit that you will earn would be nothing but 8 into 1, that is 8 rupees. So obviously this is not maximum. If you just sell the entire rod directly, 1 into 8, so in that case, sorry, 1 into 20, that would be 20 rupees, right? So if you just make one piece, or there can be multiple ways. Okay, you can make 2 pieces of length 4, you can say okay, 4 9, so price of that piece is 9 rupees, so it would be 9 into 2, 18 rupees. Again, it's better to sell the entire rod. And maybe you can do something like this: you make one piece of length 6, and you make one piece of length 2, then 6 plus 2 is 8, so one piece of length 6 and one piece of length 2, then you can see this price is nothing but 5 plus 17, this is 22. Okay, so in this particular case, this is the highest price. You can try it yourself. So our goal is to maximize the total profit. Okay, so we need to maximize the total profit. Similarly, in this particular example, you can see in example 2, all the prices are same except for unit price. So if you just make a cut of length 1 and you make 8 such cuts, in that case you will get a profit of 8 into 3, that is 24. Okay, so in the input you would be given a price array, and price array denotes the length of each cut of the rod from 1 to n. That's what is given to you. So let's see how we can actually maximize the total profit. So the idea is very simple. We do not know which is the best cut. Okay, so we will start with a brute force approach, and we will see if we can optimize it using dynamic programming or not, right? So in the brute force approach, what you can do, you can say, okay, let me just give an index here. Okay, so index is 0, 1, 2, 3, 4, 5, 6, 7. For every value of I can make a cut. Okay, for if the value of I is 0, I can make a cut of length 1. If the value of I is 1, I can make a cut of length 2. So if I say, okay, if I pick the ith piece, so if I make the cut at the ith location, so that length would be nothing but I plus 1. Okay, so if I say, okay, make a cut at make a first cut of length 3, then you can see the value of I is actually 2, right? Because length array is indexed from 1 and the price array is indexed from 0. So how much price I will get for this particular piece? So that would be nothing but it would be price of I, and this gives me a first piece cut of length I plus 1. Okay, and what would be the length of the remaining rod? So we do not know how to break the remaining rod optimally, but we can make a recursive function that knows how to compute the problem for the solution for the remaining sub problem. So we will make a recursive call on this sub problem. So sub problem will be, this is f of let's say total length is n. Okay, and you have already taken I plus 1 units out of it, so it would be n minus what is the cut length. Okay, so here cut is nothing but I plus 1. So this is what you will get if you make the first cut at the ith location. Okay, or there can be multiple options. Okay, so there can be multiple options, like you make a first cut of length 1, or if you make a first cut of length 2, or if you make a first cut of length 3, or doing so you can also make a cut of length n, right? So that means there is only one piece in the rod, you are not cutting it. So 1, 2, 3 and up to n. So for each of these cuts you will get to know the optimal answer for the entire length of the rod. Okay, so this would be price of 0 plus f of n minus 1, it would be price of 1 plus f of n minus 2, and so on, right? And this would be nothing but price of n minus 1, that is the entire rod, plus remaining length is 0, so that would be 0. So what you need to do, out of all the cases you need to pick the case that maximize your profit. So you need to take maximum of all these particular cases. So that would be nothing, that would be your f of n. So that would be your maximum price of selling the rod, right? So I hope you got an idea how we can code a recursive solution. So it would be nothing but it would be maximum of, for all values of I from 0 to n minus 1, we need to figure this value out, right? So that is what we need to do. So we will build a recursive relation using this formula, and we will have a base case. If the rod length is 0, we will also return 0. Okay, so if n is 0, then we can say return 0. So let us dive into the coding part and see how we can first build the recursive solution, and then we will build the DP based solution, right? So what I'm going to do, I'm going to type the base case first. So I'm getting the prices array and I'm getting n, that is the length of the rod. Okay,
and that is also equal to size of the prices array. So here we can say if n is less than equal to 0, in that case you return 0. Otherwise we need to find out the answer, right? So in the recursive case, okay, let us say our answer is int min. Because we want to find the maximum value, we can initialize our answer with minus infinity. Okay, so what we are going to do, suppose we have a length of rod of length 4, right? So we can say, okay, take one piece out and make a call on 3 pieces, or take 2 pieces out, or take a piece of length 2 out and make a call on length 2, or take a piece of 3 length out and make a call on length 1, or take this entire piece out and make a call on length 0. So this would hit the base case, right? And similarly here, right? So what we are going to do, we are going to out of all the sub problems that we have created, we are going to compare which gives us the maximum answer, right? So how we are going to do it, let's see. We are going to say, okay, for int I equals to 0, I less than n, I plus plus, right? So the cut length would be nothing but I plus 1. Okay, so if you carefully say here, when I say I equals to 0, that means we are making a cut of length 1. I equals to 1, we are making a cut of length 2. I equals to, we are making a cut of length 3, and so on, right? So this is what we are going to do here. So we can say our current answer would be nothing but price of the current cut that we had made, that is prices of I, plus the remaining problem answer. Okay, so that would be max profit of the remaining rod, that is n minus. That's it. And we need to update our global answer, so that would be maximum of answer and the current answer. That's it. And from here we can say, okay, let's return the answer that we have got so far, right? So let us first test our code, and I'm just going to call this function max profit. Okay, and you can see I'm getting an answer 22 for the current test case, which is true. So we make a cut of length 6 and we make a cut of length 2. 17 plus 5 is 22 for a given value of n, that is 8. So if I make this length as 3, then I should get the answer as 24. So let's run the code, and you can see it's working fine. Now let us discuss if we can optimize this solution using dynamic programming or not. So let us consider the case when n is 4. So from 4 you are making a call on 3, 2, 1, 0. From 3 you are making a call on 2, 1, 0. From 2 you are making a call on 1, 0, right? And so on. So if you carefully look at the tree, right? If you carefully look at the tree structure, you can clearly see there are a lot of overlapping sub problems that we are computing again and again using recursion. So one way is you can use top-down DP. You just add memoization to this code and it will work fine. Another way is we can actually compute these values in a bottom-up manner. Okay, so for that what we can do, we can make a DP array and we can start filling this array. Okay, and what would be the state of this? Okay, so you can see it's a linear DP problem and the state is the length of the rod. Okay, so DP of length will store the maximum profit by cutting a rod of length, right, of rod len, right? So DP of 0, what would be DP of 0? So DP of 0 would be 0, right? What would be DP of 1? So if you have just one piece, that would be same as the prices of 1, prices of 0, right? So that you can hear. Similarly DP of 2. So DP of 2, how you will compute? So you can see from 2 you can actually go to two different sub problems, DP of 1 and DP of 0. So since these are already computed, you will not expand DP of 1 any further, right? Similarly from DP of 3 you can go to DP of 2 and DP of 1 and DP of 0. So since these are already computed, you will not be computing them again, right? So this is how DP is going to help us. And what you need to do, at every step you need to take the maximum of the cases that you can form from that particular value, right, from that particular state. Okay, so from dp of n we will again have different states, n minus 1, n minus 2, and so on. And if I talk about the complexity, you can see for each state we need to iterate over different options, right? So that is going to take order n time in the worst case, and we have n such states. Okay, so the overall complexity should be order of n square. Okay, so I hope you're getting it, but if you're not getting it, things will be more clear once we start writing the code. So let's see how we can compute it. So first of all, I'm going to make a dp array, dp of length n plus 1, and let us say dp of 0 is going to be 0, right? And what we can do now is we are going to do in a bottom up manner. So for the smallest possible length would be 1, the length should be maximum n, length plus plus. Okay, we are saying okay, we are going to compute dp of 1, right? Dp of 1 for a length of rod 1, right? So for a rod of length 1, what options we have? We just have one option, that we can go to 0, right? So let's see how we are going to handle that case. So for int I equals to 0, I less than len, I plus plus. Now again, we are talking about this particular loop, right? So what we can do, we can make a cut. We can make a cut of length I plus 1, and we can say okay, our current answer would be nothing but it would be prices of I plus dp of what? Dp of len minus cut. Now you can see what I'm doing here is, let's say your length is 3, right? So what I'm doing is, I say okay, you can make a, I will go from 0 to less than n. So the values of I will be, we are filling dp of 2, dp of 3. Okay. So I'm saying okay, I will go from 0 to 2. I goes from 0, 1 and 2. So what would be the length of the cut? So cut would be nothing but I plus 1, 1, 2 and 3. Okay, so that would mean from 3 we are making a call on 3 minus 1 2, 3 minus 2 1, and 3 minus 3 0. We are making a calls here, right? So dp of len minus cut. Okay, if you take one unit here, 2 unit here, and 3 unit here, so for that piece we have already added the price. So something similar we are doing, right? We say okay, make a cut of this length and add the optimal answer for this remaining sub problem while computing dp of len, right? And this length will be always smaller than or equal to len, right? So yeah, that's what we do. And we say okay, for every state of the dp we are going to store an answer. So that answer is initialized with int min, and we can say answer will be nothing but max of current answer and answer, right? So note the step, this should be done inside the for loop here. And finally, once we are out of this loop, we have computed the answer for dp of len, right? So how do we update it? We say dp of len equals to answer. And finally, once we are out of the loop, we say return dp of, let's build the code. It should be max profit dp. So let me run the code. So again, you can see the answer is 24, and if I make it as 1, the answer should be 22. So you can see both recursive and bottom-up DP solutions give us the same answer, and I hope you should be able to understand it, right? Hi everyone, so now we are going to discuss another common problem. It's called as longest common subsequence, or LCS in short. So you're given two strings, string 1 and string 2. You need to find out the longest common subsequence of these two strings. So let us see what is a subsequence. So subsequence, you know, it's a subset of a string. Okay, so for example, if I talk about this string, you have lot of subsequences. One could be AC, one could be ABD, and so on. We need to find out a subsequence that is common in both of them. For example, A is common, so one answer could be A. But we also know AB is also common, right? So another answer could be AB, and another could be BD also. BD is common, or another could be ABD. So out of all the subsequences that are common, the longest one is ABD and ABD, because it is present in string 1, it is also present in string 2. So the longest common subsequence would be ABD in this particular case. We need to first find out the length. Okay, so length of this subsequence is 3, and later on we will see how we can print this subsequence. So these are the two things we will discuss in this particular video, and we will start with the brute force approach, right? So let us discuss how we can solve this problem in a brute force manner. So what you can do, you start keeping 2 pointers to the start of every string. Okay, so let's say this pointer is I and this pointer is J, right? And what you can do, if the values at these indexes match, that means we can include this character in the common subsequence. So we say, okay, we will take A and we will try to solve the remaining sub problems from both the strings. Okay, so I will move here, I goes I plus 1 and J will come here. Now again, this is the case, right? So we will say, okay, B and B match, so you also consider B in your answer, and you move I one step ahead, and you also move J one step ahead, so J comes here. Now C and E don't match, so what do you do? So you don't, that means either C could be a part of the subsequence or E could be a part of the subsequence, because you may have a E here, maybe, then E could be a part of subsequence, or both cannot be a part of subsequence, right? So we have something like 3 options, right? So what you will do in this case, you will say, okay, if I have a sub problem in which I have CD and another sub problem in which I have EDG, so this is I pointer, this is J pointer, so you why not try out both the options? Okay, so what you do, you move I one step ahead, you say, okay, reduce this problem to this problem. So you say, okay, whatever is your function, you take I to I plus 1 and you do not move J, so J remains here, potentially because instead of D you could have a E here, right? Or you could have a E after C, right? So we will see that later on, right? Or what you can do, you can say, okay, E won't be a part of the subsequence. What we can do, we can just move the J pointer, we will not move the I pointer. So another option would be you keep I at the same place. So this is option 1, this is option 2, right? So what I've said is, if you have this problem CD and EDG, you will try to solve 2 sub problems. One is D and EDG, and another problem is CD and DG, right? So at one time you are removing E, at one time you are removing C. And now you may ask about the case when we are ignoring both of them. So that case will be automatically generated from this point. So from this point, if you make a call, one time you will ignore D, so you end up with a null string and you will get EDG here. And another time what you will do, you will say, okay, let's ignore E and let's make a call on this part. Okay, so you will have D and DG, right? So from D and DG, what you will get, you will have I here, you will have J here, and you will say, okay, add D to my answer and make a call on the remaining string. So in the remaining sub problem, you will have G followed with null. So if one of this remaining string is null, right, then you can never have something that is you can never have something that is common, right? So you just return a 0 length string. Okay, so this is how, by making recursive calls, we can actually end up at a case where one of the string is completely we have completely iterated over one string and we reach end of a particular string, right? So in that case there won't be any common subsequence and we will hit a base case, right? So I try to give you an intuitive idea here, but what we will do, we will try to write it in a more better manner. Let us say f is a function that takes 2 strings s1 and s2 and it takes the pointers I and j, they're initialized with 0. So what we do, if we reach end of a string, if I equals to s1 dot length or j equals to s2 dot length, so in that case we should return 0, right?
So as of now, we are just computing the length, right? Otherwise, what you need to do, you need to check if s1 of I is equal to s2 of j, right? If this is the case, right, then your answer would be 1 plus the remaining sub problem. So in the remaining sub problem, you will have I plus 1 and j plus 1. But if they don't match otherwise, right, so otherwise you will say, okay, it would be max of the two cases that we have generated. Option 1, that is f of I plus 1 and j, and another option would be I comma j plus 1, right? So let us try to write it in the form of a code, and things will be more clear. So let's start writing some code, right? So let me say LCS. So I have string 1 s1, that is abcd, and I have string s2, that is abedg. What is it? Yeah, it is. So what I do, I make a function, let's say int lcs. I get string s1, I get string s2, I get I get j, and we have a base case. If I equals to s1 dot length or j equals to s2 dot length, that means one of the string is finished, we won't find anything common, so we return 0. In the recursive case, it is easy. So if the current character matches, okay, so if the current character matches, so you add 1 to your answer and you make a call on the remaining sub problem. So that would be lcs of s1 s2 I plus 1 and j plus 1. Otherwise, if the s1 and s2 don't match, right, if the current indices don't match, then you include one of them, right, in one option. So in option 1, you say, okay, the answer would be lcs of s1 s2 I plus 1 and j, and option 2 would be nothing but lcs of s1 s2 I comma j plus 1, and whatever gives you the maximum, whatever branch gives you the maximum, you return that particular option, right? So what we are trying to do here is, we say, okay, if a and a match, okay, we say, okay, my answer is 1 plus the remaining string. What is that? So remaining string is bcd and s2 is bedg, right? So here also 1 and 1 match, so you say, okay, 1 plus 1, the answer is 2 plus the remaining string cd and edg, right? Here c and d don't match, so what do? You actually make two calls. So max of one call is like you say, okay, d and edg, and another call is cd and dg, right? And here also, what do? They don't match, right? D and D don't match, so you again make two calls. One is null string and followed by edg. So this branch is going to return 0. That is clearly not the maximum one. And in one case, you say, okay, we exclude e here, right? That will be d and dg, and this will again make two calls. So here d and d match, right? So d and d actually match, it will make one call, so it would be 1 plus the remaining, so remaining is 0. So what do? You get a 1 from here, right? And what about this? So from here you make a call on d and dg, and another call on cd and g, right? So you can see you're actually creating overlapping sub problems. So that means this can be optimized using dynamic programming. Similarly, for this problem, it would be d would be common, 1 plus 0, so you would be return 1 here, right? So from this branch you would be getting 1 and 1, and maximum is 1, so answer would be 1 plus 1 plus 1, that is 3, right? So this is how you're going to get an answer 3 in this particular case. So let us see out LCS. String 1 is s1, string 2 is s2, I is 0, and j is also 0, right? And return 0. That's finished. So let me run the program LCS, and you can see the answer is actually 3. Okay.
So let's see how we can add top-down memoization in this code. So you can see in this case there are two variables that are changing. Okay, so what we will do, we will make a 2D DP array, DP of ij, and that array actually denotes what is the length of the substring if you pick the characters starting from index I till the last of string in S1, and if you pick characters from index j till the last of string in S2. Okay, so that the maximum length of LCS of these two strings will be stored in DP of ij. Okay, so you are saying S1 may we are picking from I to n minus 1, and S2 we are picking from j to length of S2. Let's say it's n1, it's n2 minus. We are picking what is the maximum of LCS of these two strings that is being stored here, right? So yeah, so what we are going to do, we are going to first find out the length of string S1 and S2. So let's say int n1 equals to S1 dot length and int n2 equals to S2 dot length, right? So what we can do is we can say let's create a DP vector, right? So I'm going to create a 2D DP vector. So it would be a vector of the type int. Let's call it as DP. And now I want to initialize this with a value -1, right? So we are not setting a value 0 because that could be a valid answer. So what we are saying is we will initialize n1 number of rows in this DP vector, and each row would be a vector, right? So here you give the number of elements, number of rows, that is n1, and each row is a vector of integers, and each row contains n2 number of cells, and each of them is initialized with the value -1. Okay, so we create a vector of the size n1 cross n2, each initialized with -1, right? So this is a DP vector. So in the recursive function we are going to pass this DP vector. So we are going to say, okay, vector of vector int and of DP, we are passing it by reference, and in all the calls we should add this vector like this, like this. And now when you are computing a particular state, right, so here you are computing a state DP of ij. So what do you say? Before returning you store the state here, so DP of ij equals to this, and similarly you are computing a state here, so DP of ij equals to this. And one thing that we need to check to avoid recomputing same states again and again, so check if a state is already computed, right? So what we do, if DP of I comma j is not equal to -1, you can say, okay, return DP of ij. So that means this state is already computed, right? So hash include vector, sorry, this should not be a DP here, right? So we are just taking a max here, right? And the code is finished, right? So let us try to run this code now, and you can see we are still getting the same answer, right? So one thing we can actually do is we can also try to print the vector, right? So for int I equals to 0, I less than n1, I plus plus. For int j equals to 0, j less than n2, j plus plus. We can say cout dp of ij and cout endl, right? So here you will see some of the states, all of the states that are visited during recursion, and our final answer would be stored at dp of 0 0, right? So dp of 0 0 will actually give us the final answer, that should be 3, because we want the answer from 0 to n1 -1, and right, so 0 0 would mean we are considering the first string from I equals to 0 till n1 -1, and we are considering the second string from j equal to 0 till n2 -1. So that means we should have a 3 here. And similarly, if the string is like something like this, ABCD and ABEGD. So for this sub problem, if we have A and A match, right? So we just the 1 plus remaining answer. So for this particular problem, this is I equal to 1, J equal to 1. So this is 1 comma 1. So this answer should be 2, right? So we should have BD, that is a common string. So this answer should be 2. Similarly, you will have some values minus 1, 1 and so on, right? So let's see what we get in this particular vector here, right? So yes, you can see. So this is the vector that we are expecting, right? So minus 1 means these states are never visited, either because of the base case, or we never ended up at such values of I and j, right? So if you just want to see uh, which states are visited by base case, you can put this condition here. So it will set those values to 0 also, right? uh, yeah, so this is something we can't do here because we have made a smaller vector, right? So I equals to s1 dot length, so this index is not present in our vector. So for that you have to do something like n1 plus 1 or n2 plus 1, then you can see the states, right? And here also you have to put n1 or n2, right? So in this, now you can run the code, right? So now you can see the states that are visited by base case, but that doesn't matter much, right? Because base case is a order 1 operation, no need to memorize anything in the base case, right? So you can see this matrix and this matrix is same, right? So we do not actually need to do this thing. So maybe you can just remove this, right? So I just wanted to show you what states are visited by the recursive calls, and we are not computing overlapping states again and again, right? Because of this top down DP optimization that we added. So in the next video, we will discuss a bottom up approach and how to print LCS.
Okay, so we'll start with matrix chain multiplication today. Matrix chain multiplication. We also name it as MCM. So we all are aware of matrix multiplication. So first let's see what is matrix multiplication. Let's assume that I have two matrices A and B, and A has the dimensionality of R1 cross C1 and B has the dimensionality of R2 cross C2. Then the main constraint to multiply these two matrices is that R1, or basically C1, should be equal to C2 or R2, sorry, and there's no other condition. So like the number of columns in A should be equal to the number of rows in B. This is the basis of matrix multiplication. Now let's see what's the cost of matrix multiplication. MM stands for matrix multiplication. So let's see what's the cost of matrix multiplication. Let's assume that each multiplication operation is O of 1. Then to get the answer for one particular element in the final output matrix, let's assume that this has dimensionality R1 cross C1 and it has dimensionality C1 cross C2. Then the dimensionality of this matrix is R1 cross C2. And now let's compute the cost to take out each element in this matrix. So the cost to take out this element is the multiplication of this element with this second element, with the second element over here, third element over here with the third element in this matrix. So basically, if this is R1, this is C1, and this is C1 and this is C2, then we can very easily see that we are performing C1 multiplications
to get this corresponding element. Like it is a summation of some C1 multiplications. So the cost to take out one particular element is C1. Now the total cost of taking out all the elements in R1 cross C2 matrix is actually equal to R1 cross C2 cross C1, or writing it in a more beautiful manner, it will be R1 cross C1 cross C2. So basically we are just removing this one C1 out of here, and this becomes R1 cross C1 cross C2. This is the cost of multiplying two matrices which are the dimensionality of R1 C1 and C1 C2. So now what is matrix chain multiplication? Matrix chain multiplication is something like a multiplication of multiple matrices which are given like this. Let's assume that A to G are some matrices which are given to us. We need to perform matrix chain multiplication to get some final output matrix. Let's assume the final output matrix is Z. Now, what happens is that if A has the dimensionality of R1 cross C1, B has the dimensionality of R2 cross C2, and so on, we are very sure that C1 will be equal to R2, and similarly R3 will be equal to C2, and this process will go on. So this is because then only matrix multiplication would actually make sense. Else there is no sense of it. So we are given that the number of rows in the preceding matrix, the number of columns in the preceding matrix is equal to the number of the number of rows in the succeeding matrix. Yeah. So as simple as that. Therefore C1 is equal to R2, and this process goes on. So like how many different dimensions would be required to state all the matrices over here? Like if these are n matrices, then I'd require the row of each one of them, the number of rows in each one of them, like row in A plus and row in B and row in C and so on. And for the last one, I'll be requiring the row as well as the column. So basically, if I'm given n matrices, then n plus 1 dimensions would be enough for me at any point of time. So n plus 1 different dimensions are actually there, because this is because C1 is equal to R2 and C2 is equal to R3. So we don't need to keep separate values for both of them, right? So now we need to obtain a particular matrix Z after multiplying these. But the point is that if the order in which we multiply matrices matters, then the cost to compute Z would be different. That's the point we have to realize. Cost to compute Z may vary according to the order in which we multiply. What is the meaning of the order in which we multiply? It's very simple. Like it may be that first we multiply A with B and then multiply this whole cluster with C to get some combination of ABC matrices, but it may also happen that we first multiply B and C and then multiply A, and so as to get some combination out of these three. So now let's think that will it actually create a difference? Yes, it will create. Let's see it through an example. Like for example, let's assume that I have 5 matrices which are which have dimensions like 4 cross 2, 2 cross 3, 3 cross 1, 1 cross 3. Okay, let's assume that we have 4 matrices which have these dimensions. So basically my If I have 4 matrices, then I need n plus 1, which is 5 dimensions, which will be 4, 2, 3, 1, 3. Yeah. So, like I'll state them to be A, B, C and D matrices. Now let's see how the cost varies when we multiply them in a different order. Let's assume I multiply A and B first, and then I multiply the result with C, and then I multiply the entire result with D. This could be one way. What can be the other way? Anything. Like we can do A into B into C would be formed first, then A will be multiplied and then D. These are two different ways of getting the same output. So like let's see the cost. The cost here would be, first of all, for multiplying A cross B, the cost would be 4 into 2 into 3. Then the cost to multiply AB into C would be 4 into 3 into 1. And then the cost of multiplying ABC all together with D will be 4 into 1 into 3. Yeah. So this would sum up to 824 plus 12 plus 12 again, which is 48. Yeah. So let's see, like if we change the order, then what happens? A cross B cross C cross D. So first of all, we are performing B cross C. So B cross C cost us 2 into 3 into 1. Okay. And now the next one, which is A cross B cross C, would cost us 4 into 2 into 1. This is because the dimensionality of A here is 4 cross 2 and the dimensionality of B cross C in entirety is 2 cross 1. That's why. Now let's add some other value, the last one. When I multiply this entire ABC with D, then my dimensions would be 4 into 1 into 3. This gives me out 6 plus 8 plus 12, which is 26. Yeah, so we can very easily see that obviously 26 is lesser than 48, and we are able to recognize the fact that the order in which we multiply the matrices may change the cost of operations, the cost to compute the final matrix. So since the cost may change, so we need some optimal way to multiply these matrices so that the final resultant matrix, the cost of computation of the final resultant matrix is the minimum possible. Like that's what desired in every case. Like we need to minimize the cost of operations. That's why we perform competitive programming. Like we need to write some code that does the same thing which in minimum number of steps, right? So that's the whole purpose we have to realize over here. Now we need to do this using some method, and this method can be a very easy DP solution. So let's think of the solution. There are many variations of this particular problem, like the matrix chain multiplication problem that exist, which we'll be discussing in further videos. So like you need to realize the importance of this and the importance of figuring out how to solve DP questions. And these are some basic DP questions which should be known to you earlier so that you are able to solve the questions which come to you later on in a very smooth manner. So let's start with the solution for this. The solution is quite simple, but the fact you have to realize is that we'll form a matrix which is of the dimension n cross n, where n is the number of matrices we have. So like we'll jump onto the case of 4 2 3 1 3, and we have 4 matrices over here, so I'll make it as a 4 cross 4 matrix. Let's number them as well, 1 2 3 4 and 1 2 3 4. I'm using one based indexing. Now let's think of it like this, that a range, like what does a row comma column represent over here? In this matrix, let's assume that the row comma column represents some substructure of matrices in this given concept. Like for example, if I write them as A1, A2, A3, A4, then R cross C, R into C basically gives me the minimum steps to multiply matrices from AR to AC. So basically, if I were given 2 comma 4, then 2 comma 4, the 2 comma 4th element of this matrix actually gives me the minimum cost, or basically this is the minimum cost, not the steps. So the minimum cost to multiply A2, A3, A4, which may be A2, A3 and then multiplying it with A4, or getting A3 into A4 first and then multiplying it with A2. Any of the ways. So here we have to realize that in this matrix, which is, I'll name it as a DP matrix, DPRC, where R is obviously less than equal to C, gives me the number of ways, or the minimum, the minimum cost to multiply the matrices that are present from the Rth position to the Cth position. As simple as that. So, like first of all, let's go on to the diagonal elements. It's very easy to realize that if we need to form some sort of a DP, then we need to find the answers for shorter ranges. Like we know that R cross C now represents C minus R plus 1 matrices. Very simple. So, and this is some sort of a sub array of matrices. So we are supposed to calculate the answer for smaller subarrays, and which would help us to calculate the answer for bigger subarrays. So moving on to the diagonal over here, we can very easily see that the diagonal elements have the same distance between their R and C values, like 1 1 the difference is 0, 2 2 the difference is 0, 3 3 the difference is 0, 4 4 the difference is 0. This is because both R and C get updated when we move into the diagonal. So actually the difference remains the same. Similarly, on this diagonal, the difference stays out to be 1. So we'll be calculating for 2 matrices. Similarly, here the distance stays out to be 3 and the distance here is 4. Yeah. So how will we compute the answer for this is the question. First of all, let's assume like the base case is the diagonal case, right? So the diagonal case where I is equal to J or R is equal to C, what's the solution in that case? Like what's the cost of a matrix staying at its position? It's obviously 0. It's very easy to realize that this is 0 because if I'm not multiplying a matrix and it stays there like A1, so it's actually the answer. So I didn't have any cost to get this particular matrix, right? But if I were to have A1, A2, 2 matrices, then surely I need to have some output of these matrices which is multiplied to get the answer, and therefore the cost is implied, right? So now getting on to 1 2, what's the answer for this? 1 2 can have just one possible answer. Like it's very simple that if you are given A cross B, two matrices AB, then there's just one way to multiply these two matrices, right? So, but we'll still go the DP way here. Like what we'll do is that we'll always select a pivot point to find out the answer. Now, let's realize what a pivot point in this case is. This is how the basic DP here functions in this matrix chain multiplication problem. So we'll realize what's the pivot point. Okay, so let's see what's the pivot point. Now, we know that if we are computing the answer for, let's say, any x comma yth position, then we need to find out the minimal answer between some sort of answers, like all the possible answers, right? So actually, for taking out the answer for the x comma yth position, I'd actually need to multiply two matrices of a smaller size, right? That's the point you have to realize, that to find out the answer for a bigger subarray of matrices, you need to find out two matrices which are to be multiplied beforehand, right? Because every time you multiply, like let's assume that we need to find out the answer for ABC, then it's actually either this or this. So basically these are two smaller sub-matrices, smaller subarrays of matrices which are being multiplied. This is range 1 to 2 and this is range 3 to 3. Similarly, this is range 1 to 1 and this is range 2 to 3. So this is what pivot point is. Like if the pivot point is 1, then the matrix to the left is multiplied with the matrix to the right. We cannot change the order of the matrices over here. So that's the fact you have to realize and proceed thereafter. Like now, if the pivot point is B, then I need to multiply all the matrices on the left first, then all the matrices on the right first, and then multiply them after that. Like x comma yth position is actually asking for the last step which is to be performed, and we need to optimize the answer over that last step. So for example, like I'll have some k which is running, this is the pivot point which is running from x to y minus 1, and what happens over here is that I first multiply the x comma kth matrix, then the k plus 1th comma yth matrix, and then multiply these two matrices. This is the fact you have to realize over here. Like I need to find out the answer, best answer amongst all these cases, where k runs from x to y minus 1. So basically, to take out the answer, I'd write a small recurrence which you can say dp of xy is actually equal to, first of all I'll write min. Now in min I'll be writing dp of xk plus dp of k plus 1y for all k belonging to x2 y minus 1. This is the recurrence it should be using, but there's one thing remaining over here, which is obviously I'll take out the cost for these two to be computed, but there would be some cost that would be incurred in multiplying these two matrices as well. So I need to add something extra as well over here. What's that? That's very simply the dimensionalities of x, the matrices from x to k. Like, what's the dimensionality of the matrix running from x to k? Like, the dimensionality would be very simply, if I stated dimensionality is given in some array AR, then it will be array of x into array of k plus 1 into array of y plus 1. This would be my dimensionality, right? This is because we can very easily see, like, if two matrices are multiplied AB, then the cost is like if the matrices are R1 cross C1 and this is C1 cross C2, then it's actually x over here, k plus 1 over here, like the number of rows in k plus 1, and this is the number of columns in y plus 1. Also, basically the number of columns in y, which should be on the position y plus 1, right? So that's why this would be the entire recurrence here. It's very easy to realize this recurrence, and now once you know this, we can very easily compute the answer. So let's jump into the example problem, the example sample test case, and find out the solution for that particular case. So like we are finding out the solution for 42313 only. We'll try to fill this matrix, DP matrix. Now, can you guys just think of the answer of DP12? We'll use this recurrence only. So now the k here goes from 1 to 1 only. So the minimum value actually is dp11 plus dp22 plus this value, which is array 1 is 4 into array 2, which is 2 into array 3, which is 3. So it is 4 into 2 into 3, which gives me the cost of 24. So I'm writing 24 very easily over here. Now, let's jump on to find out the solution for DP23. You can pause the video and try finding out its solution on yourself. We'll just be using this recurrence for finding out the answer of all the ranges in this case. So let's find out the answer now for DP23. The answer for DP23 would be minimum amongst, like there's just one case over here, DP, the k here goes from 2 to 2 only, x to y minus 1. So it becomes dp 2 to 2 plus dp33. Both of these values are actually 0. So it's 0 plus something which is to be multiplied over here. Now what is that? Array of x is actually array of 2. Array of 2 is 2. Array of 3 is 3, and array of 4 which you require is 1. So here we know that the answer is 6. So we can very easily write the answer for the range 2 to 3, which is 6. Now we'll be writing the answer for dp 34. You can compute it very easily. It will be dp 33 plus dp 44. K here goes from 3 to 3 only. And now you need to add something beyond this. What's that? It's the array of 3, which is 3. Next, it's array of 4, which is 1. And next, it's array of 4 plus 1, which is 5. So it gives me out 9. Yeah. So it was very simple to calculate the answer for these cases in which there was just one element. Now let's try finding out the answer for the cases beyond that, which is dp13. In dp13, our k goes from 1 to 2. Yeah. So like for k equal to 1, let's find out the answer. Like for k equal to 1, the recurrence would be dp of 1, 1 plus dp of 2, 3 plus array of 1 into array of 2 into array of 4. And for k equal to 2, it would be something like dp of 1 to 2, then dp of 3 to 3 plus array of 1 into array of 3 into array of 4. So what does this give me out? Like in this case, dp11 is 0, dp23 is dp23 for k is equal to 1, dp23 is 6, 0 plus 6 plus the next value is 1, 2, 4. Like array 1 is actually 4, array 2 is 2, and array 4 is 1. So it gives me out 6 plus 8, which is 14. So 14 is one possibility which comes out at k is equal to 1. I need to check out this other possibility as well. dp12 is 24. Since dp12 is 24, it will land up something greater than 24 only, so I can skip this part. I can just think that 14 is the best answer. So something positive is to be added after 24, right? So we don't need to consider over there. Like the computer would obviously compute it if you write some code for it, but logically we can see right now that we don't need to compute it further. So we are done with dp13. Now let's jump on to finding out the answer for dp2 to 4. dp2 to 4. So now you can very easily guess that the k goes from 2 to 3. So I'll need to find out the answer for 2 as well as 3. So k is equal to 2 gives me dp 2 to 2 plus dp3. The case is 2 to 4 actually, not 2 to 3. So that's why case k goes from 2 to 3, yeah, right. So the dp 3 to 4 plus, it's very simple to evaluate now, array 2 into array of 3 into array of 5, right? So what's this value? This value is very simply dp22 is 0, dp34, dp34 gives me 9, and array 2, array 3 and array 5 are to be multiplied later on. So array 2 into array 3 into array 5 gives me array 2, array 3 and array 5, 2, 3, 3, which is 9 into 2, 18, 18 plus 9 is 27. This is the answer given to me by the first case. Now let's think of k is equal to 3. It goes from, it is something like dp23 plus dp44 plus array 2 into array 4 into array 5. Fine. Now what's the answer for this? The answer would be dp23. dp23 is 2, 3 would be 6, cool. Now dp44 is obviously 0, 2, 4, 5, 2, 4 and 5. So it gives me 2 plus 2 into 1 into 3, which is 6. 6 plus 6 is 12. Obviously this is the better answer, so I'll write 12 over here. Yeah, so now we are on to the final case of evaluating dp1 to 4. You should realize the fact that the answer for this entire problem should lie on dp1 to n. This is because that's what the answer for the entire range of matrices would be, right? Because if we are computing the answer for the range r comma c in dprc, then we want the answer for the range 1 to n, and that's what is stored in dp1n. So that's the case. Now we can very easily realize that for the case 1 to 4, our k would jump from 1 to 3. So we'll be having 3 cases, and we need to find out the minimum answer amongst those 3 cases. So that would be very easy. Let's find it out. First case, k is equal to, we are finding out the answer for the range 1 to 4, and first of all the k is 1, then we'll evaluate for k equal to 2, and then we'll evaluate for k equal to 3. So for k is equal to 1, we'll be reliant on dp11 and plus dp24 plus array of 1 into array of 2 into array of 5. 1 to 5 would be 4, 2 and 3, which is 4 into 2 into 3 is 24. So 24 will be added in 0 plus dp24 is 12. So 12 plus 24 gives me out 36. Okay, let's exploit other possibilities as well. Now this would be dp12 plus dp3 to 4 plus array 1 into array 3 into array 5. 1, 3, 5 are subsequently 4, 3 and 3. So 4, 3 and 3. This itself is 36. So I can very easily assure myself that it won't give me better answer, so I'll simply jump on to k equal to 3. Now k equal to 3 would be dp13 plus dp44 plus array of 1 into array of 4 into array of 5. Okay, so what's the answer for array 1 into 1 into 4 into 5? Like array 1 is 4 into 1 into 3. 4 into 1 into 3, it gives me out something 12. Now This is 1 to 3. 1 to 3 for 1 to 3, one best answer is 14. 4 to 4 is 0 plus 12. This gives me out 26. So amongst 36, 30 something greater than 36 and 26, which is the minimum, 26. So that's why we have our answer for this problem, which is 26. So the time complexity over here is O of n cube. This is because we are on a matrix computing n square elements, order n square elements, and to compute each element we require order n time. So it is roughly O of n cube, and the space complexity is very evidently O of n square. So this is how we'll solve matrix chain multiplication. The later details will be provided in the code. Thank you.
So today we'll be coding matrix chain multiplication. So in matrix chain multiplication, I'll be making a DP array which will actually be storing it from for all ranges, right? Storing the best possible answer, and then I'll also be having an n which is equal to a dot size minus 1, because whatever the size of A is, the number of matrices is actually 1, means the A dot size minus 1, right? So this n is basically the number of matrices. Now I'll be going on from here. You need to realize this fact that I'll set the dp to 0 initially. You need to realize this fact that for I is equal to 1 to n, only I'll be going for the row would be 0 and the column would be I, let's suppose. This basically reflects the column, the cell from which I'm starting. It's a 2-dimension thing, so the cell in the first row from which I'm starting, and I'll be moving diagonally from there. So while c is less than n, I'll be making r++ and c++ simultaneously. Now in here I'll be doing the processing part. I don't need to go from 0 0 to all the diagonal elements, because obviously their cost is 0. Like the cost for having just one matrix not being multiplied is 0, right? So now I'll be selecting the pivot point. So for int pivot is equal to r+1 and pivot is less than c pivot ++, I'll be having a value which will be initialized to int max, and I'll try to suppress that value by seeing the values on different pivot points, right? And okay, the pivot can actually start from R. Basically pivot reflects the last element of the last matrix of the first subpart of the first part which you are selecting. So the value is equals to minimum of value comma the value, the dp of r to pivot plus dp of pivot +1 to c, and in that I'll be adding the cost of multiplying these two. Like these two will be containing the minimum values for them, but I need to add some cost for multiplying these both of them as well. So it will basically the number of rows in the first one, which is a of r, and the number of columns a of the first part. So that would be a of pivot +1, which will be equal to the number of rows of this part, which is a of pivot +1, and into the number of columns of this part, which will be a of c+1. You need to get it that it is not present on c, it's present on the c+1th position, because that's how it makes sense, right? because if a matrix is present on the ith position, then its row is present on the ith position and its column is present on the I plus 1th index, right? That's the entire thing. Yeah, and now we'll be assigning it to dprc is equal to value, right? And I'll be at the end returning dp of 0 to n minus 1. So let's test it with custom input. Oh sorry, let's test it first of all. Oh, sorry, I have that bad habit of writing LL. So yeah, int would be sufficient. And is there some other issue? We'll test it. Yeah, so I submitted now. So I got the correct answer over here. So that was the matrix chain multiplication part. It's obviously very simple to code, and matrix chain multiplication basically comes in as a sub part of many questions or as a necessity for many other questions. So that's the main thing. It's a very basic problem in DP. So yeah, it can help you solve many other big problems. So thank you so much, guys. That was matrix chain multiplication from my side. Thank you so much for watching.
Hi friends, in this tutorial we are going to discuss an interesting problem from HackerBlocks. The name of the problem is cell meiosis. So let us first go through the problem statement and try to understand what the problem says. So it is given that there is a scientist and he is interested in building up some cells, and this scientist initially has a container which contains only one cell, right? So the scientist wants to make n cells from a single cell. So input is a one cell, and finally we want to make n cells from this single cell. And how the multiplication can be done is, the scientist has three operations. The first operation is he can double the number of cells. Suppose he has x number of cells, he can apply an operation to make the number of cells 2x. So this is one operation, right? And second is he can increase the number of cells by 1, and the third is he can decrease the number of cells in the container by 1, right? So the three operations are, if you have suppose n number of cells already, so you can make 2n cells, you can make n plus 1 cells, and you can also make n minus 1 cells. You can decrease 1 cell, right? And with every operation it is given that there are three types of costs. So what are these costs? These costs are x, y and z, right? So it is the cost of the operation. So this operation costs x, this operation costs y, and this operation costs z. So there are three different types of costs associated with every operation. Suppose I want to make 7 cells, right? So one of the way could be that from one cell I can double it to 2, I can double it to 4, then I can increment 1 5, then I can increment 1 6, and then I can increment 1 to 7. So one way could be this. Otherwise we can also make something like this. We can start from a single cell 1, we double it to make 2 cells, we double it to make 4 cells, we double it to make 8 cells, and from 8 we come back to 7. So this is another way of making, right? So we have to think how we can solve this problem, and it is given that from a state I can go to a state 2i, or I can go to a state I plus 1, and I can go to a state I minus 1, right? So basically if we are talking in terms of DP, you can say f of I is going to be minimum of 2i, f of 2i, f of I plus 1, and f of I minus 1. So these are the three states, but here the trick is that the current state is depending upon states which are greater than the current state, as well as on the states which are lower than the current state. So this is the tricky part here, that we cannot figure out, because let us talk in terms of bottom up DP, right? So if I talk in terms of bottom up DP, I know that to build a current state I, it must be dependent upon some other states which are lesser than I, right? So let me write in the other terms that f of I is depending upon these states. So instead of writing 2i, I can write I by 2, right? Because to make cells I can double this value I by 2 to reach this state, right? I can come to I from this state, and for this state f of I minus 1, I know that I can come to I from I plus 1, right? So this represents this state, right? So f of I can be reached via 3 states. The other one state is f of I minus 1, f of I by 2 is one state, another state is f of I minus 1, and another state is f of I plus 1. Let us say we are applying bottom up DP. So we know that the linear DP table will be filled in this manner, right? So when I'm going to compute I also need the value of f of I plus 1, which is not there. This value is not there. So how do we solve now? So if you carefully analyze this problem, we can say that the current state can be divided into two cases, right? So there could be two cases. Let us first talk about the case when the value of I is odd. So I am now going to write two cases, when I is odd, and the second case is when I is even. So let us say we are talking about some even I. So if I is even, so let us also write what all operations are there. So operations are, you can double with cost x, you can increment with cost y, you can decrement the cell with cost z. So if you are talking about this state, you are computing the value of dp of I, then what will happen is, you can say you can form this value by reaching a state which was I by 2 and then directly doubling it, right? So the first option of making dp of I is going to be dp of I by 2 plus the cost of doubling, which is x. So this is the first option you have. The second option is this option. You reach the state from a previous state. So you reach this state from a previous state. So this is nothing but dp of I minus 1 plus the cost of increment, which is y. And we are not going to take the third case. Because when we say that we are reaching the current state from the I plus 1th state, this value is always going to cost more. Why? Because to reach this value, we are going to do more number of operations as compared to this state, because this is an odd value, right? And let us first consider the case of the odd. Let us first consider the case of odd value when I is odd, right? So in this case, what can happen is that if I am reaching a state like this, and this is I and I is odd. This I is odd, right? So to construct dp of I cannot come from a state I by 2. This is not allowed because I is not a multiple of 2. So this operation is not allowed. What we can do to reach 7, I want to make 7. I can either come via 6 or I can come via 8. So these are the two operations, right? To construct 7, I can reach via 6 and I can also reach via 8. So I have to check what is the answer for 6 and what is the answer for 8. So basically I need these two answers. So let us say this value is nothing but dp of I plus 1. and this value is, let's say, 7. If I reach via 6, so this answer is easy. I can say dp of I is nothing but, it is nothing but I reach 6 and I add one cell. So it is going to be dp of I minus 1 plus the cost of adding one cell, which is given to us as y. But what about this cost? This cost I know is already computed. What about this cost? This cost is not computed, right? So this cost, to reach 8, I can either reach via 7, right? Sorry, this value is 8. So to reach 8, I can either reach via 7, but since I'm already computing 7, I cannot compute 8 via 7, right? So we will not come to 8 via 7. This route we will not take because we do not know 7. So the only way of making 8 is via 4. So 8 can be constructed via the dp of 4, right? So what I need to do, I need to say that dp of 8 will be nothing but dp of 4 plus the cost of doubling, which is x, plus the cost of decrement, which is z. So what I'm doing is, from 4 I'm going to 8, and from 8 I'm going to 7. So this value can be written as dp of I plus 1 upon 2, which is the value 4, plus the cost of doubling, which is x, plus the cost of decrement, which is z. So this is how I can reach 7. So what I'm going to do, from 4 I'm going to 8 with the cost x, and from 8 I'm coming back to 7 with the cost z. So this cost is going to be dp of I plus 1 by 2 plus x plus z, and we are going to take minimum of these two costs. So this solution will be the optimal solution for all those i's when I is odd. And for the even case, we know that we can come from a previous value or from a value which is exactly half of the current value. So we are going to take minimum of these two cases. We are not considering the case when we reach even from this place. Why? Because if you take any example, you will figure out that this path is always going to cost more as compared to these two paths, right? So by breaking the problem into two steps, into two cases, one for the odd case and one for the even case, we have almost solved this problem. Now let us try to write the code and test it on HackerBlocks. So there is a sample input as well, 5213, right? So we want to construct 5 cells and the cost of operations is being given to us. So the first thing is I have to take input some values n, x, y and z, the number of cells I want to make and the cost of each operation. Then let us read the values. And let us write one function which returns a value, long solve cell problem, and we get n, we get x, we get y and we also get z. So I'm going to use bottom up dp here, and I know that the base case, what should be the base case? To construct 0 cells I need 0 cost. To construct a single cell I also need a 0 cost because one cell is already given to us. And for all the states starting from 2 going till n, I'm going to compute my answer. So I can say if I is even, I mod 2 is 0, I can say dp of I is going to be minimum of dp of I by 2 plus x and dp of I minus 1 plus y. So these are the two possibilities for the even case. Else for the odd case, I know what all possibilities are there. It is dp of I minus 1 plus y, or we go to a cell which is exactly half of the next cell, next even value, right? So which is nothing but I plus 1 upon 2 plus the cost of doubling, which is x, plus the cost of decrementing, which is z. And finally I'm going to return dp of n. Yeah, we should also construct the dp array. So let us take a dp array here. And let us try for the custom input. And let us also print our answer. So solve cell problem n, x, y and z. Alright, so you can see, writing this code, we have solved all the possible test cases. So I hope you understood this problem. So thank you for watching. I will see you in the next tutorial. Hi friends, in this video, we are going to talk about a very interesting problem from Spoj. The name of the problem is mixtures. So it is based upon the idea of dynamic programming. Let us first go through the problem statement. So in this problem, you are given that there is a character, Harry Potter, and the Potter has n number of mixtures in front of him. So there are n mixtures in front of him, and these mixtures are arranged in a row. And it is also given that every mixture has one of the colors, and these colors can be numbered from 0 to 99, and there are 100 different colors. And it is also given that Harry Potter wants to mix all these mixtures. He wants to mix all the mixtures which are lying in front of him, right? So there are some mixtures and he wants to mix them, right? So let us say this mixture is A and this mixture is B, and when we add these two, we get a new mixture whose color is nothing but A plus B mod 100. This is the new color of the resulting mixture. During this process, some certain amount of smog is generated. Some smoke is generated. Let us say this is the smoke generated, and this smoke is given as, the amount of smoke generated is given as A into B, which is basically the product of the mixtures, right? So the resultant color is the sum of the mixtures, and the smoke which is generated is equal to the product of the mixtures. So it is given that we want to find out what is the minimum amount of smoke that is generated when we mix all the mixtures together. So what is the resultant smoke amount generated, and we have to minimize this amount, right? Let us try to understand this with the help of one example. So I am given, in the first test case, there are two types of mixtures. One is having a color of 18, the other mixture is having a color of 19. So clearly, when I mix them, the amount of smoke generated will be 18 into 19, which is nothing but 342. This is a very simple test case. Let us talk about the second test case. In the second test case, I am given there are three kinds of mixtures. The first mixture is having number 40, second is having 60, and the third is having number 20. it is given in the problem that at any point we can combine only two consecutive mixtures. So this is given, we can combine two consecutive mixtures to get the resultant. So the first possibility is I combine these two. If I combine these two, I will get a new mixture with the color of 0, because 60 plus 40 is 100 and taking mod with 100 gives me a 0. So the new color of the mixture is nothing but 0. And during this process, the smoke generated is nothing but 40 into 60, which is 2400. And if I combine this mixture with the 20th mixture, what I will get? I will get a new mixture which is having a color of 20. And during this process, the amount of smoke generated is 0, because 0 into 20 is going to be 0. Right? So we can say the answer is 2400 if we combine the mixtures in this fashion. Right? The other option is we can start the other way. We can start from combining these two. If we combine these two, the smoke generated will be 1200 plus the resultant mixture which we will get is nothing but 80. And now we have to combine 80 and 40. So if we combine these two, the resultant mixture will have a color of 20, and during this process the extra smoke generated will be nothing but product of these two, which is 3200. So the net amount of smoke generated is 4400. So we can say that the first answer was better because it resulted in the minimum smoke. So we have to consider all possibilities and we have to find out which mixture produces the minimum smoke. Now let us think about a brute force approach to solve this problem. Then we will move to dynamic programming. So let us say I have some mixtures M1, M2, M3 up to Mn. If I talk in terms of brute force approach, the idea is that I can divide these mixture into two parts. I can say that I will first solve for this part and I will solve for this part, right? So at any arbitrary point, I try to make a partition. Let's say at the kth mixture, I divide all the mixtures into two sets. So the idea of dividing is that we will first solve the answer for this part and we will also solve the answer for this part, right? So let us say this answer is x, this answer is y, and we will combine these two. So what will happen? Let us try to think with the help of one example. Suppose there are mixtures A, B, C, D. Let's say the mixtures are A, B, C, D. So it is quite possible that I keep A as separate and I solve for B, C, D first. Or it can happen that I solve A, B and I solve C, D and then combine these two. Or it can happen is I can solve for ABC and later combine the result with D. These are the possibilities of placing the brackets in the first case. So I can make a partition here, I can make a partition here, I can make a partition here. So you can see we can make a partition at any place, and out of all these cases, the case which gives you the best possible answer, right, will be your answer. So this is quite similar to the matrix chain multiplication problem. So I can say that I am going to divide my mixture at every place, at every step, right? So let us break down this problem. So if I place a bar here, so it becomes ABCD. If I place a bar here, it becomes AB followed by CD. If I place a bar here, it becomes ABC followed by D. Then further we can break it down. So I can say I will divide the mixture like this, maybe like this, or maybe some other type of answer, right? So in the worst case or in the smallest case, I will get that there is only one element left, right? So we can say if only one element is left, then the resultant smoke generated is 0, because we are not mixing it with any element. So one element will produce a smoke of 0. So this will form our base case in the problem. Suppose I have two elements, right? So what will be the smoke generated? I can say if I want to find the answer for BC, I can say find the answer for B, find the answer for C, and find when BC is being combined. So when we combine BC, the smoke generated will be B into C, right? Or let us say when we combine this part, in this part we have divided our problem into two sub problems. One problem is AB, one problem is CD, right? And when we combine these two, what is the smoke that I will get? So the smoke will be, the new resultant mixture will be A plus B, the new resultant mixture from here will be C plus D. So the total smoke will be product of these two, right? And I can say A plus B mod 100 into C plus D mod 100, right? Similarly, I can say that if there is a mixture like this, A1, A2, A3 up to AI or AK, followed by AK plus 1, AK plus 2 up to AN, right? And suppose I divide the mixture into these two parts. So the answer will be the smoke generated due to this part. Let us say this answer is X. Let us say this answer is Y, plus when I will combine these two mixtures, right? The smoke generated will be nothing but summation of the new resultant mixture due to this will be having a ID like this, A1 plus A2 plus up to AK, into the new mixture generated due to this will be having a ID like this, AK plus 1 up to AN, right? So I can say the final answer is going to be nothing but f of ij will be equal to f of ik plus f of k plus 1 till j plus cumulative sum of numbers from I to k into cumulative sum of numbers from k plus 1 till n. So this is the final recurrence we are going to use in solving this problem. I hope this recurrence is very clear to you, because this number denotes the mixture ID when the first part is mixed, and this part denotes the mixture ID when the second part is mixed. And here CSum is nothing but it is the sum of numbers from whatever the I is there, and we take mod with 100 at every step, right? The cumulative sum is this, and this is given from I to k or whatever the values are being given to us, and this is the recursive call. And if we carefully analyze this, we will come to know that there must be overlapping sub problems in this example, and hence we will use top down DP or bottom up DP to solve this problem. So now let us see the coding part of it. Let us see the coding part. So the first step is I should read whatever the input is being given to me. So the first thing is in 10, and it is the number of test cases is not given, so we have to read till end of line. Is scanf. So we have to read till end of line. So we now know the value of n. We have to read n integers, which denotes what all values are there. For I will scan an array, and I must define the array also, right? So I am defining the array. So array is like this, and let us also make one DP array. So let us take input the numbers. Then we have to also let us initialize our DP array with -1. So dp of ij is going to be -1, and let us write one function, solve mixtures, which accepts the starting index of the array 0, ending index of the array which is n minus 1. Now let us write this function. So let us say return type is long, solve mixture is a function. It takes the starting point, it takes the ending point of the array. And let us write the complete code for it. So let me write it as I and j. So I can say in the base case, if there is a single element, if I equals to j, then the answer is going to be 0, because the smoke generated for a single element will be 0, or I is greater than j, then also the smoke generated will be 0. Otherwise, I can check if the answer is already computed. So I can check if the answer is already there. So that is basically for the case of an overlapping subproblem. If dp of ij is not equal to -1, I can say return dp of ij. Otherwise, our task is easy. We have to break our expression at every value of k, right? At every possible k. So I can say for int k equals to start, or k equals to I, k less than equal to j, k plus plus. Try to break the expression at every step. And before that, let us assume our current answer, which is dp of ij, is nothing but a very large value, because we have to minimize our answer. This is a very large value, and dp of ij is going to be minimum of dp of ij. Then we have to write what is the answer for now. So we know that for a given expression, it's a1, a2 up to ak plus 1, ak plus 2 up to an. So if I am placing a break here, so the answer for this part will be computed using recursion. This will be given by a function from I to k, and this will be nothing but f of k plus 1 to j, right? And when I combine these two, so what will be added into my answer is the product of the final mixture generated in this case, and the product of with the number generated in the case of this, right? So this number will be nothing but summation of ai, where I goes from I to k, and summation aj, where j goes from k plus 1 to j, right? So this will be the product. So let us write here solve mixtures from I to k plus solve mixtures from k plus 1 to j plus the product. The product is of sum. We will make this function. So sum of all the numbers in the array from I to k into sum of all the numbers which are there in the array from k plus 1 to j. This is going to be the product, and this is the smoke generated when we combine two mixtures, right? This is the smoke which is being generated. So let us write the sum function also. So long sum, and here we get two values. One value is I, or let's say one value is s, one is e, and let us say there is an answer which is initially 0. Then I use a loop from s till e. I say answer plus equals to array of I, and answer mod equals to 100, and finally I return my answer. And here we can return dp of I and j. Now let us try to run our code over some input. This is the input here. Alright, so there is a small thing that this array should be of the type long long. Right. So you can see the answer is 342 and 2400, which is same as the sample output. And let us submit it over Spodge. So you can see we got the correct answers. So I hope you liked this tutorial, you learned a lot. So thank you for watching. I will see you in the next tutorial. Hi guys, so in this problem I am taking one problem of recursion and dynamic programming, and it is called friends pairing problem. So in this problem you're given that there are n friends and they want to go for a party, and it is given that each friend can go alone or he can go in a pair, right? So each friend can go single or he can go as a pair with some other friend, right? So two friends can make a pair or one of them can go single, right? So let us see what all. So let us see one example, right? So you have, suppose, three friends and they want to go to a party, and the output should be the number of ways in which they can go to the party, right? So the number of ways in which they can go to the party. So let us see, let us make cases, right? So if one goes single, then 2 and 3 can go in a pair. If 1 and 2 go together, 3 can go single. It is also possible that all 3 go single, and it is also possible that 1 and 3 go together and 2 goes single, right? So clearly you can see for this current case you will have how many ways? You will have 4 ways, right? And similarly, if you have n friends, then you have to count the number of ways, right? So my first advice to you is try to break down the problem, right? So try to break down it and try to make a recurrence, right? So make a recurrence, right? And the hint is you can use recursion or you can use DP, and the first thing you have to do is to make a recurrence, right? So I hope you have taken your time and tried solving this problem, and now I'm going to discuss the solution, right? The solution is very easy, right? So if we treat, suppose you have n number of friends, right? So if you have n number of friends, and for the last friend, the nth friend, you can have two options, right? So you can have two options, right? So if this friend goes alone, right, so it does not matter how the other friends goes, right? So if this friend is going alone, right, so if this friend is going alone, then you have to know the number of ways in which the n minus friends are able to go, right? So all the other friends, the thing we want to compute is f of n, right? So f of n is what we want to compute. So this will be nothing but the sum of two cases. When the last friend goes alone, then we will find out in how many ways the number of n minus friends can go. So it would be nothing but f of n minus 1 plus if it does not go alone, right? So if this friend does not go alone, then it will randomly pick one of the friends to go with him, right? So let's say it picks the ith friend, right? So it can pick one friend out of n minus 1 friends. So we will pick one friends, n minus 1 c1, and now how much people are left? So in the remaining part, if we ignore this and if we ignore this, because the last friend has has already paired up with one of the friends, we have only n minus 2 friends. Now we have to ask recursion in how many ways these friends can go, and these are n minus 2 friends. So the answer is nothing but f of n minus 2, and clearly these two terms will be multiplied because the last friend can pair up with any of these. It could be 1 comma 2, 1 comma 3, 1 comma 5, 1 comma 8, 1 comma 15, right? So any two friends can form a pair, and we have to worry about f of n minus 2, right? So this value is what we need. Now this reduces to a very simple recurrence, and I hope you will be able to solve this problem. And why you should use TP? Because like Fibonacci, this problem also will have overlapping sub problems. From n you are making two calls. If n is 5, you are making two calls, 1 to 4, other call to 3. This call goes to 3 and 2, and again you will be making a call to 2 and 1, right? So this recursion tree is going to be exactly same as the Fibonacci, and you will see there will be overlapping sub problems like in this case, right? So the answer is little different from Fibonacci because of this term, and this term is nothing but n minus 1. So you will find overlapping sub problems, hence it is advisable to use dynamic programming to solve this problem. I hope the concept is clear, and the coding part you should be able to implement, right? Thanks for watching. I will see you guys in the next.
Hi everyone. So let's now talk about a very important question from interview perspective, and the question is Catalan number, right? So it's a series that you may need to derive, or you can use the exact formula sometimes, but we are going to see a particular problem that is very common. So the question is, you need to count the number of BSTs, that is binary search trees, that can be formed using n number of nodes numbered from 1 to n. So it is given that, okay, you need to construct binary search trees. So not exactly construct, you need to count how many binary search trees are there, which can be formed using n nodes, and all of them are numbered from 1 to n, right? So question can be about binary trees also. So first we will discuss about binary search trees, then we will talk about how many binary trees are there, right? Okay, so let's first revisit what is a binary search tree. For example, let's say n is 3. Let me say n is 3. So you have 3 nodes. Let's say these nodes are numbered from 1 to 3. So can you think of a BST that you can form using these 3? Yes, definitely. Let's say I can put 1 at the root node. Then I can put, let's say, 2 on the right hand side, and 3 will be on the right hand side. Okay, so this is one tree that you can make. Okay, what else you can do? You can say, okay, I will start with 1. I can, instead of putting a 2 here, I can put a 3 here, and then I can put a 2 here, right? So remember, the element which is greater than the root node goes on the right, and then the element which is smaller than the root node goes on the left. So this is what the BST property is, right? And I think these are the only trees that you can form by taking 1 as the root node, right? Maybe you can say, okay, instead of picking 1, I will pick 2 as the root node. So you can construct a tree like this. 1 goes here and 3 comes here, right? Okay. Or you can say, I can make a tree with 3 as the root node, right? So with 3, you can say, okay, I can put 1 here, and I can put 2 here. Or I can say with 3 here, I can put 2 here, and I can put 1 here, right? So you can clearly see that these are the possible trees that you can make. So you can make 2 trees where 1 is the root, you have 2 trees where 2 is the root, and you have 1 tree where 2 is the root, and you have 2 trees where 3 is the root, right? So in total, you have 2 plus 1 plus 2, 5 possible binary search trees for this given case, right? Okay, so we need to count how many BSTs are possible for a given n, right? So if I start building my logic, I can say, okay, I am given n number of nodes, and any node can become a root node. So any ith node can become a root node. So I will put, okay, let's make the ith node as the root node, right? And let us assume there is a function f of n which basically counts how many BSTs I can make using n nodes. So this is what we need to compute. So what I can do, I can say, okay, I do not know how many trees I will have in this part. Okay. So when you take I as the root node, can you guess how many nodes we can put in the left subtree? So if I talk about left subtree, you can have I minus 1 nodes in the left subtree. Okay. And can you guess how many subtrees you can make using I minus 1 nodes? Definitely, you can make number of subtrees would be equal to f of, let's say this number of subtrees is equal to x, and this is equal to f of ni minus 1. That's correct. So using all of these nodes, you can just add them to the left subtree, and the number of possible subtrees would be f of I minus 1, right? So I can compute this subproblem. I can make x number of trees where x is f of I minus 1. Okay, what about the right part? Okay, so similarly, I can make y number of BSTs in the right hand side, and that y would be nothing but all the nodes which are greater than I will go into the right hand side part. So nodes numbered from 1 to I minus 1 will go here, and all the nodes numbered from I plus 1 to n will go here, and we need to find out how many possible arrangements are there for the right hand side part. So similarly, I can say there are y type of trees possible, and this y would be nothing but it would be equal to f of n minus I. Okay, so this is what it is going to be, because if you count how many nodes are here, it would be n minus I, and if you count how many nodes would be here, it would be I minus 1, it is n minus I. So clearly, in order to construct a complete tree, I need to have a left subtree, and I need to have a root node, and I need to have a right subtree. So this is what it makes a complete tree, right? So what I can say, right? So suppose root is fixed. As of now, let's say root is fixed. So in order to make a subtree, a complete tree, I need to pick one tree from the left, I need to pick one tree from the right, and then it will be entire subtree, right? So it's a and here, right? So I can pick from x number of subtrees, I can pick one tree in xc1 ways, and root is fixed, so there is only one way to have a root, and in the right subtree I can pick one tree in yc1 ways, right? So this becomes equal to f of I minus 1 multiplied by f of n minus I. This is what it actually becomes, right? Now the question is not about, you cannot keep the root fixed, and we have seen that root can be any node, right? So if you want to find out what are the total number of trees for all possible roots, so you will just do a summation here for all I, where I goes from 1 to n, and this is what your answer is going to be, f of n. So this formula, right, and you can implement this formula using recursion, but if you observe carefully, you won't find that there are overlapping subproblems. So you can optimize it using top-down or bottom-up DP, and you can compute f of n for every value of n, right? So let me just, let us also do some dry run for a small case. Okay, we will see what happens for, let's say, n equals to 0, n equals to 1, and n equals to 2, and n equals to 3. Let's do the dry run for some small cases also, right? Okay, so I hope this is clear. So we are doing a summation because we can consider every node as a root node, and then we can count, okay, how many trees are possible in the left and how many trees are possible in the right. So in total you can pick all the trees in these many ways, right? So also let's say what would be f of 0. So f of 0 means there is no node. So you will have how many trees? You will have basically one tree, right? So if you will construct a null tree, so that is a one tree, right? So f of 0 is going to be 1, and what about f of 1, right? So if you have only one node, then also you can say, okay, only one tree is possible. You can make one of the base case as this, so it is also going to be 1. Let us compute what is f of 2. Okay, so for f of 2, we can use this formula, summation of I minus 1 into f of n minus y. So first we need to compute, let's say the value of I is 1. So we will compute f of I minus 1, which is f of 0, into f of n minus I. N is 2, right? So n is 2 here, I is 1, and f of n minus I, so f of 1. So it gives me 1 into 1, which is 1, plus something. So I will make I equals to 2. I goes from 1 to n, so I is 2. So 2 minus 1, which is f of 1, into f of n minus I. So f of 2 minus 2, which is f of 0. So this is 1 into 1, which is 1. So if you add these two numbers, so you will get the answer as 2. So for n equals to 2, it says you can make two binary search trees. So clearly we can say, so this tree would be this tree, and another would be this tree. Exactly, so this is correct. So let's talk about n equals to 3. So in n equals to 3, I can have I as 1, I can have I as 2, and I can have I as 3. So when we are computing I equals to 1, we will say I minus 1, so which is f of 0, into f of n minus I, so which says f of 3 minus 1, which is 2. So it basically means when you have 3 nodes, you are putting 0 nodes in the left, so it makes a one possible tree, and you are putting 2 nodes on the right, right? So maybe something like this, or maybe something like this, right? So effectively it means you are putting 0 nodes on the left, 2 nodes on the right, and we have already seen using 2 trees, using 2 nodes, you can construct 2 different trees that you have seen here, right? So I can say f of 2 that we have already computed. So again, this is a sub problem that we have already computed. So this will become 0 into 1 into 2, which is 2. Okay. Okay. When I is 2, which means you are going to make the second node as the root node. So you will have one node here, and you will have a one node here, and we can also check this from the formula f of I minus 1. So I is 2 minus 1 f of 1 into f of n minus I. So what is n? N is 3 and I is 2. So it is also going to be f of 1. So it is exactly same as saying you are putting one node here and one node here, and you can have this answer is 1, this answer is 1. So there is only one tree possible. And that we have also seen here, that when you pick 2 as the root node, you can construct only one possible tree. So this is 2. And talking about I equals to 3, you have I minus 1, which is f of 2 into n minus I. N is 3, I is 3, so it is going to be 0. And this answer we know is 2, this answer we know is 1, so it is also 2. So 2 into 1 is 2. So if you add all of these, you will get 5. And you can see this case is exactly same as this case. When you have 3 on the root node, you can have 2 nodes on the left like this, and there are 2 possible trees that you can construct. So this, you can see this is exactly equal to 5, right? So you can just compute this for any given value of n using top down or bottom up DP, and you would be able to solve this problem. Apart from it, there is a formula for this particular series, and if you compute this for all values of n, this series this forms a series, and this is called a Catalan series. and general term of this series is given by, let me just tell you, right? So you can use this formula 2n Cn divided by n plus 1. So this is the nth term of this series, and for a given n, you instead of doing a dp, you can use this formula, but your interviewer might ask you to derive this. For that, you have to use this particular recurrence, right? So when n is 3, you can say this is 6c3 divided by 3 plus 1, 4. So this is 6 into 5 into 4 by 1, 2, 3 and 4. So this goes off, and you get 5. Okay, so let me just write it again here. So it becomes 6 into 5 into 4 by 1, 2, 3 and 4. So this goes off, and you get, there are 5 possible ways in which you can construct a BST, right? Now one related question would be, how many binary trees would be there, right? So let me just write down. So question could be, how many binary trees can you make? Okay, and sometimes they also say, tell me how many unlabeled binary trees you can make, right? These are two very related problems. So let me use a different marker. Okay, so let's see, unlabeled binary trees you can make. Okay, so unlabeled binary trees means you're only talking about the structure, right? So if you just remove the numbers from this BST, that becomes a unlabeled binary tree, right? And number of different structures would be same as BST, so it would be nothing but, the answer would be same as BST, and this is same as your Catalan number, right? Okay, and this is equal to 2n Cn divided by n plus 1. What about binary trees, right? So when I talk about binary trees, I also have the option to permute all the nodes in the same tree. So maybe this tree can be 3, 1, 2. Okay, so we can have all possible permutations in the same tree. So given whatever is the number of trees, you can permute all the nodes in n factorial ways. So if I talk about binary trees, it would be n factorial multiplied by the Catalan number or this f of n. So it is n factorial into 2n Cn divided by n plus 1, right? So this is the number of binary trees, because you can permute all the nodes in a BST in n factorial ways. So I hope you would like this video, and thanks a lot for watching this tutorial. And maybe in the next part we will cover the implementation, but you can do it on your own as well, right? Thanks a lot. See you guys.
So we are talking about another problem which is called the optimal game strategy, right? So in this question you are given an array. Let's say it is a 2-player game basically, right? So you are given a list of numbers. Let's say these numbers are 7, 3, 2, 5, maybe 8 and maybe 4, right? So you are given some 2n numbers, right? Or maybe you are given n numbers, and where n is even here. And let us say 2 players are playing this game. There is a player A. Let's say player A is Modi and player B is Trump, right? So both of them are playing the game, and each player can pick any number from each end, right? Each player can pick a number from any end, and it is given both the players are smart, or you can say equally wise, and you have to tell me, if Modi starts the game, then what is the maximum margin by which he can win the game? Maximum margin by which he can win the game. And the winning criteria is, whatever coin you pick, you sum all the coins till the end, and the same goes for the opponent, right? So both will play alternatively, right? So they will play alternatively. So if I say that example is something like this, let me take one small example. If the coins are 2, 4, 7 and 6, let's say Modi chooses the first move. Modi says I will pick 6 and Trump says I will pick 7. Then out of 2 and 4, Modi says I will pick 4 and Trump says I will pick, this is gone and this is gone, and Trump says I will pick sorry, so Modi chooses 6, Trump chooses 7, Modi picks 4, Trump chooses 2, right? So Modi will get 10 points, Trump will get 9 points, and the winning margin is 1. So margin is just 1. So you have to find out this margin, or maybe you can say score of this Modi. Score of Modi, right? So what is the logic you will apply here? So greedy won't work here. Suppose the numbers are 2, 3 and 7 and 1. So I choose Modi. Let's say Modi is greedy. So Modi chooses 3. So 7 is exposed to Trump. Trump chooses 7. So Modi chooses 2. Trump chooses 1. Modi loses. Trump wins. So if you apply greedy, you are going to fail. So left right से देख लेंगे जो भी numbers हो यहाँ पे. So we will either pick this. So अगर let's say f of ij denote करता है the maximum score player 1 can collect, ठीक है, maximum score that player 1 can collect from I to j. So ये क्या होगा? So अगर वो ai pick करता है, right? So if player picks ai, so what is the problem for opponent? Opponent भी तो कुछ pick करेगा. So opponent will pick either this number or this number. So यहाँ पे दो cases बनेंगे. Opponent will pick either aj, sorry, or opponent will pick ai plus 1. ये opponent pick करेगा. Suppose करो opponent ने 3 pick कर लिया. So what is the remaining array for the player? मैं player का score compute कर रहा हूँ, right? So remaining array for the player is nothing but f of I plus 2 to j. और अगर opponent ने j pick कर लिया, so remaining array is going to be nothing but this, f of I plus 1 to j minus 1. And since opponent is smart, so opponent वो pick करेगा जिसमें उसका profit maximum हो रहा है, और मेरे लिए वो remaining array छोड़ेगा जिसमें मेरा profit minimum हो रहा है. So this is going to be minimum of these two, because ये वाली जो चाल चली है वो opponent ने चली है. So opponent smart है तो वो ऐसी चाल चलेगा जिसमें मेरा profit minimum हो रहा है, ठीक है. या फिर स्टार्टिंग में हो सकता है कि मैंने aj पिक कर लिया, ओपोनेंट के लिए ये वाला एरे बचा है, हो सकता है उसने ये पिक कर लिया, तो मेरे लिए क्या बचा है, f of I to j minus 2. या फिर ये हो सकता है ओपोनेंट ने ये पिक कर लिया तो मेरे पास ये एरे बच जाएगा, f of I plus 1 to j minus 1. इन दोनों का मिनिमम. अब ये वाली चाल कौन चल रहा है, I पिक करना है या j पिक करना है, ये प्लेयर चल रहा है, तो इन दोनों का मैक्स. So this is the recurrence, ठीक है. Again this contains overlapping sub problems which you can verify, and base case will be if I becomes greater than j, you can return 0. If there are not any numbers left in the array, then you can return 0. So this becomes your base case. Now you can implement it using your top down DP, right? Bottom up से भी कर सकते हैं. Is this question clear to you? बॉटम अप में देखो हर बार क्या हो रहा है, आफ्टर एवरी मूव तुम्हारा एरे 2 से छोटा हो रहा है. एक तुमने पिक किया, एक प्लेयर ने पिक किया, राइट. सो फाइनली क्या होगा, यहां तक का आंसर तो 0 होगा डायगोनल तक का, क्योंकि एक कॉइन नहीं बचेगा, 2 बचेंगे. प्लेयर के लिए 2 बचे होंगे, उनमें से वो बेस्ट पिक कर रहा होगा. अगर मैं बोलूं 10 कॉइन्स हैं एक प्लेयर ने पिक किया, एक ओपोनेंट ने, 8 रह गए, फिर 6 रह गए, फिर 4 रह गए, फिर 2 रह गए, फिर एक प्लेयर ने पिक किया, एक ओपोनेंट ने, 0 कॉइन्स, राइट। सो बेसिकली तुम्हारी ग्रिड की फिलिंग यहाँ से होगी, और इस रो में कंडीशन क्या होगी, आई इक्वल टू जे इक्वल टू आई प्लस वन, राइट। सो अगर दो ही कॉइन बचे हैं, मान लो 5 और 3, और प्लेयर की टर्न है, तो कौन सा पिक करेगा, 5 जो बेस्ट है। सो दो वाले केस में ग्रीडी लग जाएगा, अगर दो ही कॉइन्स हैं, 7 और 4 हुआ तो प्लेयर कौन सा पिक करेगा, 7, 4 और 7 हो तो प्लेयर कौन सा पिक करेगा, 7। सो इसको तुम बेस केस बना सकते हो, इसको भी बना सकते हो कि इफ जे इक्वल्स टू आई प्लस वन, देन प्लेयर विल पिक, रिटर्न कर दो मैक्स ऑफ ए आई एंड ए जे। तो इसको यूज करके अपना बेस केस लिख लेना, और ये वाले सेल्स इन पे कॉल करेंगे, और ये हो जाएगा। नहीं तो ज्यादा कंफ्यूजिंग लग रहा है तो बेटर है कि यू यूज टॉप डाउन डीपी, ठीक है। टॉप डाउन करो, एकदम चिल सीन है, कुछ भी नहीं है, बहुत ही आसान है, टॉप डाउन से बहुत जल्दी हो जाएगा। फॉर्मूला कैसे है, that if you are picking this number, then the remaining array for the opponent is this. Opponent will either pick this or pick this. So opponent अगर j चलता है तो तुम्हारे पास ये array बचता है, opponent अगर ये पिक करता है तो तुम्हारे पास ये array बचता है, वही मैंने यहाँ पे लिखा है। एंड ओपोनेंट वो array तुम्हारे लिए छोड़ेगा जिसमें तुम्हारा मिनिमम हो रहा है, क्योंकि ओपोनेंट अपना फायदा सोचेगा, ठीक है।
Now let's start writing the code for Alyona and strings from code forces. So we'll be implementing a similar solution to that described in the video, but yeah, there were some cases in video that we did not mention explicitly, which we need to code over here. So IS and IT are the same, however I'll also have a continuity and a remaining count. So if I reach IS reaches N or IT becomes equal to M, this is the base case, right? So I'll return a yes, like if rem is equal to 0, then I'll return a 0, else I'll return and something like int underscore min, so that it does not account in finding out the maximum answer, because that's not required. We need something in exact terms, so like the k value mentioned is in exact terms, so we need exactly k. So if rem is equal to 0, then only it makes sense, else we need to ignore the answer. So that's why I kept it as an int underscore min over here. Now the general condition for any top down dp would be something like this. In this case I'll return this as it is. Now the remaining cases I'll initialize ret to some int underscore min. Now there can be two cases, if continuity is equal to 1, or the other case is if the continuity is equal to 0. So we only change the number of remaining once we reach a certain condition. For example, that we have p1, p2, p3, p4 and p5. So the remaining here, like if we are standing on p3, if let's suppose p3 has a length of 5, let's assume, so and p3 is a string like a b c d e, then if we are on b in p3, then the remaining stays out to be 3. We'll change the remaining only when we reach the end of some condition, like when we'll jump from e in p3 basically makes remaining to 2. So this case is required for writing this condition as my base condition, because it may happen that if I have a remaining of 0, then some string may be in continuity which needs to be considered. So for that we need to do this. So now if continuity is equal to 1, return is equal to maximum of return comma solve is plus 1 comma it plus 1 comma remaining. So we'll just start with this case wherein this is the normal case. So it is like this. In this case we are actually jumping something, right? And so whenever we are jumping, we are actually not considering them. So we'll make it rem minus 1 and continuity equal to 0, because we are actually breaking the continuity over here, right? Similarly here, this case can also be there identically, symmetrically. So now, but it may also happen that if s of is equals to t of it, then this is a case which we need to consider. In this case, return is equals to maximum of return comma solve of is plus 1 it plus 1 comma remaining 0. So remaining comma 1. So in this case we do not change uh, like the number of remaining strings, and we continue the old string, but it may also happen that it's beneficial to cut this string now. So we change it to rem minus 1 and make the number of strings and change the continuity to 0. However, in the other case where continuity is equals to 0, we need to write these two conditions again. I'll make it return so this condition stays out to be like this, because if it's 0 then we have already counted the remaining to be correct and we are not actually breaking anything. So these two conditions are correct. How like after doing this, if s of is equal to t of it, then that's the issue. We need to handle it somehow right now. So we can do it like solve of is plus 1 it plus 1 remaining and 1. This is the issue. So whenever we start a new string over here and we ask the person to maintain the continuity, then the remaining stays out to be the same and it gives out 1 only. However, in both of these cases 1 would be added to my answer, which I earlier forgot to add. Yeah, because actually I'm including the s of is and s of t of tth element, t of ith element. So this is how this proceeds, right? So this condition is actually the same, even if its continuity is equal to 1 or continuity is equal to 0, because this is completely in our hand whether we want to continue it or not. So can we write a same thing for them? Yeah, we can actually shift this from here to here. Yeah, and before that we can simply make it to be rem minus not not cont. So actually if continuous is equal to 1, then this is same, so I can replace it by continued over there, not cont. Instead I'll replace it with this. So here I can remove these if conditions as well, and our code shrinks to a very small code. Yeah, so now we'll take input like scene n m k and scene s t, and now we'll find out the answer using solve 0 comma 0 comma k comma 0. Okay, so I need to store the dp as well. The remaining here is 12 and the continuity here is 2. Yeah, the remaining can be at max 12, right? So the answer here which is coming out is 0, which makes sense because we have not mem set the dp to -1. Once we have done this, the answer comes out to be 2. We can copy it from here and check whether it gives out 7 or not. Yes, it is giving out 7. Let's try submitting this and see whether this gives the correct answer or not. Okay, so just a second. I'll write it out to be 682/e. Okay, so it may be 681/e. Okay, so it's 683/e. No, just a second, I lost the problem, I guess. It was a T problem. Yeah. So now we'll try and submit this question. Yeah. So we have got an AC on this. So that's it from my side. Thank you very much. Now let's start writing the code for Alyona strings from code forces. So we'll be implementing a similar solution to that described in the video, but yeah, uh, there were some cases in video that we did not mention explicitly, which we need to code over here. So is and it are the same. However, I'll also have a continuity and a remaining count. So if I reach is reaches n or it becomes equal to m, this is the base case, right? So I'll return a yes. Like if rem is equal to 0, then I'll return a 0, else I'll return and something like int underscore min, so that it does not account in finding out the maximum answer, because that's not required. We need something in exact terms. So like the k value mentioned is in exact terms, so we need exactly k. So if rem is equal to 0, then only it makes sense, else we need to ignore the answer. So that's why I kept it as an int underscore min over here. Now the general condition for any top down dp would be something like this. In this case, I'll return this as it is. Now the remaining cases, I'll initialize ret to some int underscore min. Now there can be two cases. If continuity is equal to 1, or the other case is if the continuity is equal to 0. So we only change the number of remaining once we reach a certain condition. For example, that we have p1, p2, p3, p4 and p5. So the remaining here, like if we are standing on p3, if let's suppose p3 has a length of 5, let's assume, so and p3 is a string like a b c d e, then if we are on b in p3, then the remaining stays out to be 3. We'll change the remaining only when we reach the end of some condition. Like when we'll jump from E in P3 basically makes remaining to 2. So this case is required for writing this condition as my base condition, because it may happen that if I have a remaining of 0, then some string may be in continuity which needs to be considered. So for that we need to do this. So now if continuity is equal to 1, return is equal to maximum of return comma solve is plus 1 comma it plus 1 comma remaining. So we'll just start with this case wherein this is the normal case. So it is like this. In this case we are actually jumping something, right? And so whenever we are jumping, we are actually not considering them. So we'll make it rem minus 1 and continuity equal to 0, because we are actually breaking the continuity over here, right? Similarly here, this case can also be there identically, symmetrically. So now, but it may also happen that if s of is equals to t of it, then this is a case which we need to consider. In this case, return is equals to maximum of return comma solve of is plus 1 it plus 1 comma remaining 0. So remaining comma 1. So in this case we do not change uh, like the number of remaining strings, and we continue the old string, but it may also happen that it's beneficial to cut this string now. So we change it to rem minus 1 and make the number of strings and change the continuity to 0. However, in the other case where continuity is equals to 0, we need to write these two conditions again. I'll make it return so this condition stays out to be like this, because if it's 0 then we have already counted the remaining to be correct and we are not actually breaking anything. So these two conditions are correct. How like after doing this, if s of is equal to t of it, then that's the issue. We need to handle it somehow right now. So we can do it like solve of is plus 1 it plus 1 remaining and 1. This is the issue. So whenever we start a new string over here and we ask the person to maintain the continuity, then the remaining stays out to be the same and it gives out 1 only. However, in both of these cases 1 would be added to my answer, which I earlier forgot to add. Yeah, because actually I'm including the s of is and s of t of tth element, t of ith element. So this is how this proceeds, right? So this condition is actually the same even if its continuity is equal to 1 or continuity is equal to 0, because this is completely in our hand whether we want to continue it or not. So can we write a same thing for them? Yeah, we can actually shift this from here to here. Yeah, and before that we can simply make it to be rem minus not not cont. So actually if continuous is equal to 1, then this is same, so I can replace it by continued over here, not cont. Instead I'll replace it with this. So here I can remove these if conditions as well, and our code shrinks to a very small code. Yeah, so now we'll take input like scene n m k and scene s t, and now we'll find out the answer using solve 0 comma 0 comma k comma 0. Okay, so I need to store the dp as well. The remaining here is 12 and the continuity here is 2. Yeah, the remaining can be at max 12, right? So the answer here which is coming out is 0, which makes sense because we have not mem set the dp to -1. Once we have done this, the answer comes out to be 2. We can copy it from here and check whether it gives out 7 or not. Yes, it is giving out 7. Let's try submitting this and see whether this gives the correct answer or not. Okay, so just a second. I'll write it out to be 682/e. Okay, so it may be 681/e. Okay, so it's 683/e. No. Just a second, I lost the problem, I guess. Oh, it was a T problem. Yeah. So now we'll try and submit this question. Yeah. So we have got an AC on this. So that's it from my side. Thank you very much.
Hello friends, we are talking about a very interesting problem from Hacker Blocks. The name of the problem is rock, scissors and paper. In this problem, you are given that there are kids in a shakha which are playing a game of rock, paper and scissors. So what happens in this game is that every student can play a role of rock, paper, and a scissor, and it is given R number of students choose to become rocks, S number of students choose to become scissors, and there are P number of students who choose to become papers. And when there is a fight between rock and a scissor, rock kills scissor. If there is a fight between Caesar and a paper, Caesar can cut the paper. And we also know that paper can kill the rock if there is a fight between paper and a rock. Now, our task is to print the probability of rock being the only survivor in the game, Caesar being the only survivor in the game, and paper being the only survivor in the game. So let us see one test case. It is given all of the numbers of rocks, scissors and papers is less than equal to 100 and there are 10 test cases. So let us see what is the sample input. So in the first case, I am given the number of testing samples followed by the number of rocks, the number of scissors and the number of papers. So since each of these values is same, the probability of every value will be same also. So we can see that every probability comes out to be 0.3 because the number of rocks is same as the number of scissors and it is same as the number of papers. But suppose the values are changed a little bit, then we see a totally different outcome of probabilities. And we also see that this is not symmetric. This is not symmetric because if there are two number of rocks and one number of scissors and two number of papers, the output is going to be little different. So let us see how we can solve this problem using recursion and dynamic programming. So let me come here. So we are given R number of rocks, P number of papers, and S number of scissors. So I have to compute three results. So this problem has to be divided into three parts. So in the first part, I will compute what is the probability of rock being only survivor in the game. So I can say there is a function f1 which takes the number of rocks we have, it takes the number of papers, and it also takes the number of scissors, and it outputs the probability of rock being the only survivor in the game. So how this function will look like, let's also go into that. So let us also write what all fights are available possible. So if there is a fight between rock and a paper, if there is a fight between rock and a paper, then rock can kill, sorry, then paper can kill the rock, right? So if there is a fight between rock versus paper, who is going to win? Paper is going to win. If there is a fight between paper and a scissor, who is going to win? Scissor is going to win. If there is a fight between scissor and a rock, who is going to win? Rock is going to win. So these are the possible outcomes of the fights. And now we are talking about this function. The function is called f1 and it takes three arguments: the number of rocks, the number of papers, and the number of scissors. So what will happen is we will consider all the three scenarios. So we will consider all three scenarios because these kids are in a game, and in the game any scenario can happen. So suppose there is a fight between rock and a paper and paper wins. So if there is a fight between rock and a paper, then the probability of survival of rock is going to be r minus 1 because paper is going to win, so a rock is going to die. So the number of papers will remain as it is and the number of scissors will remain as it is. So this is the scenario when paper kills rock. But this is not the complete answer. So we also have to multiply with the probability of fight between a rock and a paper. So what is the probability? The probability is going to be nothing but the number of, so probability is chances of fight between paper and rock over total number of fights, over total number of fights. So what is the total number of fights? So let us also calculate these two values. So probability we need to find out by using this formula. So a fight can occur between paper and a rock when we have one paper and one rock. So we can choose one paper in PC1 ways and we can choose the rock in RC1 ways, and upon total fights. So all the fights can happen between two entities. So it could be RC1 into PC1 plus PC1 into SC1 if there is a fight between paper and a scissor, into SC1 into RC1 if there is a fight between a scissor and a rock. So these are the total fights. So I can say this is the probability, or you can write total value of the fights is nothing but R into P plus P into S plus S into R. These are going to be the total number of fights, and this formula will be used in calculating various values. So the probability of survival of rock. So we are talking about those cases when the rock survives. So rock survives when, or rock survives means we are calculating f1 of r, s and p. This is the value we are computing, or you can say rps. So f1 is a recursive function which we say computes the probability of survival of the rock. So this function is going to compute the probabilities of survival of the rock when there is a fight between a rock and a paper, and when there is a fight between paper and a Caesar, and Caesar and a rock. So let us consider the first scenario, this scenario we are talking about. In this scenario, it is going to be f1 of, there is a fight between rock and a paper. So rock is going to die. So remaining rocks are r minus 1, papers remain p, and Caesars remain s into the probability. So it is nothing but the number of rocks we have into the number of papers divided by this total value. So this is the first probability. Second probability is, suppose the rock will again survive if there is a fight between a paper and a Caesar. If there is a fight between paper and a Caesar, so what will happen? The number of rocks do not change. The number of papers will be reduced by 1, and the number of Caesars will remain as it is into the probability of this fight. So this fight can occur if there are at least one paper. So number of ways to choose the paper is p, number of ways to choose the Caesar is s upon total, which we have already computed. The third step, I know the rock will survive if there is a fight between this Caesar and a rock. So in case of Caesar and a rock, rock will win. The number of rocks remain as it is, the number of papers remain as it is, and the number of Caesars are reduced by 1 into the probability of this fight. So we need a rock and we need a Caesar for this fight divided by the total. So these are the three scenarios from where we can compute the probability of survival of the rock, and there will be some base cases also, right? So these scenarios form the recursive case. Now let us also talk about the base case. So these are your recursive cases which we can memorize using DP. Now let us talk about the base case. So in the base cases, we can see there are three parameters r, p and s. So all these parameters will approach to 0. So there will be case when r becomes 0, or you can say the number of Caesars becomes 0. In the following case, I can say the probability of survival of the rock is going to be 0, because the number of rocks are 0, so the probability of survival of the rock is 0 because all the rocks have died. Or the number of Caesars becomes 0, right? So if number of Caesars become equal to 0, it means that there is no one to cut the papers, because the opponent of the rock is paper and opponent of the paper is Caesar. So if there are no Caesars, then there are going to be, paper is going to survive and paper is going to kill the rock, right? So paper, if the Caesars do not exist, then papers are going to kill the rocks. So in that case also, the probability of survival of the rock will become 0. The other cases, the other base cases, if the number of papers become equal to 0, then what will happen? All the rocks are going to survive. So I can say in that case, I will return 1. Why? Because if papers are killed, the rocks are going to survive. So this basically means if paper does not exist, then the rocks will survive. then the rocks will survive. So this is an important base case for the survival of rocks. Similar cases will be for the other two parts as well. So this was the first case when we are talking about the final survival of the rock. Similarly, we can write two more cases when we want to talk about the survival of paper and we want to talk about the survival of the Caesar. So only the base cases will change, rest of the cases will remain almost same. So let us see about the second case. So we have to write the case when Caesar is surviving, and we have to write the third case, the probability of survival of the paper. Now let us see these cases with the help of our code. So I have already written a code here. So I have written three functions. The first function, right, tells us about the probability of survival of the rock. So let us see this function. So this function basically tells the probability of survival of the rock, right? In this case, we know if the number of paper becomes 0, the probability of survival of rock becomes 1, because paper is the only item which kills the rock. And here I have used memoization, since there are three parameters, one is R, one is S, and one is P. So it becomes a problem of 3D-DP. And every state has these three dimensions. So if a particular state is already computed, we directly return the answer. Otherwise, we compute the total is this. We say initially result is 0, then to our result we add three values. So these are the three recursive cases which I have just told, and with every recursive case I am multiplying the probability of that case. So in this case, the first case, paper kills rock. When paper kills rock, the number of rocks are decremented by 1, the number of papers do not change, and the probability of a fight between rock and a paper is nothing but R into P upon total. Similarly, we are talking about the case when rock kills Caesar and Caesar kills paper. So similarly, I have written these two cases as well. And by adding the probability of these three cases, I know that final answer is nothing but the sum of these three probabilities. So I have written dp of RSP is nothing but the result. So this entire function is for the rock. Similarly, I have another function f2 which is for the paper. Sorry, this is for the Caesar. So you can see if the number of rocks becomes 0, the probability of survival of the Caesar becomes 1. So this function has been written for the Caesar. And you can see when number of paper is 0 or the number of Caesars is 0, the answer is 0, because paper is the only thing which can kill the rock, and paper kills rock and rock kills Caesar. So if the number of papers is 0, so there is no one to kill the rock, and ultimately rocks are going to kill the Caesars. So in that case also, the probability of survival of the Caesar becomes 0. And the rest of the stuff is same. These function calls are almost same like the earlier ones. So if there is a fight between paper and a rock, so this is the equation. If there is a fight between rock and a Caesar, this is the equation. And if there is a fight between Caesar and the paper, we write this is the equation. Paper is reduced by 1 because Caesar cuts the paper, and the probability is S into P upon total. And finally we compute this value. Remember, after every call, and this is the third case, very similar to the above two cases. So in main, what I have done is I have taken the number of test cases followed by the values of RSP, then I call the setDP function. So it basically initializes our 3D array with -1. So it initializes all the elements of the 3D array with -1 as the entry. So I have initialized before calling the f1 function. Then again before calling the f2 function, I have initialized this array, again calling the f3 function, and before that I have initialized my 3D array, right? And in the output, I want my output to be precisely 9 places after decimal, so I have used the set precision function followed by answer 1, answer 2 and answer 3. So this is how the entire code is being made. Now let us try to run this code over the sample input. So this is the setDP function, right? So let us run our code over the input and let us see what is the output we are getting. So this output is 0.333 when all the test cases are 2. For this test case, it is same as the desired output, right? Now let us submit it over HackerBlocks and verify if this code works. So language is C++, and let's submit it. So you can see this code passes all the test cases, and this is how we solved this problem. And let us also talk about the complexity of the solution. So you can clearly see that we have used 3D DP, and we are given in the question the constraints. So it is given R, S and P are less than equal to 100. So our complexity is nothing but we are building this array dp of RSP. So this is 100 into 100 into 100, which is of the order 10 per 6, and it is also given there are 10 test cases. So the final solution is getting accepted because we are doing work less than equal to 10 raised to the power 7. So this is how we solved the rock, paper and the scissors problem. Thank you for watching. I hope you liked this tutorial. Hi friends, we are talking about a very interesting problem from HackerBlocks. The name of the problem is Diwali puzzle. In this problem, you are given that Diwali season is going on and everyone is decorating their homes with lights. So we write 1 for the bulb which is in on state and 0 for the bulb which is in the off state. And what Bob does is he creates an array of size equal to the number of light bulbs. Suppose there are n bulbs, so Bob creates an array of n light bulbs. Some of these bulbs are in on state and some of these bulbs are in off state. And what he does is he calculates the sum of all adjacent pairwise products. It means he will multiply these two, 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 and he will multiply these two. So sum of pair of products in this case is going to be 0 plus 0 plus 1 plus 0 plus 0, right? So the sum of pair of products is going to be 1. So we are interested in knowing that how many combinations of these light bulbs of size n are there that will give sum of products equal to a given value k. It means we are given the value of n and the value of k. See this test case. So see this test case, we are given n and we are given k, where n denotes the number of total light bulbs and k denotes the required sum of products of adjacent elements. So k is the required sum which we want to make, and you can see that as the constraints are quite large, so if you try to generate all possible combinations of light bulbs, it will take you 2 raised to the power 100 time for every test case, so which is very large. So in any case, the brute force solution will not get accepted, so we have to think something better. So we will take the help of dynamic programming to solve this problem. Let me tell you with the one example, one example test case. Let us see. So for example, the sample input is, there are 6 test cases, and in every test case you are given the value of n and you are given the value of k. The output is 2. So the question says there are 5 light bulbs. I do not know in what order the lights should be placed, but the output is 2. Sorry, the output should be 3. So we have to place, let us try to place bulbs like this. So if I found the cumulative sum of ones and zeros, so in this configuration I have assumed 4 bulbs are on and 1 bulb is off. So the configuration of bulbs is not given. This we have to assume ourselves. So let us say what is the sum. So sum is nothing but 1 into 0 plus 0 into 1, which is again 0, plus 1 into 1 plus 1 into 1. So this sum is nothing but 2, but the required sum is 3. So we cannot try this configuration. So we cannot have this as our configuration. Instead, what we should have, I should have something like this. I should have 4 bulbs in on state and the final bulb in off state. So what is the answer for this one? It is 1 into 1 plus 1 into 1 plus 1 into 1 plus 1 into 0. So this gives me the sum of products of pairwise elements as 3. And another configuration which I could have is, instead of placing 0 at, I can place this 0 in the beginning. So again I will have 0 plus 1 plus 1 plus 1. Again the sum of products is 3. So I can see there are 2 configurations possible, hence 2 is my final output. So we are given the value of n and k, and we have to output how many possible configurations are there in which sum of product of elements is exactly k. So this is our problem. So I give you 2 minutes to think about the solution, then you can watch this tutorial to understand it better. Now to understand the solution, we have to take a n size array. Let's say we have a array of n elements, or you can say we have to fill elements in all the n positions, right? So if we try to generate every possibility, then it is going to take a lot of time. So what we are going to do, we are going to use dp, because there must be some overlapping sub problems in this case as well, because it is quite possible that in multiple configurations the first part of the configuration is same. It is quite possible, right? So what I'm going to do, I'm going to build up the array in a left to right fashion and using dynamic programming. So let us see when we get 1 in our answer, right? So suppose you have some numbers, some lights placed like this, and this is the box you are filling, right? Suppose this is the current position, this is the ith position which you are going to fill, right? So if you put 1 at this position, you will see your contribution to the answer will be incremented by +1. So you can say the count will increase by +1 because this pair will contribute 1. So it will depend upon what is the previous element which you have stored in your array. So it will also depend upon the previous element. So if the previous element was 1 and the current element is also 1, then your count will increase, otherwise it will not increase. Suppose the previous element was 1 and the current element which you put is 0, then your count will not increase. Or if your previous element was 0 and your current element is either 1 or 0, again if you multiply these two elements, your count is not going to increase. So these are the cases which will help us to solve this problem. So let us talk about some recurrence here now. So I can say if my previous element in my array was equal to 1, then my answer is going to be since we are doing it recursively, so we know what is the answer generated so far. We know the answer generated so far. Whatever answer we have generated so far, we are going to do answer equal to answer plus the answer of the remaining part, right? So the remaining part will be computed using recursion. So what is this part? So at the ith index I am placing a 1 here, right? And this becomes the remaining part. Now this becomes the remaining part, or this becomes the remaining part. So whatever contribution I get from the remaining part will be my answer, and answer denotes the number of ways to generate a count of a, right? So I can say it is nothing but answer plus my recursive function f, which accepts the current index I, and since we are calling upon the next position, so the current index is I plus 1, and for this position if I am placing a 1 here, so this becomes a previous, right? So let me define the function. So let us first define the function. So there is a function like this: f of I, the current index, what is the value at the previous index, and what is the count you have generated so far. The third parameter is the count, right? So this is the function which I am going to use. So here I denotes the index at which I am going to compute my answer. Previous denotes what does the entry in the previous cell contain. Does it contain 1 or does it contain 0? And count denotes what is the count, what is the sum I have generated so far, right? So if the previous element was 1 and I am placing 1 at the current index, we are talking about this case. So the previous element was already 1 and we are placing 1 at the current index. So in the next call, the previous element now becomes 1 and count becomes count plus 1, because in our total answer we have added 1 more, right? So count becomes count plus 1. Otherwise, if the previous element was 0, then I can say answer is going to be answer plus f of, if the previous element was 0 and I place 1 at the current position, right? So we are talking about this kind of case. This was the previous element and we are talking about this position, ith position. So at the ith position I am still placing 1 and the previous element was 0. Now the new previous element is going to be 1, and but the count will not increment because the pairwise product of 1 and 0 is going to be the same. So whatever is the count earlier is the count now. Now let us talk about the case when we place 0 at the current position, right? So in this case the value of the previous element will not matter. So let's talk about another case when we are placing 0 at the current position. Placing 0 at the current cell. So in this case, the value at the previous cell will not matter. So whatever is the value at the previous cell will not matter, because at the current position I am placing a 0, and this 0 multiplied with any number is not going to contribute anything to my answer. So I can say my answer is now going to be whatever the contribution, whatever the answer I'm going to get from the remaining part. So answer equal to answer plus f of I plus 1. Now at the current position it is 0. For the next cell, this cell forms the previous position. So the element at the previous position is now 0, and my count is going to remain as count because the answer is not going to increase, right? So this is the case when we are placing 0 at the current cell, and these are the cases when we are placing 1 at the current cell. So when we are placing 1 at the current cell, it also depends if the previous cell contains 1 or 0, right? But when we are placing 0 at the current cell, it does not depend whether the previous cell contains 1 or 0. And this is the answer for our current call. So I can say f of I previous and count is the answer, right? So I previous and count is equal to our answer. And you know, this can be converted into a dp. So it can be written as dp of I previous and count is our answer, right? And we know this I can take 100 values, this previous can take 2 values, and this count again can take 100 values as it is given in the question. So the complexity is of the order 10 raised to the power 4 steps for every test case, right? And we know there are 100 test cases, so the overall complexity is of the order 10 raised to the power 6, which will get accepted. So let us try to write this problem in the form of code. We will think about base case and we will also try to solve this problem. So I have constructed a DP array and I have written a function f, or maybe you can give it a different name. So this function accepts 3 values. One is the current index I'm working upon, the second is the previous value, and third is the count. Count denotes whatever sum I have generated so far. So in the base case, since I am starting from the index 0, so if I reaches n, it means we have covered all the n elements, all the n bulbs, and we can check if count becomes equal to x. So here x equals to k in the question, so we can say return 1, otherwise we can say return 0. So what is happening is that we try various possibilities. Suppose we place 0 here, we place 1 here, again we place 1 here, we place 1 here, and we place 1 here, right? And I now comes to this index, so 0 1 2 3 4, and suppose n was 5 and I now comes to this index. So we already know that the count generated so far is nothing but 3, and we check if this 3 is equal to 3. Yes, so count is equal to x, and we say return 1. So we know that we have found one way of making sum equal to 3. So this is what the base case means. And I'm going to use top down DP, right? So I will add a check that if the current state of the DP, which depends upon 3 parameters, has been already computed or not. So if this state has been computed or not, so I can check if DP of I previous and count is not equal to -1, it means the answer has been computed. So I can say return dp of I previous and count. Otherwise, if it is not computed, I'm going to compute my answer, and I can check if previous equals to 1. If the previous number was 1, then my answer will have this thing, the same recurrence which we had written in the otherwise our answer is going to be this. The current element is still 1, but the count does not change if the previous element was 0. So suppose you are filling the array and the previous element was 0 and current element you are putting as 1. So the product of these two numbers is not going to add anything in your count, but here it will add +1, right? So here I think I should add +1 here. Suppose the previous number was 1 and the current number is also 1, right? So previous was 1 and the current is also 1. So this is going to add +1 to your count. So let me write +1 here, and whatever the answer we get from the remaining part will be added to our answer, whatever we get from this remaining part. So this remaining part starts from I plus 1, and for this part the previous element is 1 because the previous of this is 1, and for this part the previous element is also 1, so this element is 1. And it is also given that we have to take mod. So let's say answer percentage equals to mod, and we are also left with case when previous element, when the current element is 0, right? So when the current element we put is 0. So let us also try to compute the answer when we try to put current element as 0. So current becomes a previous for the next element and count remains the same. And let us also take the mod here. And let us return now dp of I previous and count. And this is equal to answer. I think that's all. So let us try to run our there is a small mistake. This should be f. This should be f here. F is a function. So let me give one input, and the values of n and k are 5 and 3. So yes, the answer is 2, and let us run for the sample input as well. So 2118541. Yes, so it matches with the sample output, and let us submit our code. Yeah, so all the test cases have been passed. So the one thing which you should see is in the initial call, what I have done is I have put the previous element as 1, right? So I am starting from the first index, and the 0th element I have put as 0 here, and the 0th element, right? So this element is 0 and this element is also 1, and I'm starting from the first index in both the examples. In both the calls, I'm starting my call from this point, and this point. That's why the initial I is 1 and the previous element is kept 0 and the previous element is also kept 1, and the initial answer, the initial count is 0, right? So initial count is 0, and for both of these cases, whatever answers I get, I have added them, right? So I computed the answer when the first element or the zeroth element was 0. I computed the answer when the first element was 1, and I summed up these two answers. So this allowed me to compute my final answer. I hope you understood this amazing problem. Thank you for watching. Hi friends, we are discussing interesting problem from Hacker Blocks, which is Valentine magic. So in this problem, you are given that you are in Russia, and in Russia, the number of boys is less than the number of girls, or maybe you can say there are more number of girls in Russia as compared to the number of boys. So all the boys have an advantage of choosing a girl for the Valentine evening because the number of girls is more, so every boy is bound to get a girl for the Valentine evening. And it is also given that each boy has some certain number of chocolates, let's say X, and each girl has some number of candies, let's say Y. So our task is to minimize the sum of absolute difference between boys chocolate and the girl's candy. So every boy is going to be paired with a girl, and we have to minimize the difference between the number of chocolate that boy has and the number of candy that the paired girl has, and this we have to do for all the pairs, right? And this will also happen that some of the girls will not be paired with any of the boys, but that's perfectly fine, right? That's perfectly fine. So the first line of the input gives you two integers n and m followed by n values and m values. So n is the number of boys and m is the number of girls, and it is given the number of girls is greater than equal to the number of, and you can have up to these many chocolates and these many candies, and the number of boys and girls are of the order 5000. And for example, consider this test case. So here you are given that there are two boys and 5 girls, and these are the number of chocolates that the two boys have, and these are the number of candies that the girls has. So I can pair the boy having 4 chocolates with the girl having 4 candies, and I can also pair the boy having 5 chocolates with the girl having 5 candies. So in this case, the sum of differences is going to be 4 minus 4 plus 5 minus 5, which is going to be 0. So this is the exact output, right? So now let us see how we can solve this problem algorithmically. So we are talking about the Valentine magic problem. So let's say we are given boys b1 b2 up to there is a ith boy having some candies, and the last boy, nth boy, and there are some girls g1 g2 jth girl and the mth girl, right? So we have these many girls. The first thing that comes to our mind, in order to minimize the difference, we should have both the arrays as sorted. So we should have the boys array in a sorted order, and we should also have a girls array in a sorted order. Why? Suppose boys are having 1 and 2 candies, and the girl is having, let's say, 4 and 3 candies, right? So if I pair the first boy with the first girl and the second boy with the third girl, then I know that this is not going to minimize the difference. So a good thing would be that I can place 3 here and I can place 4 here. So this will help me to minimize the difference. So here the difference will be now 2 and here it will be again now 2. So the first thing that is looking quite intuitive is that we should keep both the arrays sorted. Then we will figure out that a boy will be paired to which girl, right? So let me talk about the ith boy, right? So I can say the ith boy can be paired to the jth girl, right? To some jth girl, or it could be paired to some other girl in the remaining array, right? So if I do not pair the ith boy with the jth girl, it might be paired with some other girl, right, in the remaining array, right? Because every boy has to get a girl, but not vice versa. So every boy must get a girl. So either it should be the current girl or maybe some other girl in the remaining part. So for this boy, either it will get this girl, or if not this girl, it will get some other girl in this part. So again the same story will repeat. Either it will get the second girl or some other girl in the remaining part. Same thing will go for this one. So either it will get the current girl or it will get some other girl in the remaining part. So we will make our choices in such a way that total answer is minimized. Suppose if I pair the ith boy with the current girl. So if I pair the ith boy with the jth girl, so what I am going to get? I am going to get, let us say that the current array, this array is A, and let us say this array is B. So A array is for the chocolates array, B array is for the candies array. So if I pair, so suppose I am going to compute the answer for f of ij, or maybe, yeah. So this could be written as, it means I am pairing ith boy with the jth girl, and we have to, so in this case the contribution will be absolute value of ai minus bj plus the remaining answer for the remaining part. So remaining boys start from f of I plus 1 and the remaining girls start from j plus 1. So I can say it is going to be f of I plus 1 and j plus 1 if I pair the ith boy, right? Second option is I do not pair the ith boy with the jth girl. So I keep the boy and I call on the remaining part of the girls array to figure out, to let it pair with some other girl but not with the current girl. So I can directly call on f of I do not change because the current boy is not paired and the girls array is now shortened. So I call on the remaining part of the girls array and I take minimum of these two. I take minimum of these two. So this is going to be my recurrence for the problem. So this is the case when the boy is paired, and this is the case when the boy is not paired. Boy is paired with the current girl, and this is the case boy is paired later, paired with some other girl in the remaining part. And I have not taken this type of case f of I plus 1 and j because there is no possibility that a boy is not paired, right? So we can skip the girl but we cannot skip the boy. Every boy must get the girl. So now let us try to write this in our code and let us try to solve the problem. So I have a function called f ij, which denotes the final answer for I boys and j girls. And here I have taken input n and m, then I have input the array of chocolates, array of candies. I have also sorted them. I have also sorted both the arrays, right? And I'm going to use top down dp for solving this problem. This is a top down dp, and initially the values of I and j are 0 0 because we are starting from the 0th boy and the 0th girl. So we are starting from the 0th boy and the 0th girl. So either these will get paired. If not, the boy will get paired with some other girl from the remaining part, right? So these things will happen. So this is the function long f, which gets the I is the index for the boy, I is the index for boy, and j is the index for girl. And in the base case, if I reaches n, it means we have paired all the boys. We have paired all the boys, and the remaining part does not contain any answer. So answer should be 0. And if j equals to m, it means we have rejected all the girls. We are not using any girl. So it means some of the boys are left, but girls have finished. So we have rejected lot of girls and no girl is left, no girl is available for the boy. So it means this is not a valid configuration. This is something which we were not expecting to happen, but this has happened. So we can say return int max. So if I return int max, or maybe I can return infinity, so this will automatically make our answer going to reject this case. So as we are going to take minimum later on, so this case will be automatically rejected. So we will ignore those cases when we have rejected all the girls and no girl is available for the boy. So otherwise we have two options, right? So the first thing let me check is if dp of ij is already computed. If this value is not equal to -1, I can directly return this value. And if this value is being computed, then we have two options. So the first option is that we take the absolute difference of ai with bj, because we are pairing the ith boy with the jth girl and we are calling on the remaining part. So remaining part becomes f of I plus 1 and j plus 1. The other option is that we do not pair the current boy with the jth girl, and instead we call on the remaining girls array. So we can directly write f of I and j plus 1. We have rejected the jth girl. So this is the case by rejecting the jth girl, and this is the case by accepting the jth girl. And we have to take those cases which gives us the minimum answer. So dp of ij will contain minimum of option 1 and option 2, and this we are going to return. Now let us try to run our code on hacker blocks. Let us give this as the sample input and let us test it. So the answer is 0 for the current case. Alright, let me make the value as 6 here. In this case the answer should be 1. Yeah, so it is 1. I think this is perfectly fine, and let us submit it. So yes, we got all our test cases passed. Right, now let us talk about the complexity of this solution. So you can clearly see that we have taken a 2D dp array and dp of ij. So it is a 2D dp, right? And you can know that I can contain up to 5000 values and J can also contain up to 5000 values. So this is nothing but of the order n square, right? So of the order m into n. So this will get accepted. So I think this question is clear to you guys. Thank you for watching. I will see you in the next tutorial.